Hello there, and welcome to the Sleep Porch. Tonight, we'll be taking an epic journey into the wonders, mysteries, and marvels of our universe. Science has made remarkable progress in revealing this immense frontier. We've mapped galaxies, measured ripples in space-time, and uncovered the behavior of invisible yet powerful forces. But for every advance we make, more questions arise. The universe keeps its secrets well, and many of the ideas we've come to rely on may only be the first step of a much deeper reality. Space may be stranger than our models suggest. Time might not behave the way we assume, and even the foundations of matter and energy might just be fragments of a much grander theory. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Take a deep breath. Allow your shoulders to soften, and let the day fade away as we explore our amazing universe together. Let's begin. The universe may contain regions that are forever hidden from us. Beyond the boundaries of what we can observe, space continues to expand into areas whose light will never arrive here. Those distant regions are not merely far away. They are separated by the finite speed of light and by the expansion of space itself. Even with flawless instruments and more time than any human lifetime could allow, some parts of reality would still remain unreachable. Within those unseen domains, matter could organize into galaxies and structures that never sent a single photon toward us. Physics there might obey the same rules we know, or it might bend them in subtle ways we can never test. When we gaze at the night sky, we are looking at a small window into a much larger whole, aware that events are unfolding right now that no one here will ever observe. The universe may be filled with stories that will never be told. There could be entire regions of space governed by different laws of physics. Many modern theories propose that what we call the laws of nature may not be uniquely fixed. Certain ideas in cosmology and fundamental physics allow constants, such as particle masses and interaction strengths, to take on different values in different regions of a larger reality. In one cosmic domain, stars might never ignite. In another, atoms might be unstable, or entirely different kinds of matter might form. We only know the behavior of our own patch, where the numbers happen to support long-lived stars and complex chemistry. It is possible that beyond any horizon, there are expanses where even the idea of a stable atom would be impossible. Our familiar physics could be a local dialect spoken in a much larger landscape of possibilities. If that is true, then what we call fundamental might be more like a regional custom. One example among many, with no way for us to visit the others and compare. We still do not know what happened before the first moment of time. Our best cosmological models describe how the universe evolved from an early hot and dense state, but they do not fully explain what, if anything, came before. At very early times, gravity and quantum physics must both matter. Yet we do not yet have a single theory that combines them consistently. When we run the equations backward, they eventually stop giving meaningful answers, as if the mathematical surface of time itself ends. Some proposals suggest a prior contracting phase. Others imagine a bounce, and some describe time as emerging from something more primitive that does not resemble ordinary before and after. Observations of the sky give us clues about the early fireball, but they cannot directly pierce whatever lies beyond that veil. The question of a beginning may even be the wrong way to think about it. Yet our minds are drawn to it. What does it mean for time to start? And can there ever be a reason for the first instant? Space might be infinite, or it might loop back on itself. When we look out into the cosmos, we can measure how space is curved on vast scales. But those measurements do not yet tell us the global shape of everything. One possibility is that space extends without limit, stretching on forever with no boundary and never returning to where it started. Another is that space has a finite volume but no edge. Like the surface of a sphere generalized into more dimensions, so that if you could travel far enough in one direction, you might eventually return to your starting B point. Different shapes of space would subtly change the pattern of structures we see in the sky. But those differences are extremely delicate and hard to detect. Our observations so far are consistent with many possibilities. The true shape of all that exists could be simpler or stranger than we imagine, and we may never travel far enough to find out for certain. There could be invisible dimensions interwoven with the ones we see. We experience reality as having 3 directions of space and 1 of time. But some theories that try to unify the forces of nature work only if additional spatial directions exist. These extra directions could be curled up to sizes unimaginably small, so that we do not notice them in daily life. Their presence could gently affect how particles move and how gravity behaves, leaving only subtle traces in experiments and cosmic observations. In such a picture, every point in familiar space would really be a tiny, multidimensional structure, with paths that loop through directions our senses cannot follow. If these hidden dimensions exist, they might allow new kinds of particles, or even connect distant regions of space in ways we have barely begun to picture. Looking for them requires creative experiments and careful study of how the universe evolved. The idea that our world might be only part of a larger dimensional tapestry remains an open and profound possibility. We do not know what space itself is made of. We talk about space as if it were an empty stage, a smooth backdrop where matter moves and light travels. Yet, we do not truly understand whether that stage is fundamental or built from something deeper. Some approaches to quantum gravity picture space as emerging from discrete building blocks, perhaps a network of relations or tiny units of area and volume that only look continuous from far away. Others imagine space arising from patterns of quantum information, like a vast web of entanglement that gives rise to distance and geometry as collective effects. Even in ordinary physics, vacuum is not truly empty, but filled with fluctuating fields that can give rise to real particles. These hints suggest that the motion of a simple void may be an illusion. If space has an underlying structure, then at extremely small scales, our familiar concepts of location and distance might dissolve, replaced by something that does not fit our usual intuition. Time may flow differently in parts of the universe we cannot reach. Relativity tells us that the passage of time is not absolute. It depends on motion and on gravity. Clocks deep in gravitational wells tick more slowly compared to clocks far away, and objects moving at high speeds experience less elapsed time than those at rest. Across the universe, matter is arranged in complex ways, from dense clusters to vast empty regions, so the rate of time can vary from place to place. In distant galaxies, the rhythm of processes could be slightly offset from our own, even if no one there would notice the difference locally. In extreme environments near very compact objects, the difference becomes even more dramatic. with outside observers watching events unfold in slow motion. Because we cannot synchronize clocks across unreachable distances, we are left with a patchwork of local times woven together by theory. The idea that there is a single universal now becomes difficult to sustain once we take the cosmos into account. The universe might be one bubble among countless others. Certain theories of cosmic inflation suggest that the rapid expansion in the early universe might not have stopped everywhere at once. In some regions, expansion could have ended and cooled, forming bubbles where conditions stabilized enough for galaxies and stars to appear. In other regions, the accelerated growth could have continued, spawning further bubbles with potentially different properties. Our observable universe would then be one such bubble, occupying a finite domain in a much larger, inflating background. Other bubbles might never collide with ours, remaining forever separated by growing distances and by regions where space still stretches at an enormous rate. Within those distant domains, physics might take different forms, or perhaps echo our own in ways we will never confirm. This picture turns what we call the universe into one example inside a greater multiverse. It offers explanations for certain cosmic puzzles, yet raises even deeper questions about what counts as reality. There could be structures larger than anything we can observe. Astronomers have discovered clusters, filaments, and sheets of galaxies that span astonishing distances, weaving a cosmic web through space. Yet our surveys are limited by how far light has traveled since the early universe, and by the parts of the sky we have been able to study in detail. It is entirely possible that beyond the boundaries of current data, there are arrangements of matter even grander than the largest known formations. Perhaps superstructures that bend our assumptions about how uniform the cosmos should be. Some hints already challenge expectations, such as huge alignments that appear more coherent than standard models predict. Whether these are statistical flukes or glimpses of something deeper remains uncertain. If truly colossal structures exist beyond our horizon, their gravity could influence the motion of galaxies we do see, leaving only indirect signs of their presence. In that sense, unseen architecture might be quietly shaping the cosmos we can measure. We do not know whether the universe has an edge or no boundary at all. When we talk about the universe, it is natural to picture a region with some kind of border beyond which there is nothing. Yet in physics, the idea of an edge to space is problematic because edges usually imply something outside. One alternative is that the universe is finite, but curved in such a way that it has no boundary, like the surface of a sphere that ends nowhere, even though it has limited area. Another possibility is that space extends indefinitely, with no edge and no outside, only more and more of the same fabric. Our observations of the cosmic background and the distribution of galaxies tell us about geometry within the part we can see, but they do not conclusively answer the global question. Even our language struggles because we are trying to describe the totality of everything from within. Whether there is a true edge, a closed shape, or infinite extent remains one of the deepest open puzzles. The universe might be expanding into something we cannot perceive. When we measure the motion of distant galaxies, we find that space itself is stretching, carrying them farther from us. Yet the question of what this expansion is happening into remains unresolved. In standard cosmology, space does not need an outside. It can grow the way a pattern on a balloon grows, even if you focus only on the two-dimensional surface without considering the air around it. Still, it is difficult not to wonder whether the fabric of the cosmos is embedded in something larger. If such an external realm exists, it would not necessarily follow the rules of our own space or time. It might not contain matter, energy, or geometry as we understand them. Our instruments are designed to measure what happens within the universe, not beyond it. As a result, any wider container would remain hidden from view, leaving us to infer possibilities only through mathematics and the behavior of distant galaxies. The true nature of expansion remains one of the most puzzling questions in modern science. We still do not understand why space is so smooth on vast scales. Across billions of light years, the universe looks remarkably uniform. The temperature of ancient radiation varies only by tiny fractions, and matter spreads out in a pattern far more even than one might expect. This smoothness is surprising because regions separated by extreme distances could never have interacted in the early universe. There was simply not enough time for light or any other signal to travel between them. To explain this, theories propose a brief phase of extremely rapid growth that allowed regions now far apart to originate from a small connected area. Although this idea fits the data well, we still do not know what triggered that growth, how it ended, or whether alternative explanations might work. The uniformity we observe could carry information about processes that occurred before the earliest moments we can probe. Space may hold silent clues about a deeper mechanism that shaped the entire cosmos long before galaxies began to form. The universe could carry subtle imprints from events before its birth. The oldest light in the universe is a faint glow that has traveled across space for almost the entire cosmic history. Although it has been studied with great precision, it might contain traces of processes that happened even earlier than the hot, dense state usually described as the beginning. Certain models of cosmic evolution predict that ripples, patterns, or slight distortions might survive from an earlier phase, carried forward as the universe expanded and cooled. These features would be extremely delicate, hidden within the noise of cosmic data, and difficult to distinguish from ordinary fluctuations. If they exist, they could reveal information about conditions that no current experiment can recreate. They might hint at a prior contraction or a more complex transition that preceded the familiar expansion. The possibility that our universe retains the fingerprints of an earlier era invites the idea that the cosmos has a longer and richer story than we can presently observe. There may be hidden patterns in the cosmic web we have not recognized. When astronomers map the distribution of galaxies, they discover a sprawling network of clusters, filaments, and great empty voids. This intricate web resembles the structure of living tissue or neural pathways, showing how gravity shaped matter on the largest scales. Yet we may only be seeing the most obvious layer. Deeper mathematical relationships might link the positions and motions of galaxies in ways we have not yet noticed. Subtle symmetries could be present in the alignment of structures, or long-range correlations might exist that require new tools to detect. Even the way galaxies rotate or cluster might follow hidden rules that have gone unrecognized. As surveys grow more detailed, they may reveal unexpected organization buried within the apparent randomness. Patterns like these could hint at undiscovered physics or at early cosmic processes that left long-lasting effects throughout the web of matter that stretches across the universe. the universe might end in ways we cannot yet imagine. Cosmology offers several possible futures, yet none are certain. If dark energy remains steady, space will continue expanding at an ever-increasing rate, gradually isolating galaxies from one another until the night sky grows empty and cold. If dark energy strengthens, the expansion could accelerate so dramatically that even atoms might eventually be pulled apart. If dark energy weakens or reverses, the universe could slow, halt, and collapse into a dense state, possibly leading to a new expansion. Other possibilities involve transitions in the underlying vacuum of space, changes in physical laws or processes we have not yet formulated. Because we cannot measure the future behavior of dark energy or the stability of the vacuum, we face fundamental uncertainty about how the story of the universe concludes. Each scenario shapes matter and time in profoundly different ways. The vast future remains an open landscape of possibilities, each hinting that our cosmic era is only one chapter in a much longer narrative. There could be cycles of cosmic creation beyond our horizon. Some theoretical frameworks imagine that the universe did not begin with a single event, but instead passes through repeating phases of contraction and expansion. In such a picture, our own cosmic history would be part of a larger sequence, with previous cycles imprinting subtle hints on the structure we observe today. Although these ideas are difficult to test, they offer explanations for certain puzzles about uniformity and fine structure. If the universe has experienced multiple cycles, then each era might inherit conditions shaped by those that came before. Entire sequences of galaxies, stars, and cosmic evolution could have risen and faded long before our own epoch, leaving few traces except possibly in the earliest moments of the current expansion. These cycles might continue far into the future, forming a grand rhythm of creation and transformation that lies beyond our observable domain. Whether such patterns truly exist remains unknown, yet they provide a striking alternative to a single beginning. We do not know what started the rapid expansion of the early universe. Observations strongly support the idea that the universe underwent a brief period of extremely fast growth shortly after its earliest moments. This expansion smoothed out irregularities and set the stage for the formation of galaxies. However, the cause of this rapid growth remains mysterious. Proposed explanations include new fields of energy, transitions between physical states, or deeper mechanisms that might involve the fabric of space itself. Each proposal attempts to account for the characteristics we see today in ancient radiation and the arrangement of matter. Yet none has been confirmed, and several predict effects that are very subtle. Without a way to directly examine the conditions of that early time, we must rely on indirect clues and careful analysis of cosmic patterns. The true trigger of this expansion remains an open question, and understanding it may require insights that unify ideas about gravity, quantum physics, and the origin of space. The universe might have dimensions curled too small to detect. Some theories that aim to unify the forces of nature suggest that in addition to the familiar 3 dimensions of space, there may be extra directions folded into extremely tiny shapes. These compact dimensions would be far smaller than any current experiment can probe, hidden within the structure of each point in space. Their geometry could influence particle behavior, alter gravitational interactions, or allow new types of motion that cannot occur in ordinary space. Although these dimensions would not be directly visible, their presence might produce small deviations in measurements of particle collisions or leave faint signatures in the early universe. Searching for these effects requires precise instruments and creative experimental designs. If such curled dimensions exist, they would imply that our everyday experience captures only a small part of a much richer spatial environment.
The universe might be built on a multidimensional foundation that remains almost entirely concealed. We do not know whether space emerges from something deeper. Modern research has raised the possibility that space is not a fundamental entity, but instead arises from more basic components. In some models, geometry is produced by patterns of quantum information or by networks of relationships between microscopic elements that do not resemble locations in any ordinary sense. Distances, directions, and even the flow of time could be large-scale consequences of these underlying structures. Evidence for such ideas comes from studies of black holes and quantum physics, where traditional concepts break down and new principles appear to link geometry with information. Although these ideas are still speculative, they offer a route toward unifying gravity with the world of particles. If space is emergent, then familiar reality might be analogous to a surface formed from countless unseen interactions. Understanding the deeper layer could change the way we think about the fabric of the universe and the nature of existence itself. The universe could be a projection of a more fundamental reality. Certain approaches to quantum gravity suggest that the three-dimensional world we experience may be encoded on a lower dimensional structure, somewhat like a hologram. In these ideas, the full complexity of space and matter emerges from information encoded on a surface with fewer dimensions than the space it represents. This notion grew out of black hole research, where the information required to describe them appears to scale with surface area rather than with volume. Extending that insight to the entire universe suggests that reality may have an unexpected kind of architecture. This does not imply that the universe is an illusion, but it does hint that our everyday sense of depth and location might be secondary to more fundamental principles. Experiments and observations are starting to probe pieces of these ideas, yet the question is still very much unresolved. The idea that the cosmos could be a projection unsettles many intuitive assumptions and opens new paths for describing the foundations of physics. Dark energy itself may be changing over time in ways we cannot yet measure. Astronomers have found that the universe's expansion is accelerating, a discovery commonly linked to an unknown influence known as dark energy. Yet we do not know whether this mysterious force is constant or shifting over cosmic time. Our measurements cover only a narrow slice of the universe's history, and any slow variation would be extremely difficult to detect. If dark energy changes, it could alter the ultimate fate of the cosmos, either strengthening to drive galaxies apart ever faster, or weakening enough for gravity to slow the expansion in the distant future. It might even undergo transitions, behaving differently in past eras than it does today. The difficulty lies in the fact that dark energy does not interact directly with matter or light. We infer its presence only through the motion of galaxies and the geometry of space. Subtle changes could hide beneath current uncertainties, waiting for more precise observations or new ways of mapping cosmic history. The nature of dark energy remains one of the most profound mysteries in physics. Dark matter could be something entirely outside known physics. We observe the influence of an unseen mass that surrounds galaxies and shapes the large-scale structure of the universe. This invisible matter does not emit light or interact strongly with normal atoms, although many theories attempt to explain it using new particles. Another possibility is that dark matter does not belong to the familiar family of forces and interactions at all. It could arise from a sector of physics that barely touches the one we experience. In such a scenario, dark matter might have its own kinds of particles, motions, and internal processes, operating in a shadow-like framework that rarely influences ordinary matter except through gravity. This idea opens the door to entire worlds of behavior that remain hidden from every detector on Earth. If dark matter truly lies outside known physics, then solving its nature will require ideas beyond the standard approaches. Its presence could be a clue, but our view of reality captures only a fraction of what exists. There might be particles passing through us that we cannot yet detect. Even within the known laws of physics, countless particles move through space constantly.
Some are familiar, such as neutrinos, which pass through matter with little interaction. Others may exist beyond our current understanding. These hypothetical particles could permeate the cosmos, drifting through planets, stars, and living beings without leaving detectable traces. Their interactions might be so weak or so unusual that they escape every current instrument. Some theories predict particles that rarely collide with normal atoms, while others propose entities that do not fit the usual categories of matter and energy. The Earth might be immersed in a sea of undetected particles that influence cosmic evolution, yet remain invisible to us. Each new generation of detectors reaches further into this landscape, searching for signs in faint flashes of light, subtle vibrations, or rare collisions. The possibility that unknown particles are quietly passing through us every moment suggests that much of reality may be hidden just beyond our reach. Dark matter could form structures as complex as the visible universe. Although dark matter is invisible, its gravity affects everything around it. Models of cosmic evolution often show dark matter gathering into halos that guide the formation of galaxies. Yet, these halos might not be simple clouds. They could contain layers, clumps, waves, or patterns shaped by interactions within the dark sector. If dark matter has its own forces or particle families, it might be capable of forming structures as varied as those made of atoms. These structures would not emit light, but they could influence the motions of stars and gas, shaping galaxies in ways we have not yet recognized. Some simulations suggest that dark matter might form filaments within halos or support long-lived patterns that affect how galaxies rotate. Discovering such structures would require incredibly detailed observations and new theoretical tools. The idea that an unseen architecture coexists alongside the visible cosmos highlights how limited our perspective may be. Dark energy might interact with matter in ways we have not observed. Most interpretations treat dark energy as something that influences only the expansion of space, not the behavior of matter. However, some theoretical models allow for a faint connection between dark energy and the particles that make up stars and galaxies. If such an interaction exists, it could cause subtle shifts in the masses of particles with the strength of forces over vast periods of time. These tiny changes might accumulate across cosmic history, leaving patterns in the distribution of galaxies or affecting the rate at which structures formed. So far, no clear evidence for such interactions has appeared. Yet the possibility remains open because the required effects could be extremely small. Future surveys that examine distant galaxies more precisely may reveal signs of a hidden dialogue between dark energy and matter. If this connection exists, it would reshape our understanding of how the universe evolves
and reveal a bridge between two of its most mysterious components. There could be multiple types of dark matter hidden in plain sight. Most discussions of dark matter assume that it is composed of a single kind of particle. Yet nature often prefers variety. Ordinary matter includes atoms, molecules, plasma, dust, and countless other forms. Dark matter might be just as diverse. Some types could be cold and slow-moving, others warm and faster, and still others could bind into composite objects through interactions within the dark sector. Each type would influence galaxy formation differently, creating a much richer landscape than most simple models predict. Because dark matter does not emit light, this diversity would not be visible directly. Instead, the mixture might reveal itself through subtle features in the motion of stars or the shapes of galaxies. Understanding such complexity would require new methods of analyzing cosmic data and new theories that allow dark matter to have internal structure. The idea of multiple unseen components hints that the dark side of the universe could be far more intricate than we imagine. Dark energy could hint at a deeper layer of reality we do not see. The discovery of accelerated expansion forced physicists to consider that the vacuum of space contains energy with unusual properties. This energy does not behave like matter or radiation. Its effects suggest that space itself has an underlying structure that influences how it stretches. Some proposals link dark energy to quantum fields that fill all of space, while others connect it to geometric features that emerge from deeper principles.
If dark energy reflects a hidden layer of reality, then our familiar understanding of space might be only a surface-level description. The behavior of dark energy could reveal information about this deeper framework. Yet, we currently lack the tools to probe it directly. Observations of distant supernova, galaxy clustering, and the cosmic background provide clues, but the full picture remains obscure. Dark energy may be the most accessible sign that reality contains levels we have not uncovered. Dark matter might be a shadow of processes in higher dimensions. Some theoretical models propose that our universe contains more spatial directions than we can perceive. If higher dimensions exist, dark matter might be an echo of processes occurring within them. In this view, particles we detect only through gravity might be objects moving or interacting in directions unseen by ordinary senses. Their apparent invisibility could be a natural consequence of their higher dimensional nature. They would interact weakly with familiar matter because they occupy different slices of reality. Yet their mass would still tug on stars and galaxies. This idea offers possible explanations for why dark matter behaves differently from ordinary particles and why it forms large halos around galaxies. Detecting such effects would require looking for small deviations in gravitational behavior or searching for signs of extra-dimensional motion. If dark matter is truly linked to higher dimensions, discovering its nature would change our understanding of what space itself can be. There could be entire stars made mostly of dark matter. If dark matter can clump under gravity, it might gather in high enough concentrations to form compact objects. In some cosmological scenarios, dark matter could collapse into dense regions that behave like stars, yet without nuclear reactions or visible light. These dark stars would be practically invisible to telescopes that rely on electromagnetic radiation. Instead, their presence might be revealed through gravitational influence alone. Some theories imagine dark matter particles that can release energy through exotic interactions, allowing dark stars to shine faintly in ways we have not yet identified. Others picture them as cold, quiet bodies drifting through galaxies, leaving only subtle gravitational footprints. Finding such objects would require precise mapping of stellar motions or gravitational lensing. The existence of dark stars would add an entirely new category to the cosmic inventory,
showing that the universe contains kinds of stellar bodies fundamentally different from anything we have ever seen. Dark matter might carry information about ancient cosmic eras. Because dark matter interacts so little with ordinary particles, it has preserved its original properties across almost the entire history of the universe. While atoms were broken apart, fused and reshaped in stars, dark matter remained largely unchanged. Its distribution today still reflects the conditions that existed long before galaxies formed. If we could decode its structure, we might learn about epochs that no radiation can directly reveal. For example, slight variations in dark matter density might reflect events in the very early universe, or transitions that occurred before familiar particles emerged. Mapping these patterns requires detailed observations of how galaxies move within their halos and how matter clusters on different scales. Each measurement provides a hint of the ancient landscape that shaped the cosmos. Dark matter serves as a quiet record keeper of eras beyond direct observation, storing information in the way it is arranged across space. Black holes may contain regions where the fabric of reality breaks down. When matter collapses under a term gravity and forms a black hole, the equations of general relativity predict that spacetime curves more and more sharply toward the center. At some point, these equations indicate that curvature becomes infinite. This is a sign not of a literal infinity, but of the failure of our current theories. Near such extreme conditions, the familiar rules of space, time, and physics may dissolve. Quantum effects should become important. Yet we do not have a complete theory that unites quantum mechanics with gravity. As a result, the interior of a black hole remains an unsolved frontier. Physical quantities that behave smoothly elsewhere may no longer make sense. Even the concept of location could break down. This mysterious region is hidden from the outside world by the event horizon, so no signal can carry direct information outward. The unknown interior remains one of the most dramatic reminders that our understanding of reality is incomplete. A black hole center could be something other than a singularity. Although classical theory predicts a point of infinite density at the core of a black hole, many researchers believe that nature avoids true infinities. Alternative models propose that quantum effects could replace the singularity with something more complex. Some ideas picture a region of extremely high but finite density. Others describe a tiny sphere where quantum pressure counteracts gravity. Still others imagine a surface where space-time undergoes a phase transition. These possibilities depend on how quantum gravity operates. And since that field remains under development, no single answer has emerged. Observations of black holes do not reveal their centers, so indirect evidence must be used. The behavior of gravitational waves, the motion of matter near the event horizon, and the stability of black holes over long periods may offer clues. Each scenario implies a different internal structure, suggesting that black holes might contain exotic states of matter or geometry unlike anything we have studied in laboratories. There might be paths through black holes that lead elsewhere. The mathematics of general relativity allows solutions where black holes connect to distant locations or even other universes through hypothetical bridges. These structures are often unstable and may collapse too quickly for anything to pass through. Yet they remain intriguing possibilities. If quantum effects modify the interior, such pathways might become more stable in certain models. A traveler attempting to cross would face enormous tidal forces and unpredictable physical conditions, making any journey purely theoretical for now. Some theories propose that what appears to be a black hole from the outside could be connected to a different region that looks like a white hole from within, ejecting matter instead of absorbing it.
These concepts arise naturally in the equations of gravity. Yet we lack evidence to determine whether any of them correspond to real physical objects. Even so, the idea that black holes might serve as gateways hints at a universe more interconnected than our senses suggest. Black holes could store information in ways we do not understand. A long-standing puzzle in physics concerns what happens to information carried by matter that falls into a black hole. Quantum theory insists that information cannot be destroyed. Yet classical black holes appear to erase the details of anything that enters. Efforts to resolve this contradiction have led to the idea that information might be encoded in subtle patterns on the event horizon, or stored in quantum states of the gravitational field. Some proposals suggest that the horizon behaves like a physical surface, with an enormous number of microscopic degrees of freedom. Others propose that information is released slowly through radiation during the black hole's lifetime. None of these ideas are fully proven, and each raises new questions about how information is represented in spacetime. The resolution of this puzzle could reveal a deeper connection between quantum theory and gravity, showing how the universe preserves its history even in the most extreme environments. There might be tiny, primordial black holes scattered through the cosmos. In the very early universe, density fluctuations could have been large enough in some regions to collapse directly into small black holes. These primordial objects would not have formed from stars, so their masses could range from extremely small to quite large. If they exist, they might contribute to dark matter or influence cosmic evolution in subtle ways. Some might have evaporated completely, while others could still drift through galaxies invisibly. Their presence might be revealed through gravitational lensing of distant stars, through disruptions in the motions of objects, or through faint radiation produced during their final stages of evaporation. Despite careful searches, no confirmed detection has yet been made. The possibility of primordial black holes remains open, offering a link between the physics of the early universe and the dark matter puzzle. If they are real, they would provide a direct window into conditions that existed long before the first stars formed. We do not know what happens at the very edge of a black hole. The boundary that separates the interior of a black hole from the outside universe is called the event horizon. It is not a solid surface, but a region where escape becomes impossible. Although general relativity predicts how the horizon behaves, quantum effects complicate the picture. According to theory, the horizon emits radiation due to quantum processes, yet the detailed mechanism remains unclear. Some research suggests that the horizon might have a complex structure influenced by quantum information. Others picture it as a smooth boundary with no special features. Because we cannot observe the horizon up close, our understanding relies heavily on theory. The behavior of particles, light, and information near this boundary may hold clues about the unification of physics. The edge of a black hole is a frontier where known laws reach their limits, making it a key area of study for anyone seeking a deeper understanding of gravity and quantum mechanics. Black holes could evaporate in ways we have never observed. Quantum theory predicts that black holes emit radiation, slowly losing mass over extremely long timescales. This process, while theoretically robust, has never been directly observed because even small black holes evaporate far too slowly for current detectors. Some models suggest that evaporation might include bursts of energy or changes in the spectrum of the emitted radiation at late stages. Others propose that the final moments could reveal new physics involving exotic particles or transitions in the nature of space-time.
If evaporation proceeds differently from the standard picture, it could alter our understanding of energy conservation, information preservation, and the life cycle of black holes. Detecting these signals would require either an unexpectedly small black hole near Earth or a new method for observing extremely faint radiation across the cosmos. The final fate of black holes remains an open question, one with profound implications for the nature of the universe. Some black holes might have formed before the first stars existed. Most black holes arise from massive stars collapsing at the end of their lives. However, conditions in the early universe may have allowed black holes to form directly from dense regions of primordial gas. These black holes would predate the first stars and galaxies, acting as seeds that influenced early cosmic structure. Their growth could help explain how some supermassive black holes became so large so quickly, an ongoing puzzle in astronomy. Early black holes might have interacted with the surrounding gas, altering the rate at which the first stars formed. Observations of ancient quasars reveal extremely massive black holes at times when the universe was still very young. Understanding how these giants arose may require the existence of an earlier generation of black holes formed through mechanisms unrelated to stellar evolution. These ancient objects would provide insight into the earliest chapters of cosmic history. Black holes could shape the universe more than we realize. Although black holes are often pictured as isolated objects, their influence extends far beyond their immediate surroundings. The largest galaxies appear to have enormous black holes at their centers, and the energy released by matter falling into these giants can shape the growth of the entire galaxy. Jets of high-energy particles can heat or disperse gas, regulating star formation across vast regions. Even smaller black holes can influence their environments by triggering bursts of radiation or stirring the motion of nearby matter. On cosmic scales, the collective activity of black holes may affect how structures evolve, how galaxies cluster, and how gas circulates between regions. These effects, although indirect, can reshape entire regions of space over immense periods of time. The role of black holes in cosmic evolution is still being uncovered, hinting that they are not merely endpoints of stellar life, but engines that drive large-scale transformations. There may be hidden black holes that emit almost no light at all. Most known black holes are discovered through the radiation produced by hot gas spiraling into them. However, many black holes may exist in quiet environments where little matter falls inward. These objects would be almost completely dark, detectable only through their gravitational pull. Some may drift through space alone. Others may reside in the outskirts of galaxies or within star clusters. Finding them requires careful analysis of stellar motions, gravitational lensing, or rare interactions with surrounding objects. The universe could contain far more black holes than current observations suggest, with many remaining invisible. These silent black holes hold clues about stellar evolution, galactic dynamics, and the unseen population of remnants scattered throughout the cosmos. Their existence reminds us that much of the universe may be made of objects that reveal themselves only through subtle gravitational effects. Gravity might behave differently on scales larger than galaxies. Astronomers have tested gravity with remarkable accuracy inside our solar system and within galaxies. But across the largest scales of all, it becomes much harder to know whether the familiar equations still hold. The motions of galaxies inside clusters, the speed at which vast structures form, and the patterns imprinted in ancient cosmic light all rely on gravity operating over immense distances. Some measurements point to small tensions between prediction and observation, hinting that gravity might alter its behavior ever so slightly when extended across enormous scales. These differences could be minute, yet still powerful enough to influence how the universe expands or how large cosmic structures take shape. A number of ideas suggest that gravity could weaken, strengthen, or subtly change character in the emptiest regions of space. Others propose that such effects arise because the universe is not perfectly uniform. Sorting through these possibilities demands deeper surveys, more precise models, and new methods for testing gravity across cosmic environments far beyond anything reachable in laboratories. There may be unseen forces at work across the vast distances of the cosmos. In addition to gravity, the universe may host long-range forces that barely affect everyday matter, but shape the cosmos in subtle ways. These hypothetical forces could influence how galaxies move or how clusters evolve. They might act extremely weakly, making them difficult to detect within the solar system, yet influential across billions of light years. Some theories predict that these forces emerge from new fields that fill all of space, guiding the behavior of dark matter or interacting with matter only through delicate channels. Such forces could help explain unusual motions within galaxies or unexpected patterns in cosmic structure. Detecting them would require precise observations of distant objects, careful comparison with theoretical predictions, and a willingness to consider that the universe might include influences far beyond the familiar. 4 fundamental interactions. If hidden forces exist, they would reveal an enriched and more intricate picture of cosmic behavior. Gravity might be linked to quantum information in a way we do not yet see. Ideas from quantum theory and general relativity increasingly suggest that spacetime might be connected to the flow of information. In some approaches, the curvature of space could emerge from the structure of microscopic quantum states, with gravity arising as a large-scale consequence of how information is organized. This perspective connects the bending of light, the motion of planets, and the behavior of black holes to deeper patterns involving entanglement and quantum correlations. If this link is real, then classical gravity might be the visible expression of an underlying informationational fabric. Evidence for these ideas comes from studies of black hole thermodynamics and from mathematical correspondences between geometry and quantum systems. Yet no direct experiment has confirmed the connection. Understanding it may require entirely new tools that bridge the gap between quantum physics and gravity. This possibility hints that the universe's geometry may not be fundamental, but instead a reflection of hidden formational rules. The universe could contain gravitational phenomena we have not imagined. Most of our understanding of gravity comes from observing planets, stars, black holes, and large-scale structures. Yet the universe is vast enough that phenomena unknown to us may occur under extreme conditions or in regions we have not yet explored. There might be exotic gravitational configurations where space-time behaves in ways not described by simple curvature. Strange objects could exist that bend space in asymmetrical or unpredictable patterns. Regions with unusual forms of matter might produce entirely new gravitational effects that have left only faint or indirect signs in observable data. As our instruments improve, we may uncover hints of these unfamiliar behaviors, perhaps in gravitational wave signals or in anomalies found in the distribution of distant galaxies. The full diversity of gravitational possibilities may extend well beyond our current theories, waiting to be discovered in the deep reaches of the cosmos. There might be regions where gravity temporarily weakens or strengthens. The strength of gravity is usually treated as constant, yet in some theoretical frameworks, it could vary slightly in time or space. These variations might arise from fields that evolve slowly across cosmic distances, or from interactions between gravity and unknown components of the universe. If gravity fluctuates gently, These changes would be far too small to notice on Earth, but they could influence cosmic evolution over immense periods. Regions where gravity is slightly stronger might form structures earlier, while weaker regions might delay the growth of galaxies. Observations of distant clusters and the cosmic web, they hold subtle signs of such variations. Distinguishing them from ordinary cosmic variability is challenging, requiring careful analysis of large datasets and sophisticated simulations.
If gravity does shift in strength, even by tiny margins, it would imply a deeper and more dynamic foundation underlying one of nature's most familiar forces. Gravity could leak into dimensions beyond our own. Some theories propose that gravity might not be confined to the familiar three-dimensional space we inhabit. Instead, it could spread into additional spatial directions that are hidden from ordinary perception. If so, gravity would appear weaker than expected in our three-dimensional world because part of its influence would extend into these unseen directions. This idea could help explain why gravity is so much weaker than other forces. It might also produce distinctive patterns in experiments designed to detect tiny deviations from Newtonian behavior. On cosmic scales, gravity leaking into higher dimensions could influence the rate at which structures grow, or contribute to the accelerated expansion of the universe. Although no conclusive evidence has been found, the possibility remains compelling because it integrates naturally with theories that attempt to unify the fundamental interactions. Discovering extra-dimensional effects would reshape our understanding of space, matter, and the behavior of the cosmos. The gravitational constant might not be constant everywhere. The constant that sets the strength of gravity plays a central role in every astronomical calculation. Yet we do not know whether it is truly fixed across space and time. If it varies even slightly, it could influence the formation of stars, the behavior of galaxies, and the evolution of the universe. Subtle shifts might occur due to interactions with unknown fields, or due to processes that began in the early universe. Observations of distant objects offer indirect tests, yet distinguishing true variation from ordinary astrophysical differences is extremely challenging. Some studies have searched for signs in the timing of pulsars, the brightness of supernova, or the distribution of galaxy clusters. So far, results remain inconclusive. If future measurements reveal that the gravitational constant changes, it would indicate that gravity is not a simple universal force, but a dynamic quantity shaped by deeper layers of physics. The way gravity works near the beginning of time is still unknown. As we trace cosmic history backward, conditions become increasingly extreme. Temperatures rise, densities climb, and quantum effects become significant. Under such circumstances, general relativity alone cannot describe gravity. We need a theory that unifies gravity with quantum physics. Yet, that theory remains incomplete. Without it, we cannot fully understand how space curved or how matter behaved during the earliest moments after the beginning of the universe. Clues may be hidden in the pattern of ancient cosmic light, in the distribution of large-scale structures, or in the behavior of gravitational waves. These hints suggest that gravity may have operated differently at that time, perhaps allowing phenomena that no longer occur. The early universe represents a laboratory with conditions impossible to recreate on Earth. Understanding gravity in that environment remains one of the most pressing challenges in cosmology. There could be particles that mediate gravity in subtle ways. In quantum field theory, forces are often transmitted by particles. If gravity follows a similar pattern,
it might be mediated by a hypothetical particle. Such a particle would interact extremely weakly, making it nearly impossible to detect in experiments. Its existence could influence gravitational waves, modify the behavior of black holes, or subtly affect how matter clusters on large scales. Some theories predict families of such particles, each contributing in different ways to the overall behavior of gravity. Detecting them would require methods capable of isolating incredibly faint signals or observing effects that accumulate over cosmic distances. These particles may also interact with unknown fields or dimensions, complicating their behavior. If they exist, they would provide a direct route toward unifying gravity with quantum theory, revealing the microscopic structure behind the force that shapes the cosmos. Gravity might arise from something deeper than space-time. The familiar picture of gravity as the curvature of space-time may be an approximation of a more fundamental process. In some models, gravity emerges from the collective behavior of microscopic constituents that do not resemble space at all. These constituents could be quantum bits of information, relational structures, or other entities that operate according to rules unlike any classical theory.
Space-time itself would then be a large-scale phenomenon, much like temperature arises from microscopic motion. If gravity is emergent, then understanding its true nature requires identifying the underlying components and the principles that govern them. Evidence for this idea comes from connections between thermodynamics, information theory, and black hole physics. Although still speculative, the concept offers a unified way to link gravity with quantum mechanics. It suggests that our sense of space, time, and curvature may be secondary effects shaped by an unseen foundation that determines how the universe behaves at its deepest level. The first stars may have been unlike anything in the modern universe. Astronomers believe the earliest stars formed from pristine gas containing only hydrogen and helium, the simplest elements created in the first minutes of cosmic history. Without heavier elements to cool the gas efficiently, these stars may have grown far more massive than anything that typically forms today. Some theories suggest that they reached hundreds of times the mass of the Sun, burning at extraordinary temperatures and living for only brief periods before collapsing or exploding. Their interiors may have produced the first heavy elements, seeding later generations of stars and shaping the chemistry of the universe. Because these earliest giants lived fast and died young, they vanished long before any galaxy reached maturity. Detecting traces of them requires studying faint signals imprinted on ancient cosmic light, or observing extremely distant galaxies where their influence remains embedded in the distribution of gas. The nature of these first stars remains unknown, yet they set the stage for everything that followed. We do not know how the first galaxies formed so quickly. When telescopes peer back into very early cosmic times, they reveal galaxies that appear surprisingly mature. Despite the short intervals since the first stars ignited, these early galaxies contain structured regions, vigorous star formation, and sometimes even central black holes. Standard models predict that assembling such complex systems should require longer periods than the universe appears to have given them. This mismatch has prompted renewed study of how gas collapses, fragments, and ignites under primordial conditions. It also raises questions about whether our theories correctly describe how matter behaved during the first few 100 million years. New observations continue to find surprisingly bright and organized early galaxies, deepening the puzzle. These discoveries hint that early cosmic environments may have fostered rapid growth through processes not yet fully captured in simulations. The first galaxies remain key to understanding how the large-scale structure of the universe emerged from initial fluctuations.
Some ancient galaxies look far older than they should be. Observations of extremely distant galaxies sometimes reveal systems that appear too massive, too bright, or too chemically enriched for their age. These galaxies formed when the universe was still in its infancy, yet they display properties expected of far later epochs. Their stars can show signs of earlier generations, even though there should not have been enough time for multiple cycles of formation and evolution. This tension challenges models of galaxy growth, prompting scientists to examine whether star formation was more efficient in early conditions, or whether unknown mechanisms accelerated their development. Some of these galaxies may have undergone rapid mergers, while others may have collapsed unusually quickly from dense pockets of primordial gas. Each explanation carries implications for cosmology, suggesting that our picture of early cosmic timelines may need refinement. These ancient outliers remain compelling markers of unexplained processes that shape the earliest structures in the universe. There could be stars made almost entirely from exotic particles. Most stars shine through nuclear fusion of familiar elements, but some theories propose the existence of stars composed partly or entirely of exotic forms of matter. These hypothetical objects might use dark matter interactions as an energy source, or they might consist of particles that do not follow the usual rules of nuclear physics. If such stars exist, they would behave differently from ordinary ones. Their temperatures, lifetimes, and internal structures could diverge dramatically from standard expectations. They might emit unusual spectra or produce neutrino signatures unlike any known stellar process. Detecting them would require careful searches for stars that appeared too dim, too bright, or too stable for their mass and age. These exotic stars would offer direct insights into unfamiliar physics, showing that starlight may not always come from the same kinds of processes that power the familiar cosmos. We do not know how supermassive black holes grew so fast. Giant black holes, millions or billions of times the mass of the Sun, exist in galaxies throughout the universe. Yet observations show that some of these giants were already enormous when the universe was still very young. Their rapid growth poses a challenge because known processes of accretion and merging do not seem efficient enough to build such massive objects so quickly. Several ideas attempt to resolve this puzzle. Some propose that the first black holes formed from stars far larger than any seen today. Others suggest that entire clouds of gas may have collapsed directly into black holes without forming stars first. Another possibility is that early environments allowed unusually rapid feeding rates. Each explanation requires conditions that differ from those found in the modern universe. Understanding how these giants emerged so early is essential because they influenced the evolution of the first galaxies and shaped large-scale cosmic development. Some galaxies appear to lack dark matter for reasons we cannot explain. Dark matter is thought to be essential for galaxy formation, providing the gravitational framework that holds stars and gas together. Yet a handful of observed galaxies seem to contain far less dark matter than expected, and in some cases, almost none at all. Their stars move more slowly than predicted, suggesting that dark matter does not dominate their mass. These unusual systems challenge widely accepted ideas about how galaxies form and evolve. Some hypotheses propose that interactions with neighboring galaxies stripped away dark matter, while others suggest that these galaxies may have formed through processes not yet understood. Observing them more closely may reveal whether they truly defy expectations, or whether hidden complexities in their structure mask the presence of dark matter. These galaxies remain rare but important, offering unexpected insights into the diversity of cosmic evolution. There could be entire galaxies made mostly of invisible matter. While some galaxies appear to lack dark matter, others might be composed almost entirely of it. Such galaxies would contain very few stars, making them extremely faint and difficult to detect. Their presence could be inferred only through gravitational effects on nearby objects or through subtle lensing of background light. If these dark-dominated galaxies exist, they might account for a portion of the missing matter in the universe and provide clues about how dark matter behaves on galactic scales. They might form in regions where normal matter could not cool efficiently or where star formation was suppressed. Studying them would deepen our understanding of how structure forms in the dark sector and how galaxies assemble under a wide range of initial conditions. Discovering even a few would dramatically expand our view of what counts as a galaxy. There might be stellar objects that do not fit in any known category. Astronomers classify stars into familiar groups based on temperature, mass, and composition. Yet surveys occasionally reveal objects that defy simple categorization. Some appear too cool to be stars, but too warm to be planets. Others show chemical signatures or brightness patterns that do not match standard models. These oddities may represent previously unknown stages of stellar evolution or entirely new kinds of objects shaped by exotic physical processes. They could be remnants of unusual formation histories or products of environments not seen elsewhere. Understanding them requires detailed observation and creative thinking about how matter behaves under unexpected conditions. Each new anomaly challenges the boundaries of established classifications, reminding us that the universe may host forms of stellar structure that are rare, fragile, or simply unfamiliar. They could be ancient cosmic structures we have not yet seen. The observable universe contains clusters, filaments, and other large-scale formations. But our surveys cover only a limited portion of the cosmos. Beyond the reach of current instruments, there may be structures older, larger, or more complex than any mapped so far. These might include massive collections of galaxies, unusually shaped regions of cosmic voids, or patterns imprinted by early processes that no longer operate. Some features may be so faint or diffuse that they blend into the background, while others may lie beyond our observational horizon. As telescopes and analysis techniques improve, we may uncover hints of these hidden structures through gravitational effects. Subtle warping of ancient light or surprising alignments could point to such effects. Discovering them would deepen our understanding of how matter organized itself across cosmic time. Some stars may also end their lives in ways we do not yet understand. Most stars follow well-mapped paths from birth to final collapse. Yet certain observations reveal stellar deaths that do not fit standard explanations. Some explosions shine far brighter or dimmer than their mass would predict. Others leave behind unusual remnants or release energy in patterns that strain known physics. In some cases, stars may collapse straight into black holes without any visible explosion, while others may only partially collapse, leaving behind exotic cores. These irregularities suggest that the internal processes governing stellar endings may involve layers of complexity missing from current models. Investigating such events demands rapid detection, coverage across many wavelengths, and careful comparison with theoretical expectations. The many different ways stars reach their final moments remind us that stellar evolution still holds unresolved mysteries. Neutron stars might hide states of matter unknown on Earth. Inside a neutron star, matter is compressed to densities far beyond anything achievable in laboratories. Under such conditions, atoms no longer exist in familiar forms. Electrons are forced into protons, forming an immense sea of neutrons, packed together with almost no empty space between them. Yet, even this description may be too simple. The pressure in the core could become so extreme that neutrons break down into their constituent particles or rearrange into entirely new states of matter. Some models predict a fluid of quarks, while others imagine strange particles that appear only under the most intense compression. These extreme environments may host behaviors not found in any other place in the universe. Because we cannot probe neutron star interiors directly, we rely on clues from vibrations, cooling patterns, and the way these stars react when paired in binary systems. Each observation offers a hint, yet the true nature of matter inside remains an unsolved and profoundly compelling mystery. There could be objects denser than neutron stars, but not black holes. The known universe contains white dwarfs, neutron stars, and black holes, but some theories suggest the existence of objects that fall between the last two categories. These hypothetical bodies could be composed of exotic particles or unusual arrangements of matter that resist collapse even at extreme densities. They might be smaller and heavier than ordinary neutron stars, yet not compressed enough to form an event horizon. If such objects exist, they would challenge our understanding of the nuclear forces that hold matter together. Their signatures might hide in puzzling mass measurements or unusual behaviors in binary systems. Distinguishing them from known objects requires precise observations of how they bend light and how they interact with companions. These ultra-dense bodies would provide a natural laboratory for physics beyond the familiar, revealing new layers of complexity in how matter behaves under pressures far surpassing anything seen on Earth. Some neutron stars might convert entirely into exotic matter, as certain neutron stars gain mass through accretion or evolve over long timescales. Their internal pressure may reach thresholds where neutrons become unstable. In some models, this instability triggers a conversion to strange matter or quark matter, creating an object radically different from its original form. This transformation could occur suddenly or gradually, altering the star's rotation, magnetic field, and thermal properties. If the entire interior converts, the star becomes a new type of compact object with a different density and structure. Detecting such transitions would require careful monitoring of pulsars for abrupt changes in timing or unexpected shifts in emitted radiation. These conversions, if real, would reveal that nature supports forms of matter more exotic than anything observed in laboratories. The idea that a neutron star can transform from one extreme state to another adds a remarkable dimension to the study of compact objects. There could be planets orbiting neutron stars that should not exist. The discovery of planets around neutron stars came as a surprise because the violent events that create these compact remnants should destroy or eject any nearby worlds. Yet several pulsars host planets that orbit steadily, suggesting either remarkable survival or formation from debris after the original star's explosion. These planets experience intense radiation and extreme gravitational conditions, making them unlike typical worlds around ordinary stars. Some may have formed from disks of material shed during the supernova, while others may be remnants of disrupted companion stars. Their unusual origins raise questions about how planets can form or endure in hostile environments. Studying them allows researchers to explore the outer limits of planetary physics and examine worlds shaped by conditions far removed from those that influenced the solar system.
These strange planetary systems highlight the resilience and diversity of planetary formation across the cosmos. Neutron star collisions might produce unknown particles. When two neutron stars spiral together and merge, they create some of the most extreme conditions in the universe. Temperatures soar and densities climb, producing an environment where nuclear reactions and particle interactions reach energies far beyond those achievable in particle accelerators. Such collisions might generate particles that do not appear in ordinary reactions, revealing aspects of physics that remain hidden in normal cosmic conditions. These events also produce gravitational waves and bursts of radiation that can carry subtle information about the particles involved. If unknown particles are created, they might affect the distribution of energy or alter the signatures observed by telescopes. Each merger offers a rare opportunity to study matter at its most extreme, providing clues about the behavior of fundamental particles under conditions that existed only briefly in the early universe. Some neutron stars spin in ways that defy current physics. Neutron stars are known for their rapid rotation, yet some exhibit spin rates or timing behavior that challenge theoretical expectations. Certain pulsars maintain astonishingly stable periods, while others glitch suddenly, changing rotation speed in unpredictable jumps. A few spin so fast that their survival seems to defy limits imposed by structural integrity. These behaviors may involve complex interactions among the crust, superfluid interior, and magnetic fields. They might also hint at processes not yet understood, such as interactions with exotic matter or instabilities rooted in quantum phenomena. Observing these spin patterns helps researchers test models of how compact objects evolve and how their internal layers interact. The diversity of rotational behaviors suggests that neutron stars may host intricate mechanisms that push the boundaries of known physics. There could be pulses of neutron star activity we have never detected. Neutron stars emit radiation across a wide range of wavelengths, much of it highly directional. If their beams do not sweep across Earth, we never observe their signals. Many neutron stars may therefore remain unknown, hidden simply because their emission does not intersect our line of sight. In addition to regular pulses, neutron stars can produce bursts, flares, or subtle vibrations that may be too faint or too brief for current instruments to capture. Some phenomena may require new detectors or more sensitive surveys to uncover. There might be entire classes of neutron star emissions that lie just outside the capabilities of existing technology. Detecting these would expand our understanding of how neutron stars transfer energy, how their magnetic fields evolve, and how their interiors respond to stress. The unseen behaviors of these compact objects likely form a rich and unexplored domain of astrophysics. Neutron stars might hold clues about the universe's earliest moments. Because neutron stars contain matter compressed to densities similar to those present shortly after the beginning of the universe, studying them offers insights into physical conditions that no laboratory can replicate. Their cores may preserve information about interactions that shaped the early cosmos, including transitions between different states of matter. The behavior of their crusts, magnetic fields, and oscillations reflects fundamental forces that also influenced early cosmic evolution. Observations of neutron stars in binary mergers provide data about how matter behaves at extreme temperatures and densities, echoing conditions from the first fractions of a second of cosmic history. By decoding the signals from these events, scientists hope to learn about forces and particles that operated in the earliest moments. Neutron stars serve as natural time capsules, holding information from epochs otherwise inaccessible. Some neutron stars might be slowly transforming into black holes. As neutron stars age or accumulate matter from companions, they may approach the threshold at which gravity overcomes all internal pressure. When this limit is crossed, the star can collapse into a black hole. This transformation may not occur abruptly. Some models suggest a gradual sequence of internal changes as the star becomes increasingly compact, with phases marked by shifts in rotation, magnetic fields, or emission properties. Observing these signatures might allow astronomers to witness the stages leading to collapse. Such transitions would reveal the fine boundary between the stability of neutron matter and the gravitational pull that forms a black hole. Identifying stars on the brink of this transformation would provide valuable information about the fundamental limits of matter and the complex pathways that lead to the creation of black holes. Neutron star crusts could contain the strongest material in the universe. The outer layers of a neutron star form a crystalline lattice of nuclei packed together under extreme pressure. This material must support enormous magnetic fields and withstand immense stresses caused by rotation and internal motion. Calculations suggest that the crust structure may be hundreds of times stronger than any known substance on Earth. It could deform without breaking, endure intense strain, and store vast amounts of elastic energy. When this crust finally gives way, it may produce sudden changes in rotation or bursts of radiation. Understanding the properties of this remarkable material helps explain how neutron stars behave under stress and why they sometimes experience abrupt shifts. Its strength reflects the unique conditions of these compact objects, where extreme density and pressure create forms of matter that simply cannot exist anywhere else. We still do not know what most comets originate from. Comets carry some of the most ancient material in the solar system, yet their true origins remain elusive. While many are believed to come from a distant reservoir known as the outer cloud, we have never observed this region directly. It lies so far from the Sun that any objects within it reflect almost no light, making them effectively invisible to telescopes. The few comets we see are those that have been nudged inward by gravitational disturbances. But these represent only a tiny sample of what likely exists. Their compositions vary widely, hinting at different birthplaces or histories. Some contain ingredients associated with deep cold environments, while others show signs of processing in warmer regions. This diversity suggests that comets may form in multiple zones or migrate long distances before settling into the far reaches of the solar system. Until we develop ways to detect objects across those extraordinary distances, most of their place of origin will remain a hidden chapter of our solar system story. There could be entire clouds of objects beyond the reach of our telescopes. Astronomers suspect that the outskirts of planetary systems may hold vast collections of icy bodies, far larger in number than the comets and asteroids we observe near the Sun. These distant clouds could contain trillions of small objects drifting silently through space. Because they reflect so little light and lie at such great distances, they evade even the most powerful telescopes. Their existence is inferred from the behavior of long-period comets and from models of how planetary systems form. These unseen populations may include bodies with diverse compositions, shapes, and histories, each shaped by conditions in the early solar nebula. They could also influence the motion of nearby stars, or record subtle gravitational interactions from ancient encounters. Detecting them will require future missions that can sense faint thermal signatures or gravitational effects across enormous distances. Until then,
the outermost regions of planetary systems will remain among the least explored realms in astronomy. The space between stars may hold more than dust and gas. Interstellar space is often described as a thin mixture of dust, gas, and radiation. Yet, growing evidence suggests that it may contain far more complexity. Observations of absorption lines and faint emissions reveal unexpected molecules, unusual temperature gradients, and hints of structures that do not fit simple models. Some regions appear to host dense clumps of material that drift independently, while others contain magnetic patterns that extend for great distances. There may also be charged particles and tiny grains with properties distinct from those found in the solar system. These components influence how light travels through space, how stars gather material, and how shock waves from supernovae propagate. The interstellar medium is dynamic, shaped by stellar winds, radiation, and passing clouds. Understanding it requires combining chemistry, plasma physics, and studies of cosmic dust. Far from being empty or simple, the space between stars may be a vibrant and evolving environment. There could be invisible structures moving through interstellar space. As astronomers map the galaxy, they find variations in starlight that hint at objects or patterns passing between us and distant stars. These features do not match the behavior of known clouds or dust. Some appear transient, shifting on timescales too short for ordinary interstellar material. Others produce effects that suggest large but diffused structures with properties unlike typical gas or dust formations. These invisible shapes might be composed of extremely fine particles, magnetic filaments, or low-density material that interacts with light in unusual ways. They could fall naturally through turbulence or arise from processes not yet understood. Detecting them requires repeated observations of the same stars and careful analysis of subtle changes. If such structures are common, they may influence how matter cycles through the galaxy, shaping star formation and the distribution of interstellar material. Their elusive nature highlights how much remains undiscovered in the vast spaces between stars. Some rogue objects traveling through space defy classification. Occasionally, astronomers detect objects moving on trajectories that do not match typical comets, asteroids, or planets. These rogues drift freely through space, unbound to any star. Some may be fragments from disrupted planetary systems, while others might have formed independently in the cold depths between stars. Their properties vary widely. A few show comet-like activity when approaching a star, while others behave more like dense, rocky bodies. Some move at speeds that suggest distant or tumultuous origins. Because they do not remain in the solar system for long, studying them requires rapid observation and careful analysis. These visitors offer insights into the diversity of material in the galaxy and the processes that eject objects from planetary systems. Their unusual features challenge existing categories and reveal that the galaxy may hold many forms of wandering bodies we have only begun to identify. Interstellar space may contain reservoirs of frozen, ancient material. Cold regions far from stars allow molecules and dust grains to survive unchanged for immense periods. These reservoirs could hold frozen gases, complex organic compounds, and minerals older than many stars in the galaxy. When such material is disturbed by shock waves or passing objects, fragments may drift into denser regions, influencing star and planet formation. Some of the frozen material may carry signatures of chemical processes that occurred in the earliest phases of the galaxy. These reservoirs also affect the temperature and ionization of interstellar clouds, shaping the cycle of matter between stars. Detecting them is difficult because they emit little radiation. Yet faint signals in the infrared and radio bands hint at their presence. These silent storehouses of ancient material serve as archives of cosmic history, preserving clues about conditions that shaped the earliest environments in the galaxy. There might be complex magnetic fields spanning vast distances. The galaxy is threaded with magnetic fields that twist, bend, and interact with charged particles. These fields are difficult to map because they do not emit light directly. Instead, they reveal themselves through the behavior of cosmic rays, polarized starlight, and the motion of gas clouds. Some regions show remarkably coherent structures extending through interstellar space, suggesting large-scale organization. Others display tangled patterns, shaped by turbulence or shock waves from exploding stars. These magnetic fields influence star formation, guide charged particles, and help regulate the temperature of interstellar gas. They may also shape the boundaries between different regions of the galaxy, creating large but invisible frameworks that affect how matter moves. Understanding these magnetic structures is essential for modeling the behavior of the interstellar medium. Yet, many details remain unknown. Their complexity points to processes that span enormous distances and long periods of cosmic time. There could be waves through space we have not yet recognized. Beyond gravitational waves, which ripple through space-time itself, there may be other forms of waves moving through the galaxy. These could arise from oscillations in magnetic fields, fluctuations in charged particle densities, or variations in interstellar pressure. Some may travel slowly through diffuse gas, while others might move rapidly across regions filled with plasma. Because they do not emit strong light, they are difficult to detect with traditional instruments. Their presence could influence the formation of stars, the behavior of cosmic rays, or the distribution of material across the galaxy. Detecting these waves would require sensitive measurements of radio emissions, polarization patterns, or tiny changes in the motion of interstellar gas. Discovering such hidden waves would reveal new channels through which energy flows across cosmic environments, adding depth to our understanding of galactic dynamics. Exotic molecules may form in interstellar regions where chemistry should fail. Some areas of interstellar space are so cold and diffuse that chemical reactions should be extremely slow. Yet, observations reveal molecules that seem too complex to form under such barren conditions. These exotic compounds range from simple organics to surprisingly intricate structures. They may arise from reactions on the surfaces of dust grains triggered by faint starlight or cosmic rays. Alternatively, they might form within transient pockets of denser material that collapse and disperse quickly. The presence of these molecules challenges traditional ideas about where chemistry can occur. Their distribution influences the composition of forming stars and planets, seeding young systems with raw material that may play roles in later chemical evolution. Understanding how these unexpected molecules form requires a combination of laboratory experiments, modeling, and careful astronomical observation. Their existence highlights the creativity of nature in environments once thought chemically inactive. There might be unseen objects passing through our solar system. The solar system is vast, and many regions remain poorly explored. Objects with extremely dark surfaces or unusual compositions could drift through its outer reaches without reflecting enough light to be detected. Some may follow long, looping orbits that keep them far from the sun for most of their journey. Others might pass through only once, moving quickly and silently before returning to interstellar space. Their gravitational influence on known planets or comets might be too subtle to measure. Detecting such unseen bodies would require wide-field surveys capable of spotting faint movement against the background of stars. Future missions that map the sky continuously may finally reveal these hidden travelers. Their discovery would expand our understanding of the solar system's population and shed light on the variety of objects that wander through our celestial neighborhood. The nature of quantum vacuum energy remains a deep mystery. Empty space is not truly empty. According to quantum physics, even the quietest vacuum contains a restless sea of energy that cannot be removed. This energy influences how particles behave and how fields interact. Yet its true origin remains unclear. Calculations of vacuum energy often produce values far larger than anything observed in the real universe, suggesting that something in our understanding is incomplete. This energy might interact with space in ways that affect cosmic expansion, hinting at a possible connection to dark energy. It could also shape how fields fluctuate across vast distances. Because vacuum energy cannot be switched off or isolated, it can only be inferred indirectly through subtle measurements of particle behavior or delicate shifts in atomic states. Every attempt to explain it opens new questions, suggesting that vacuum energy may hold clues to deeper layers of reality that lie beyond current theories. Particles might pop in and out of reality from hidden realms. Quantum theory allows particles to appear briefly, interact, and vanish again, borrowing energy for a fleeting moment before conserving the total balance. These ephemeral phenomena are usually described as fluctuations. Yet, some researchers explore the idea that they may be linked to realms outside ordinary space. In these views, particles could momentarily dip into hidden layers of the universe before returning, creating short-lived signatures in measurable quantities. If such realms exist, they could host structures or fields that influence our world only through these brief interactions. Detecting these events directly is nearly impossible because they occur on unimaginably small scales and over extremely short intervals. Instead, scientists search for tiny deviations in particle collisions or unexpected patterns in the behavior of quantum fields. These fleeting appearances hint that the universe may include unseen dimensions that leave only the faintest traces. Quantum processes could influence the entire cosmos. Although quantum physics typically governs the world of the very small, some processes may have effects that ripple through the universe on enormous scales. Fluctuations in quantum fields during the earliest phases of cosmic history might have seeded the large-scale structure of galaxies. Tiny variations could have grown into the clusters and voids visible today. Quantum tunneling might also play roles in processes that affect the lifetime or evolution of the cosmos. Even the stability of space itself could depend on quantum interactions occurring throughout the vacuum. These possibilities suggest that the behavior of particles and fields on minute scales can shape the universe's fate. Understanding these influences requires bridging the gap between quantum theory and cosmology, two domains that operate under vastly different conditions. Their intersection remains one of the richest and most mysterious areas of modern physics. We do not know whether reality is continuous or pixelated. Mathematics often describes space and time as smooth and continuous, yet some theories propose that, at the smallest scales, they might be composed of discrete units. These tiny building blocks could determine the limits of how finely space and time can be divided. If reality is pixelated, then notions such as position, motion, and energy may behave differently near these fundamental scales. Experiments that probe extremely short distances or high energies are necessary to test this idea. Yet achieving such conditions is far beyond current technology. Indirect hints may come from the behavior of gravitational waves or from subtle anomalies in the motion of particles. Determining whether the universe is continuous or discrete would reshape our understanding of geometry, physics, and the nature of space-time. It remains one of the deepest, unanswered questions in theoretical science. The universe might be haunted by virtual particles we cannot observe. Virtual particles constantly influence measurable properties,
even though they do not appear in ways detectable as ordinary matter. They modify forces, shift energy levels, and alter how particles interact. These unseen contributors arise naturally from quantum fields that fill space, flickering into relevance only during specific processes. Though they vanish almost immediately, their effects accumulate across countless interactions, subtly shaping everything from atomic transitions to the behavior of electromagnetic fields. Virtual particles may also play roles in more mysterious phenomena, such as the vacuum energy problem or the behavior of space under extreme conditions. Their existence reveals that much of reality operates through hidden processes that can be inferred only through their influence on observable quantities. Understanding them forces physicists to accept that unseen layers of activity underpin the physical world. Quantum fields could be more fundamental than space itself. Some interpretations of physics treat quantum fields as the primary ingredients of reality, with particles emerging as excitations of these fields. In this view, even space may not be a fixed stage, but a phenomenon that arises from deeper interactions among fields. The geometry of the universe, the strength of forces, and the behavior of matter could all be consequences of patterns embedded within these fields. If this perspective is correct, then space might not exist independently, but instead emerge from relationships among more basic components. Evidence for this idea appears in attempts to unify gravity with quantum theory. Some approaches suggest that space-time curvature reflects how information or entanglement is distributed within quantum fields. Uncovering the precise structure of this deeper layer remains an enormous challenge. Yet its implications would transform our understanding of the universe. Quantum uncertainty might shape the large-scale structure of the universe. Quantum uncertainty dictates that particles cannot have perfectly defined positions or energies. During the universe's earliest moments, this uncertainty created tiny irregularities in the distribution of matter and energy. Over cosmic time, gravity amplified these irregularities, causing some regions to grow into galaxies, while others became vast voids. Thus, the overall structure of the universe may owe its shape to random fluctuations at quantum scales. Even now, quantum uncertainty may guide processes such as the behavior of black holes, or the properties of dark energy. The connection between microscopic indeterminacy and macroscopic structure illustrates the profound reach of quantum principles. Understanding this link requires studying both ancient cosmic light and simulations that model how small variations grow into immense formations. The idea that randomness on the smallest scales shaped the architecture of the cosmos remains one of the most remarkable insights of modern science. There could be unknown quantum states filling the entire cosmos. Quantum fields can occupy many possible states, some familiar and others never observed directly. The vacuum itself may represent only one configuration within a much larger landscape of possibilities. If the universe contains regions where fields settle into different states, these variations could influence the strength of forces, the masses of particles, or the behavior of space. Such states might be stable, longevid, or ephemeral, leaving faint imprints on cosmic history.
They could shape how matter formed, how galaxies evolved, or how the universe expands. Detecting them is extremely difficult because their signatures may be subtle or hidden within the background of known phenomena. Nevertheless, their existence is supported by some theoretical models that seek to explain a diversity of physical constants. Unknown quantum states may operate quietly throughout the cosmos, influencing reality in ways we have not yet recognized. Quantum effects might affect gravity in extreme situations. General relativity describes gravity as the curvature of spacetime. Yet, at very small scales or under extreme conditions, quantum processes may alter this behavior. Near the centers of black holes, or in the earliest moments of the universe, the smooth geometry predicted by relativity may break down. Quantum fluctuations could produce irregularities, distortions, or limits on how sharply space can curve. These effects might prevent singularities or change the fate of collapsing matter. They could also influence how gravitational waves propagate or how black holes evaporate. Studying such situations requires combining quantum theory with gravity, a task that continues to challenge physicists. Although indirect hints appear in theoretical models, direct evidence remains elusive. Understanding how quantum processes modify gravity would open a window into the deepest workings of the universe. Reality might depend on information in ways we do not yet understand. Emerging ideas in physics suggest that information could play a central role in shaping reality. In this view, the properties of particles, the behavior of forces, and even the structure of space may reflect patterns of stored or distributed information. Some theories propose that the universe's geometry arises from networks of quantum entanglement. Others argue that physical laws follow from principles of information preservation. These concepts connect areas once thought unrelated, linking thermodynamics, quantum mechanics, and gravity. Evidence appears in the behavior of black holes, which seem to store vast amounts of information in unexpected ways. If reality truly operates according to informational principles, then matter and space may be surface expressions of deeper laws. Grasping those laws would transform physics, opening an entirely new way to investigate the universe. Fast radio bursts could arise from processes we've never yet conceived. Fast radio bursts are fleeting pulses of radio energy that last only fractions of a second. Yet within that brief moment, they unleash more power than many stars emit over long periods. Their origins remain profoundly mysterious. Some repeat, others appear only once, and many arrive from regions of the sky with no clear source nearby. Proposed explanations range from magnetars to collisions to unusual plasma effects, but the wide variety of signals suggests that at least some may come from mechanisms not yet imagined. Their extraordinary brightness points to extremely compact sources, while their timing and structure sometimes display irregularities that existing models struggle to explain. Because they travel across vast distances, they carry information about the medium between galaxies. Yet, that information is difficult to interpret. Some bursts arrive with structures too complex for current explanations. As new instruments capture more events, the puzzle deepens, pointing to physical processes that may stretch or reshape our understanding of cosmic energy. Some cosmic signals could originate from unknown natural engines across the sky. Telescopes detect signals that do not fit cleanly into known categories. Some are too sustained to be bursts, yet too irregular to be typical emissions from stars or galaxies. These signals may arise from natural engines that have not yet been identified. Extreme magnetic fields, turbulent environments, and interactions between exotic particles could generate emissions unlike any familiar process. Some signals vary in brightness or frequency in ways that do not correspond to standard astrophysical cycles. Others show sudden changes that hint at hidden mechanisms operating deep within cosmic structures. The galaxy may host dynamic engines that activate under conditions we have not yet observed directly. Understanding these signals requires gathering more data, refining analysis methods, and keeping an open mind about processes that may exist outside established frameworks. Each unexplained pattern offers a clue to unseen behavior in the universe. There might be flashes of energy we have not learned how to detect. The universe produces many kinds of emissions, yet our instruments detect only a narrow range of possible signals. Some energy bursts may be too faint, too brief, or emitted at wavelengths beyond the reach of existing technology. These flashes could occur during rare cosmic events, or in environments where matter and radiation behave in unfamiliar ways. They might carry information about extreme physics, exotic particles, or transitions that occur deep within compact objects. If we lack detectors tuned to the right frequencies, these events pass unnoticed. As new observatories expand sensitivity across previously unexplored ranges, astronomers may uncover flashes that reveal unknown processes. Hidden bursts could help explain unexplained cosmic variations or missing energy signatures. The possibility that entire classes of events remain invisible underscores how much of the universe operates beyond our current perception. Some cosmic rays arrive with energies we cannot explain. Cosmic rays are high-energy particles that strike Earth from space. Most originate from known processes such as supernova remnants or active galaxies. Yet a small fraction arrive with energies far too high for these sources. These extreme particles challenge theories of acceleration because no known environment appears capable of imparting such incredible energy. They may arise from rare cosmic phenomena, interactions involving exotic particles, or processes that occur near the boundaries of extreme astrophysics. Their paths through space bend under magnetic fields, making it difficult to trace them back to their origins. This obscures the nature of the mechanisms that launched them. Studying these rare particles may reveal new physics operating at energies far beyond those produced by any human-made accelerator. They represent one of the most direct windows into high-energy processes, but the universe keeps largely hidden. They could be signals hidden in the noise of the universe. Astronomical data contains vast amounts of background noise, created by natural processes such as dust emission, cosmic microwave radiation, and faint starlight. Within this noise, subtle signals may be buried. These signals could originate from phenomena too weak or too rare to stand out clearly. Some might be patterns that repeat only over long timescales, while others might appear as barely detectable variations. New analysis techniques using advanced modeling and machine learning may help uncover these hidden signs. If such signals exist, they could reveal unknown objects, transitions, or interactions. They might also provide clues about processes that shaped the early universe or influence cosmic structure today. The possibility that important information lies concealed within noise adds depth to the challenge of interpreting astronomical observations. Some gamma-ray bursts might reveal unknown cataclysms. Gamma-ray bursts are among the brightest explosions known, often linked to collapsing massive stars or merging neutron stars. Yet a subset of these bursts do not match established categories. Their durations, intensities, or afterglows differ from expectations. Some appear too short for stellar collapse, yet too long for known merger processes. Others lack expected signatures in lower energy wavelengths. These anomalies suggest that additional kinds of cosmic cataclysms may exist, involving mechanisms not yet understood. They might arise from exotic stars, unusual magnetic events, or interactions involving compact objects in unexpected configurations. Because gamma rays carry enormous energy, even small differences in their emission mechanisms reveal profound variations in underlying physics. These unusual bursts may hold clues to rare or extreme events that occur infrequently, but shape the evolution of energetic regions of the universe. There could be rhythms in cosmic activity we have not yet noticed. Across the cosmos, many processes follow cycles, from stellar pulsations to galactic interactions. Yet some rhythms may be so slow, faint, or irregular that they escape detection. These long-term or subtle cycles might govern changes in magnetic fields, variations in emission from compact objects, or shifts in large-scale cosmic structures. They could also operate on timescales far longer than human history, making them difficult to observe without continuous, long-term monitoring. Detecting such rhythms might require observing many objects simultaneously, or analyzing historical data for patterns. If these cycles exist, they could reveal coordinated behavior across distant regions, or provide insights into processes that evolve gradually. Cosmic rhythms may be hidden background patterns shaping the dynamic behavior of the universe. Some astronomical events might repeat on timescales longer than human history. Certain cosmic phenomena occur so infrequently that no human has witnessed more than a single instance. Ancient star eruptions, rare collisions, and slow changes in stellar interiors may repeat only after long intervals. Some stars may undergo dramatic transformations on cycles lasting thousands or millions of years. These events could influence surrounding environments, trigger waves of star formation, or reshape cosmic structures. Because these timescales extend far beyond recorded observations, it is difficult to confirm whether certain phenomena repeat or are singular occurrences. As data accumulates over generations, astronomers may begin to detect signs of cyclic behavior. Understanding these long-term processes will reveal how objects evolve over deep time and how seemingly stable systems undergo changes on scales that transcend human experience. There might be transient phenomena too brief for current instruments. Many astronomical events occur in the blink of an eye, releasing energy in extremely short bursts. If these flashes last only microseconds or nanoseconds, current detectors may not be fast enough to register them. Such transient events might arise from rapid magnetic reconnection, particle interactions in extreme environments, or collisions involving small bodies. Detecting them requires instruments with very high temporal resolution and continuous monitoring. Because they vanish almost instantly, their properties may differ significantly from longer events. These fleeting phenomena may play important roles in transferring energy, shaping radiation fields, or influencing cosmic environments in ways not yet understood. Their discovery would expand the known spectrum of celestial behavior. The universe could emit glows from processes outside known physics. Some aspects of cosmic radiation may come from mechanisms that do not fit into current models of particle physics or astrophysics. These glows could be diffuse emissions spanning large regions or faint backgrounds produced by unfamiliar interactions. They might emerge from exotic particles, transitions in quantum fields, or processes linked to dark matter. Their spectra would differ from ordinary starlight or thermal emission, making them difficult to identify within existing datasets. Detecting such glows requires careful separation from known backgrounds, and creative approaches to interpreting faint signals. If confirmed, they could reveal entirely new categories of energy release that operate quietly across the universe. Life might arise in conditions completely foreign to us. On Earth, life depends on liquid water, moderate temperatures, and a familiar set of chemical reactions. Yet, the universe contains environments far outside these boundaries. There are worlds with crushing pressures, extreme cold, violent radiation, or atmospheres filled with chemicals toxic to known organisms. In such places, life could emerge through pathways unlike anything in terrestrial biology. Reactions that fail in Earth-like settings might flourish under different conditions. Energy could come from sources unrelated to sunlight, such as deep chemical gradients, magnetic interactions, or slow geological processes. Structures that resemble cells might form from exotic materials that behave predictably only under extreme conditions. These possibilities force us to consider that life is not a narrow phenomenon, but a process shaped by its environment. If such unfamiliar life exists, detecting it will require methods that do not rely on assumptions drawn from a single example. It expands the search for living systems into realms we once dismissed as barren. The building blocks of life could form in places we would not expect. Complex organic molecules appear in interstellar clouds, on icy comets, and within the atmospheres of giant planets. These environments seem inhospitable, yet they host chemical reactions that produce ingredients essential for life. Radiation, cold temperatures, and dust grains provide surfaces and energy sources that drive unusual chemistry. Some clouds contain long carbon chains, while cometary ice traps molecules that may have formed in ancient cosmic regions. Even gas giant atmospheres show hints of compounds that could serve as precursors to biological structures. These materials may later seed young planets or accumulate on surfaces where conditions eventually allow life to develop. The universe seems to be a factory for organic components, producing them across environments with no resemblance to Earth. Understanding these processes helps explain how life's essential ingredients may arise long before planets are ready to host living systems. The universe might host life based on chemistry we do not yet understand. Life on Earth uses a narrow set of molecules built around carbon, hydrogen, oxygen, and nitrogen. Alternative forms could rely on entirely different chemistries. Some environments may support molecules that remain stable only under extreme pressures or temperatures. Solvents other than water could permit reactions that assemble structures unfamiliar to terrestrial biology. Elements such as silicon, sulfur, or phosphorus might form the basis for self-sustaining systems that process energy and replicate. These hypothetical life forms would not resemble microbes, plants, or animals. Their metabolic pathways, structural components, and modes of growth could be unrecognizable. Detecting such life requires moving beyond Earth-centered assumptions and considering signatures based on unexpected patterns in heat, chemistry, or energy flow. The variety of possible chemistries suggests that life may exist in forms that challenge every definition currently used in science. Life elsewhere could evolve in environments we cannot imagine. Planets and moons throughout the universe experience conditions far different from those found on Earth. Some are locked in perpetual darkness, while others endure long cycles of intense heat and extreme cold. Certain worlds have thick atmospheres, boiling oceans, or surfaces coated in exotic materials. Life, if present, would adapt to these conditions, using strategies shaped by unique evolutionary pressures. Organisms might rely on energy from tidal forces, deep interior heat, or chemical gradients created by unusual minerals. They might develop structures suited for dense atmospheres or low gravity. Evolution could produce behaviors and sensory systems unlike anything on Earth. Considering such diversity widens the scope of what living worlds may look like and prepares us to recognize life even when it emerges under extraordinary conditions. They could be biological processes happening in extreme cosmic settings beyond planets. Biological activity might occur in environments that seem completely unsuitable. Certain asteroids contain materials that could support simple chemical cycles. Subsurface oceans on icy moons may host thermal vents where living systems take root. Free-floating objects in interstellar space could contain internal heat sources, maintaining pockets of liquid beneath icy crusts. Even dust-laden clouds may shelter molecules capable of developing into primitive systems. These possibilities show that biology might not require stable surfaces or traditional planetary conditions. Instead, it could arise wherever chemical complexity and energy sources align. Studying these environments expands the search for life into regions previously considered irrelevant for biology. Life might leave traces we do not yet know how to recognize. Most searches for life rely on signatures familiar from Earth, such as oxygen, methane, or chlorophyll-related pigments. Yet even life may produce byproducts unlike anything found in terrestrial ecosystems. It might release gases that appear inert or unimportant, create patterns in heat emissions, or alter minerals in subtle ways. Such signatures may blend into background noise or be dismissed as ordinary geological effects. Recognizing them requires new frameworks that consider a wide range of possible biosignatures. These may include unusual chemical ratios, unexpected atmospheric cycles, or repeating patterns not caused by natural processes. Understanding how life alters its environment in unfamiliar ways will be crucial for identifying living systems across the universe. The universe could host civilizations with unknown technological signatures. If intelligent life exists elsewhere, its technologies may not resemble radio transmissions, satellites, or optical signals. Advanced civilizations might use energy sources invisible to current detectors, or construct structures that blend into natural backgrounds. They could manipulate magnetic fields, reshape planetary atmospheres, or leave imprints in radiation fields that appear natural to us. Their communication methods may not rely on electromagnetic waves at all. Technologies based on principles we have not yet discovered might operate across scales or frequencies outside human detection capabilities. Searching for such civilizations requires expanding our expectations beyond familiar ideas. Unknown signatures may be hiding in existing data, waiting for new perspectives to reveal them. Some worlds might hold ecosystems entirely unrelated to our own. On distant planets, ecosystems could develop with species that do not share Earth's genetic or biochemical foundations. Their interactions might follow rules shaped by alien environments, such as constant storms, dim starlight, or abundant minerals unknown on Earth. Food webs might rely on chemical energy rather than sunlight. Organisms could use materials that are unstable in terrestrial conditions, forming tissues and structures that behave unpredictably when compared to Earth-based life. Such ecosystems would rewrite our assumptions about how living communities form, interact, and evolve. Their discovery would offer insight into the adaptability of life and the range of ecological possibilities available across the universe. life could exist in forms that do not rely on planets. Floating habitats in interstellar space, suspended environments within giant planet atmospheres, or stable structures around stars could all support life.
Some systems may provide heat and chemical gradients without needing a solid surface. Life might arise in clouds of organic particles, or within long-lived vortices in thick atmospheres. It could occupy magnetic structures, or exist within networks of complex molecules drifting through space. These possibilities challenge the idea that planets are the primary homes for biology. Instead, life may thrive wherever conditions allow complexity and energy flow, even if no planet is present. The universe may reveal forms of life that change our idea of what life is. As we explore more worlds and detect more signals, we may encounter systems that blur the line between life and non-life. These forms could challenge the definitions used in biology, forcing scientists to rethink concepts such as metabolism, growth, and reproduction. Some systems might rely on processes unfamiliar to Earth's chemistry, while others might operate at scales too small or too large for traditional categories. Discovering such life would expand the boundaries of science, offering new perspectives on how matter organizes itself into living patterns. The universe may hold examples that redefine the very meaning of being alive. We might one day watch the birth of a new universe. Though our universe feels complete, some theories suggest that new universes may still form, sprouting from quantum fluctuations or budding off from black holes. If so, the birth of a new universe may one day be something we can glimpse, though never enter. It would appear as a bubble of spacetime forming and expanding, disconnected from our own. To us, it might be only a flash, a brief distortion gone before we could understand. But within that bubble, an entire cosmos could unfold with its own stars, its own galaxies, and perhaps its own forms of life. The idea is dizzying that new realities may be blooming even now, unseen beyond our reach. If true, then creation never truly ends. It is always beginning again. Universes growing out of universes, a cosmic garden with no final boundary, no final horizon. The cosmos is still ringing from its earliest moments. When the universe was born, it was filled with ripples of energy, vibrations in spacetime itself. These primordial waves still echo faintly across the cosmos, etched into the background radiation, and perhaps still rippling invisibly through space. Astronomers call this the cosmic ringing, the aftershocks of creation, frozen into the fabric of reality. With sensitive instruments, we can trace these patterns, learning about the very first moments of the universe, when physics itself was still settling into form. To imagine it is to hear a faint, endless hum. The universe singing softly from its own beginning. Long after the first light faded, these echoes remain, telling a story billions of years old. They are reminders that the universe has memory, that every vibration, every ripple leaves a trace. Creation itself still resonates quietly in the silence of the night sky. The oldest light we can see comes from 380,000 years after the Big Bang. Before that moment, the universe was a glowing fog, so hot and dense that light couldn't travel far without scattering. But as it expanded and cooled, it reached a turning point. Atoms formed, the fog cleared, and light was suddenly free to move. That ancient light is the cosmic microwave background, and we can still detect it today. It's the oldest direct signal in the universe,
not from stars or galaxies, but from the universe itself when it was just beginning to become transparent. The photons we observe now have been traveling for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. This light is faint but ever present, a quiet glow that carries the memory of the universe's earliest clarity. Some stars have planets made almost entirely of diamond. In certain solar systems, the chemistry is very different from ours. If a planet forms with more carbon than oxygen, and the pressures are high enough, something remarkable can happen. A diamond planet. Astronomers have discovered at least one such candidate, a dense world orbiting a pulsar, likely the remnant of a dead star. Based on its mass, density, and composition, the entire planet may be a crystalline form of carbon, essentially a giant diamond. It's far too hot to sparkle, and it wouldn't look like a jewel up close. But deep beneath the surface, immense carbon lattices could stretch for thousands of kilometers. These strange worlds aren't common, but they remind us how diverse the universe can be. A planet made of rock, a planet made of gas, and sometimes a planet made of crystal. The universe may have no edge, just endless curvature. It's tempting to imagine the universe as something with an edge, a border we could reach if we traveled far enough. But space doesn't seem to work that way. According to general relativity, the shape of space is determined by its contents, and current evidence suggests that the universe is either infinite or so vast and curved that it loops back on itself. If that's true, you could, in theory, travel in a straight line forever and eventually return to where you started, not by hitting a wall, but by wrapping around curved space. This is similar to how traveling around Earth doesn't reveal an edge, just a globe. The universe may work in the same way, on a much grander scale, not infinite in space, but infinite in journey. The universe is vast, and you are a way for it to know itself. For all its galaxies, stars, and mysteries, the universe would be silent without eyes to see and minds to wonder. Through us, through life, thought, and curiosity, the cosmos reflects upon itself. Every question asked, every star admired, is the universe becoming aware of its own grandeur. You are made of its atoms, shaped by its stars, carried by its history. In you, the vast reaches of time and space have found a voice, a perspective, a fleeting spark of consciousness. To rest beneath the night sky is to realize that you and the stars are not separate, but parts of the same whole. The universe is vast beyond imagining. Yet in you, it has found a way to wonder at its own existence. That is perhaps the greatest wonder of all. Some stars are stripped down to bare cores of pure carbon. Stars come in many forms, and some live such unusual lives that they end as something rare and strange. These are white dwarfs made almost entirely of carbon, stripped of their outer layers until only their dense crystalline cores remain. In essence, they are stars that have become giant cosmic diamonds, glowing faintly as they cool. Over billions of years, they will crystallize fully, their interiors hardening into lattices of pure carbon. Though they no longer shine as brightly as their former selves, they are treasures of the cosmos, brilliant in concept, if not in light. To imagine them scattered across the galaxy is to picture hidden jewels drifting silently among the stars. Each one is the remnant of a lifelong past, a shining ember turned into a gem, proof that even in death, stars can become beautiful in new ways. Most of the universe's history hasn't happened yet. Though the cosmos feels ancient at more than 13 billion years old, this may only be its beginning. Stars, galaxies, and even black holes will continue to exist for trillions upon trillions of years to come. In fact, the era we live in, when stars are still shining, when galaxies are bright, may be just the opening chapter of an unimaginably long story. The majority of the universe's history lies ahead in epochs we cannot truly fathom. There will be times of fading starlight, of cooling embers, of black holes slowly evaporating, and of silence stretching into infinity. To us, the present feels vast, but it is only a fleeting moment in the life of the cosmos. We live in a universe that is still young, its greatest ages yet to unfold, its longest dreams still waiting to be dreamed. Supernova remnants keep expanding for thousands of years. When a massive star explodes as a supernova, the brilliance fades within weeks or months. But the remains of the explosion, shells of gas and dust, continue expanding for thousands of years. These remnants grow into vast clouds, glowing faintly with the energy of the blast. One of the most famous is the Crab Nebula. Born from a supernova observed on Earth nearly 1,000 years ago, it is still expanding, still spreading its filaments of light across space. These remnants are not only beautiful, they are the forgers of new creation, scattering elements that will someday form stars, planets, and life. To see one is to glimpse the echo of violence, softened into delicate shapes of color and light. They are cosmic afterimages, reminders that even in endings, the universe leaves behind traces of wonder that linger for ages. The sun once had a twin, and it may still be out there. Some astronomers believe that our sun was born with a twin, a companion star formed from the same cloud of gas and dust over 4.5 billion years ago. Many stars form in pairs, and there's no reason to think our sun was an exception. If it existed, this lost sibling would have drifted away long ago, pulled apart by the slow gravitational tug of the Milky Way. It might still be out there, orbiting the galaxy on a different path, invisible to us now. Some theories even link this twin, nicknamed Nemesis, to mysterious extinction patterns on Earth, though there's no solid evidence for that. Still, the idea lingers. But our sun, steady and alone in our sky, may once have shared its birth with a silent partner, long vanished into the stars. A raindrop of neutron star would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, incredibly dense remnants left behind after supernova explosions. They're only about 20 kilometers wide, but their mass is greater than the sun's. The matter inside is so densely packed that a single teaspoon of it would weigh billions of tons. If you imagined a single raindrop of neutron star material, it would be heavier than any mountain on Earth. That kind of density defies our everyday experience. Atoms are crushed together so tightly that electrons and protons merge into neutrons, forming a kind of superfluid neutron soup. Neutron stars are extreme objects, small, dark, heavy, and spinning rapidly. Yet within their silent mass, they preserve the imprint of stellar collapse, a final condition where matter becomes almost pure gravity. Light from a single galaxy can sometimes reach us along more than one route. At times, light does not move in a straight line. In areas of space where gravity is especially intense, such as near massive galaxy clusters, space-time itself bends. That bending curves the path of light the way glass bends a beam. This effect is known as gravitational lensing. One of its strangest results is that we can occasionally observe multiple images of the same distant galaxy from different directions. These appearances may form arcs, blurred smears, or even full rings. They are not copies in space, but copies in perception, different journeys that light has taken through warped spacetime to arrive at our eyes. In a handful of rare cases, astronomers have even seen the same supernova appear to explode more than once, as its light arrived along separate gravitational paths. It is a quiet reminder that in the universe, even light can wander, take the long way around, and still make it home. The first stars may have shone 1,000,000 times brighter than the sun. The very first stars were unlike anything we see today. Born from the pure hydrogen and helium left after the Big Bang, these stars, called population the third stars, likely formed with no metals at all, making them massive, hot, and short-lived. Some may have been hundreds of times the mass of the sun. They would have burned through their fuel quickly, shining 1,000,000 times brighter than our own star, then collapsing in spectacular explosions after just a few million years. None of these stars survive today, but their brief lives changed the universe.
They created the first heavy elements, seeded galaxies with light, and set the stage for everything that followed, including us. Their light is gone now, but their fingerprints remain in the chemistry of ancient gas clouds and in the quiet structure of the early cosmos. Dark matter streams through your body as you sleep. As you lie still, dark matter flows silently around you. It's not some invisible mist. It's a form of matter that doesn't interact with light, doesn't reflect, emit, or absorb it. But it has mass, and it responds to gravity. Our galaxy is surrounded by a vast halo of dark matter, and as Earth moves through this halo, trillions of dark matter particles are thought to pass through every square smilla of your body each second. They don't collide with your atoms, they don't leave a trace, but they're there, ghost-like, ever-present, and essential. Without dark matter, galaxies wouldn't hold together, cosmic structures wouldn't form, and the universe would be very different. We still don't know what dark matter is made of, but we know this much. It's part of your world, passing through you, silently and continuously, even as you sleep. Some galaxies glow without any stars inside. In the quiet reaches of the universe, astronomers have discovered galaxies that shine but barely contain any stars. These ghostly systems are full of gas and dark matter, but show little to no evidence of star formation. Some may have lost their stars in violent gravitational encounters. Others may never have made many stars at all. A few are nearly invisible except in certain wavelengths of light, faint smudges in deep surveys of the sky. These galaxies challenge what we thought we knew about how galaxies form and evolve. If they're rich in dark matter, why haven't they built stars? If they had stars once, where did they go? These dim, quiet systems float through space like forgotten bones of cosmic history. Remind us that not every galaxy is filled with blazing light. Some simply drift unseen and unanswered. The universe has a cold spot that shouldn't exist. In the cosmic microwave background, the faint glow left over from the Big Bang, there's a patch of sky that's unusually cold. It's not just a little cooler than its surroundings. It's significantly colder and much larger than scientists expected. This cold spot spans hundreds of millions of light years, and its presence doesn't quite match the smooth randomness we'd expect from early universe physics.
Some think it may be the imprint of a vast cosmic void. Others wonder if it could hint at something even stranger, like the collision of our universe with another in the very early moments of inflation. No explanation so far fully fits. The cold spot remains one of the most quietly unsettling puzzles in cosmology. Not a screaming anomaly, but a whisper that something about our universe may not be what it seems. The moon is slowly leaving us behind. Every year, the moon drifts a tiny bit farther away from Earth, about 3.5 centimeters. That's roughly the rate at which your fingernails grow. This slow retreat has been happening since the moon formed, around 4.5 billion years ago. Back then, it was much closer, and a day on Earth was just a few hours long. The cause is tidal friction. As the moon pulls on Earth's oceans and Earth spins beneath them, a small transfer of energy gradually pushes the moon outward in its orbit. It's a quiet, relentless process, invisible on human timescales, but unmistakable over eons. In the far future, Earth and the moon may become tidally locked, always showing the same face to each other. For now, it just keeps slipping away, little by little, as we spin beneath its distant, glowing light.
Binary stars can swap their outer layers like dancers in contact. In some binary star systems, the two stars orbit so closely that their outer layers begin to touch. As they evolve, one star can swell and spill matter onto the other, creating a delicate, spiraling exchange of material. Sometimes the transfer is calm and steady. Other times it triggers bursts of light, rapid rotation, or even a complete merger. The physics is complex, but the image is oddly graceful. Two stars locked in orbit, spinning close enough to brush and blend. One star may end up stripped to a glowing core, while the other becomes swollen and enriched. Their fates are bound together. Some of the most unusual objects in the universe, like certain supernova or compact neutron star pairs, begin as these quiet, touching binaries, a reminder that in space, even stars can share, change, and sometimes embrace. The vacuum of space is not truly empty. Even in the deepest, darkest reaches of space, far from any star or galaxy, the universe is never truly empty. According to quantum physics, what we call vacuum is a sea of activity. Tiny particle-antiparticle pairs blink into existence and vanish almost immediately. These quantum fluctuations happen all the time, everywhere, creating a kind of restless background to reality itself. They can influence the motion of particles, affect the behavior of fields, and even contribute to the energy of empty space. This is part of what gives rise to dark energy, the mysterious force accelerating the expansion of the universe. So when we picture deep space as silent and still, that image is only partly true. Beneath the quiet lies a dance of probabilities, a hidden hum of creation and disappearance, always just below the surface of nothing. Time may flow at different rates in different regions of the cosmos.
We think of time as steady, a ticking rhythm that flows the same for everyone, everywhere. But in reality, time is deeply linked to gravity, motion, and the shape of space-time itself. In regions where gravity is strong, like near a black hole or a dense galaxy cluster, time slows down relative to places where gravity is weaker. This isn't just theory. It's been confirmed by experiments, satellites, and atomic clocks. But some cosmologists wonder whether time could also vary on even larger scales,
Could different parts of the universe experience time at slightly different rates due to how the universe expanded in its early moments? The idea is speculative, but it opens strange possibilities. In a cosmos governed by relativity, even time may not be absolute. It may stretch, slow, or bend, quietly shaped by the space through which it flows. The Milky Way has a hidden halo that's larger than the visible galaxy. When we look at images of the Milky Way, we see a glowing spiral, stars, dust, and gas arranged in beautiful arms. But surrounding this familiar structure is something vast and mostly invisible: the galactic halo. It's a huge sphere of diffuse gas and dark matter that extends far beyond the visible edge of the galaxy, reaching distances many times greater than the span of the disk itself. This halo contains ancient star clusters, stray stars, and vast amounts of unseen mass. It's held together by gravity, shaped by the history of collisions and merges, and plays a quiet role in the galaxy's stability. Though we can't see it directly, we infer its presence through the motion of stars and the bending of light. The Milky Way, it turns out, is just the bright center of something much larger, a glowing heart wrapped in invisible arrows. We've detected light from a galaxy just 200 million years after the Big Bang. The universe is about 13.8 billion years old, but light doesn't travel instantly.
It moves through expanding space, stretched and slowed along the way. That's why we can see galaxies not as they are, but as they were long ago. Recently, astronomers using the James Webb Space Telescope identified light from a galaxy that existed just 200 million years after the Big Bang, a blink of time on the cosmic scale. That light has been traveling toward us for more than 13.12 billion years. The galaxy itself is small, faint, and primitive, but it holds clues to how the first structures formed. Observing it is like looking through a narrow window into a world we were never meant to see. The universe in its earliest chapters, when darkness was just beginning to give way to stars. The large-scale structure of the universe looks like a neural network. When astronomers map the positions of galaxies across enormous distances, a surprising pattern emerges. Galaxies aren't scattered randomly.
Instead, they cluster together along long thread-like filaments with vast empty regions, cosmic voids in between.
This interconnected web stretches across billions of light years and is sometimes called the cosmic web. One theory is that when you zoom out far enough, this structure looks uncannily like a neural network, the kind found in the human brain. Dense nodes of galaxies are like neurons, and the filaments are like axons connecting them. Of course, the resemblance is purely structural. The universe isn't thinking, but it's still quietly beautiful to consider. The largest structure we know, and the one inside your own mind, shaped by entirely different physics, can end up looking so strangely alike. Stars can sing through the vacuum of space. There's no air in space, so we don't hear sound the way we do on Earth. But stars still make sound, deep, slow vibrations that travel through their interior gases like seismic waves through a planet.
These pressure waves make the star pulse and oscillate, and scientists can detect them by observing tiny changes in the star's brightness or surface motion. The field that studies this is called asteroseismology, literally the seismology of stars. Each star has its own internal frequencies, like a fingerprint determined by its size, structure, and age. By listening to these stellar vibrations, scientists can peer inside stars and learn what's happening beneath the surface.
It's a kind of cosmic echolocation, a way to hear the music of stars across light years, even if the song is silent to human ears. Some stars are older than the galaxies they live in. Galaxies are not built all at once. They form over time, merging with smaller systems and drawing in stars and gas from other regions. That means some stars inside a galaxy can be older than the galaxy's current structure. They may have formed in earlier smaller galaxies that later merged into a larger one.
These ancient stars often live in the outskirts or in globular clusters, tightly bound groups that orbit far from the galaxy's core. Some of them are over 13 billion years old, nearly as old as the universe itself. They carry the chemical signature of a much younger cosmos, when there were fewer heavy elements and only the simplest atoms. These stars are like fossils, quietly acquired survivors from before the galaxy fully came together. Their light is old. Their stories began before much of what we know had even formed. There are galaxies without dark matter, and we don't know why. Dark matter is thought to be the invisible glue holding galaxies together. It explains why stars in the outer regions of galaxies move faster than expected, and why galaxies cluster the way they do. But in the last few years, astronomers have found galaxies that seem to defy this rule. Galaxies that behave as if they have no dark matter at all.
Their stars move as though only the visible matter is present.
This discovery was unexpected, and it doesn't fit easily into current models. Some scientists think the dark matter was stripped away during past collisions. Others wonder if we still don't fully understand what dark matter is. By the way, these strange galaxies suggest that the universe still has secrets, and that the things we think are universal may not be so universal. After all, the sun rings like a giant, booming bell. Deep inside the sun, sound waves ripple through the plasma, bouncing from one layer to another and setting the entire star into subtle, continuous vibration. These waves aren't like the sounds we hear with our ears. They're pressure waves, low, slow, and far below human hearing. But with sensitive instruments, scientists can detect them and use them to study the sun's internal structure. This field is called helioismology.
By observing how the sun rings, scientists can map what's happening deep below the surface, its density, rotation, and even its hidden flows of hot gas. The sun, in this sense, acts like a musical instrument, vast, complex, and always playing. We just need the right tools to listen. And what we hear helps us understand not only the sun itself, but stars everywhere. Galaxies follow filaments made of something we cannot see. The universe's largest structures aren't made of stars or gas. They're shaped by something invisible, dark matter. Over billions of years, this dark matter formed enormous filaments stretching across space. And galaxies tend to form and move along these filaments like beads on a string. We can't see the filaments directly, but we can infer them by observing how galaxies cluster and how light bends as it passes through these regions. The filaments can span hundreds of millions of light years and connect vast clusters of galaxies.
In between lie great voids, nearly empty regions where very little matter exists. The dark matter filaments act like a hidden scaffolding for the visible universe, shaping how galaxies grow and where they go. And yet, we still don't know what dark matter is. The structure is there, immense, unseen, and quietly holding the universe together. Space can stretch faster than the speed of light. In normal circumstances,
Nothing can move faster than light. But space itself isn't bound by that rule. During the early moments after the Big Bang, space expanded so rapidly that regions of the universe were pulled apart faster than light could travel between them. This wasn't motion through space. It was the expansion of space itself. Even today, distant galaxies aren't racing away because they're moving quickly through space. They are receding because the space between us and them is stretching. And if they're far enough away, that stretching makes them recede faster than light, which is why we'll never see them again. It's not a violation of physics, but a quiet consequence of how space behaves on cosmic scales. The universe doesn't need to rush. It simply expands calmly and relentlessly beyond what we can follow. Our solar system moves through space like a helical spiral. It's easy to picture the planets orbiting the sun in neat, flat circles. But zoom out further and something stranger emerges. The sun itself is moving, orbiting the center of the Milky Way at nearly 1 million kilometers per hour. As it moves, the planets follow in tow, not just circling the sun, but spiraling through space behind it. The combined motion creates a helical pattern, like a corkscrew or a twisting ribbon. Everything is in motion. The planets, the sun, the stars, the galaxy itself. There is no stillness in space, only graceful, ceaseless drift. Even as we sleep, we're tracing slow spirals through a galaxy in motion, wrapped in layers of orbits within orbits. A dance so vast, we never feel it. Even nothing has a temperature. If you travel far enough from stars, planets, and galaxies into deep intergalactic space, you'll find yourself surrounded by what seems like pure emptiness. But even the vacuum has a temperature. That temperature is about 2.7 Kelvin, just a few degrees above absolute zero. It comes from the cosmic microwave background. The leftover glow from the Big Bang, now stretched and cooled by billions of years of cosmic expansion. This faint radiation fills the entire universe. No matter where you go, it's there. It's the quiet thermal signature of the early universe, still lingering, still measurable. And in the future, it will cool even further. In a few trillion years, the universe may approach absolute zero, but never quite reach it. Because even in the vastest emptiness, the echo of heat remains. Quantum fluctuations may have shaped the entire universe. At the smallest scales of reality, far smaller than atoms, the universe behaves unpredictably. Tiny, random fluctuations in energy can appear and vanish in an instant due to the uncertainty built into quantum physics. And according to many cosmologists, those brief, random blips may have been magnified during the universe's first moments through a process called inflation. As space expanded at unimaginable speed, tiny fluctuations were stretched to cosmic proportions. Those fluctuations became the seeds of structure, the places where matter would clump, where galaxies would form, where stars would eventually ignite. In other words, the grand structure of the cosmos, the galaxies, the filaments, the voids, may all trace back to fleeting, random events at the smallest possible scale. Everything we see today, born from the trembling of nothing. Dying stars can pulse like heartbeats across millions of years. Not all stars end with a bang. Some fade more slowly, and during their final stages, they can pulsate, swelling and shrinking in rhythmic cycles. These stars, called variable stars, change in brightness over time. In some cases, the changes are steady and regular, repeating like a slow heartbeat. The pulses are caused by changes in the star's outer layers, gases expanding and cooling, then collapsing and heating up again. Some stars pulse every few days, others take months or even years to complete a cycle. These rhythmic stars have been used to measure distances in space since their pulsation patterns relate to their true brightness. They also serve as quiet reminders that, even in death, stars can keep time. Not with a clock, but with a long, slow breath across cosmic ages. Earth is inside a giant bubble of hot gas.
If you could see far into the invisible wavelengths of light, past what your eyes can detect, you'd find that our solar system sits inside a vast, glowing bubble of hot gas. It's called the local bubble, and it stretches for hundreds of light years in every direction. This bubble is thought to have been carved out by ancient supernova, exploding stars that blasted shock waves into the surrounding gas, heating and clearing it out. Now, our solar system drifts quietly through this low-density region, surrounded by a shell of hotter gas and dust. It's not dangerous, it's not something we can feel, but it's there, a kind of quiet chamber around us, born from violence long ago, now part of the gentle backdrop of our galactic neighborhood. There's a vast, empty region behind the Great Attractor. The Great Attractor is a mysterious gravitational anomaly, a region of space so massive that entire galaxy clusters, including our own Milky Way, are slowly drifting toward it.
But behind this immense concentration of matter lies something even stranger. A region known as the dipole repeller, where space appears unusually empty. It's not just a patch with fewer galaxies. It's a vast cosmic void, stretching for hundreds of millions of light years. And oddly enough, its emptiness seems to push galaxies away. Together, the Great Attractor and the dipole repeller create a quiet gravitational tug-of-war that helps shape the motion of our local universe. We're drawn forward by unseen mass and pushed back by the emptiness beyond. It's a reminder that in the cosmos, both presence and absence can shape the path we follow. Neutrinos pass silently through the Earth and through you. Right now, trillions of particles called neutrinos are passing through your body, and you'll never feel them. Neutrinos are incredibly light, neutral particles produced in enormous numbers by the sun, exploding stars, and even the early universe itself.
They barely interact with normal matter. They can fly straight through a planet or your entire body without leaving a trace. Some pass through detectors buried deep underground, where rare collisions help us study them. But most simply pass through unnoticed. These particles are everywhere, all the time, silently streaming through space and matter alike. They move at nearly the speed of light, and yet they almost never touch anything. The universe is full of motion, even when everything feels still. The most massive stars can collapse directly into black holes without a bang. We often imagine the death of a massive star as a violent supernova, a brilliant explosion lighting up the galaxy. But for the most massive stars, the end can be strangely quiet. Some stars are so heavy that when they run out of fuel, their cores collapse inward. And gravity wins so completely, so suddenly, that even the outer layers fall straight in.
No explosion, no bright farewell, just a sudden disappearance. This process is called a direct collapse. In a moment, a star is gone, replaced by a black hole, silent, invisible, and crushingly dense. Astronomers have even observed stars that seem to vanish without a trace, as if the light simply blinked out. It's a reminder that not all cosmic endings are fireworks. Some are whispers into the dark. Galaxies can orbit one another like moons around planets. We tend to think of galaxies as isolated islands in space, but many live in small groups where they interact and even orbit one another. Our own Milky Way, for example,
has dozens of smaller satellite galaxies. The large and small melanic clouds are the most famous. These companions move around the Milky Way like moons around a planet, slowly tracing long elliptical paths through space.
At times, larger galaxies draw stars away from their companions, creating flowing streams and tidal tails that can stretch across millions of light years. Gradually, a smaller galaxy may be entirely absorbed. These cosmic dances unfold over billions of years, slow, elegant interactions on a scale that is difficult to grasp. In the stillness of deep space, even galaxies can find companionship. The universe's most brilliant explosions arise from collapsing magnetic stars. There exists a rare type of blast known as a magnetar hypernova, and it may rank among the brightest events the universe can produce. A magnetar is a neutron star with an unimaginably intense magnetic field, trillions of times stronger than Earth's. When a massive star collapses into a magnetar and releases its energy rapidly, it can generate a flash of light and energy far exceeding that of a typical supernova.
These events may account for some long-duration gamma-ray bursts, brief surges of high-energy light that cross the universe and momentarily outshine entire galaxies. The explosion lasts only seconds, but its light can reach us from billions of light years away. It's one of the universe's most intense phenomena, created by a small, dense object wrapped in magnetic fire, collapsing in on itself. The edge of the observable universe is not the edge of the universe. When we look out into space, there's a limit to how far we can see. About 46 billion light-years in any direction. That's the edge of the observable universe. It's not a wall or a boundary, just the furthest distance light has had time to reach us since the Big Bang, given the expansion of space. Beyond that, the universe likely continues. We just can't see it yet. And because the expansion of space is accelerating, some parts of the universe are moving away from us faster than light.
That means their light will never reach us, not even in infinite time. The observable universe is like a bubble of vision, not the full size of reality, but just the part available to us. Beyond that, more galaxies, more stars, maybe forever. Some galaxies shoot jets of plasma for millions of light years. At the heart of many galaxies lies a supermassive black hole. And sometimes, as matter falls toward it, not all of that matter disappears. Some of it gets caught in magnetic fields and blasted outward in narrow, powerful jets. Streams of plasma moving near the speed of light. These jets can stretch far beyond the host galaxy itself, reaching lengths of millions of light years. We see them glowing in radio wavelengths, forming enormous lows that mark their reach. Galaxies like these are called radio galaxies, and their jets are among the largest structures in the universe. It's a strange irony.
The most powerful outflows can come from the regions around black holes, where light can barely escape.
Even silence, it seems, can leave a mark. There's a star that orbits the Milky Way backward. Most stars in the Milky Way orbit in the same general direction, following the galaxy's rotation, but not all of them. There's at least one known star that moves in the opposite direction. Its orbit is retrograde, cutting against a flow like a salmon swimming upstream. How did it get that way? One possibility is that it was part of a smaller galaxy that merged with the Milky Way long ago, and its orbit reflects that older, different system. Or it may have been flung into its current path by a gravitational slingshot, perhaps involving a black hole or dense star cluster. Either way, it's a quiet reminder that not all stars follow the rules. And even in the vast clockwork of the galaxy, there are wanderers going their own way. The center of the galaxy smells like raspberries and rum.
It sounds like a joke, but it's real. Astronomers studying the chemical composition of a dust cloud near the center of the Milky Way discovered a molecule called ethyl formate. On Earth, it's associated with the flavor of raspberries and the scent of rum. Of course, the galactic center doesn't actually smell. The vacuum of space wouldn't carry scent the way air does. But the presence of these molecules hints at the complex organic chemistry unfolding in deep space. There are alcohols, sugars, and even amino acid precursors in interstellar clouds. It's not life, but it's the kind of chemistry life might need. So, while space may not smell like fruit and liquor, it contains the building blocks floating silently between the stars. One galaxy is headed straight for the Milky Way, and it's already touching. The Andromeda Galaxy is our nearest large galactic neighbor, and it's on a slow-motion collision course with the Milky Way.
Right now, it's about 2.5 million light-years away. But that gap is closing. In about 4 billion years, the two galaxies will begin to merge. And interestingly, the outer halos of both galaxies, their vast clouds of hot gas and dark matter, are already overlapping. So, in a sense, they've begun touching already. The eventual merger will be more of a graceful blending than a crash. Stars will mostly pass by one another without colliding. Over time, the two spirals will become one larger elliptical galaxy. We sometimes call this future system Milka. It's a long wait, but it's already in motion. A cosmic meeting playing out over billions of years. The cosmic microwave background still glows all around you. Every part of the universe, including the space around you right now, is filled with a faint glow called the cosmic microwave background. It's the afterglow of the Big Bang, light released when the universe was about 380,000 years old. Back then, the cosmos was a hot, dense plasma. When it cooled enough for atoms to form, light was finally free to travel. That light has been moving ever since, stretched into microwaves by the expansion of space. Today we detect it as a near uniform glow in all directions. It's not something you can see or feel, but sensitive instruments can pick it up as a kind of cosmic whisper. This glow is the oldest light we can observe, a quiet signal from the universe's childhood, still echoing through space and time. Some supernovae are powered by invisible collapse, not light. Supernovae are known for their brightness, massive explosions that briefly outshine entire galaxies. But not all supernovae are luminous. Some are what astronomers call failed supernovae. In these cases, a massive star core collapses, forming a black hole. But the outer layers don't explode outward in a visible flash. Instead, they may fall inward, feeding the black hole silently. In rare instances, we've watched stars that seemed stable suddenly vanish from view. No explosion, no fading glow, just darkness. These disappearances suggest a collapse so complete that almost all of the energy is swallowed. There's still tremendous violence, but most of it is hidden. It's a reminder that not all cosmic deaths make noise.
Some happen in silence, deep inside gravity's grip. There are entire galaxies made mostly of gas and dark matter. We often picture galaxies as bright spirals or glowing ellipticals filled with billions of stars. But some galaxies are barely visible at all. These dim systems contain very few stars, but they still have mass, mostly in the form of gas and dark matter. They're difficult to detect with regular telescopes and often appear only as faint smudges or through indirect measurement.
Some of these galaxies may be failed systems, structures that never formed many stars, perhaps because they were stripped of gas or heated too early in cosmic history. Others may be temporary phases in galactic evolution. What they all have in common is subtlety. No fireworks, no spiraling arms, just quiet gravitational presence. They remind us that not all galaxies shine. Some simply exist. Black holes can collide and merge in cosmic dances. When two black holes orbit one another, they emit ripples in spacetime called gravitational waves. As energy leaks away, the black holes spiral inward until they merge in a final dramatic moment. Two invisible giants becoming one. These collisions don't make light, but they send out bursts of gravitational waves that we can now detect on Earth. The first of these signals was observed in 2015, confirming a century-old prediction by Einstein. Since then, we've detected dozens more. Each one tells a story about massive objects colliding in distant galaxies long ago. These black hole merges happen quietly, invisibly, but with incredible force, converting entire solar masses of energy into waves that ripple across the universe. And for a moment, the fabric of space itself sings. Some stars die in slow motion, taking billions of years to fade. Not every star ends in a sudden explosion. Smaller stars, like our Sun, die much more slowly. After burning through their hydrogen fuel, they expand into red giants, shedding their outer layers into space. What remains is a dense, hot core, a white dwarf. This remnant no longer produces energy. It simply radiates away its leftover heat very, very slowly. A white dwarf can take billions of years to cool, gradually dimming until it becomes invisible. A black dwarf. But the universe isn't old enough for that to have happened yet. Every white dwarf that's ever formed is still glowing somewhere, quietly fading in the dark.
The death of these stars is less like a firework and more like an ember cooling gently over cosmic time. Time near a black hole slows down compared to Earth. In Einstein's theory of general relativity, gravity doesn't just pull on matter, it bends space and time. The stronger the gravitational field, the slower time flows relative to areas of weaker gravity. Near a black hole, where gravity is extreme, this effect becomes dramatic. If you were to orbit just outside the event horizon, time for you would pass much more slowly than for someone far away. Minutes near the black hole could mean years elsewhere. This isn't science fiction. It's a real, measured effect called gravitational time dilation. We've even observed it in milder form with GPS satellites around black holes. It becomes profound. In a way, they don't just trap light, they stretch time itself. The void between galaxies is colder than any lab on Earth.
Far from stars, planets, or even gas clouds, the vast spaces between galaxies are astonishingly cold. The temperature there drops to just a few degrees above absolute zero, about 2 degrees. 7 Kelvin. That's colder than any natural place on Earth, and colder than most environments we can create, even in advanced laboratories. This chill comes from the near total absence of particles and energy. There's nothing to hold heat, just a scattering of stray atoms and the faint microwave glow of the early universe. These intergalactic voids are the quietest, loneliest places we know. Enormous and empty, stretched across millions of light years. They are the universe's deepest shadows, holding only the background whisper of creation. The universe is getting more transparent as it ages. In the early universe, light couldn't travel freely. The cosmos was filled with a hot plasma, a fog of free electrons and atomic nuclei that scattered photons constantly.
But as the universe expanded and cooled,
It reached a point where electrons combined with nuclei to form neutral atoms. Suddenly, light could move unhindered. This event, called recombination, happened about 380,000 years after the Big Bang, and it released the cosmic microwave background we still detect today. Since then, the universe has continued to grow more transparent. The formation of galaxies and stars added new pockets of light, and as matter spreads out, there's less and less to block a photon's path. With time, the darkness has become clearer. Space, once glowing and opaque, now lets light pass through almost unimpeded. The first stars were giants, short-lived and fierce. The earliest stars, born when the universe was still young, were unlike most we see today. They were immense, hundreds of times more massive than the sun, blazing hot and bright. These giants lived short lives, burning through their fuel in just a few million years before collapsing in powerful supernova. With no heavy elements to temper them, they were made almost entirely of hydrogen and helium, pure children of the Big Bang. Their light pierced the darkness of the early universe, beginning the long process of reionization that made space transparent. Though none of these first stars survive today, their echoes remain in the elements they forged and the galaxies they helped shape. They were the first lanterns in a dark cosmos, brief but vital, laying the foundations for every star, planet, and world that would come after. They forged the first heavy elements in their cores. Within the blazing hearts of those early stars, nuclear fusion worked tirelessly. Hydrogen fused into helium, then into heavier and heavier elements as the stars aged. But only the most massive could go further, creating carbon, oxygen, and even iron before collapsing. When they exploded as supernova, these elements were scattered into space, mixing with the raw hydrogen and helium that still lingered. These heavy elements became the building blocks of later generations of stars, and eventually of planets and life. Without the furnaces of those ancient stars, the universe would contain no iron for blood, no carbon for cells, no oxygen for breath. To realize this is to see stars not only as lights in the sky, but as alchemists forging the ingredients of life. We are the children of their fire, shaped by the remnants of their blazing cores. Every atom in your body was born in a star. The calcium in your bones, the oxygen in your breath, the carbon in every cell, all of it was forged in stars. Long before Earth existed, stars lived and died, scattering their elements into the galaxy. Over countercycles, these elements gathered into new clouds, which collapsed to form new stars, new planets, and eventually, us. You are quite literally made of stardust. This is not a metaphor, but a scientific truth. Without the alchemy of stars, there would be no matter to build life. When you look up at the night sky, you are looking at your own history, written in fire and fusion. Every twinkle is a reminder that we are deeply connected to the cosmos. Our very bodies built from its remnants.
To rest beneath the stars is to rest among family, kin to the universe itself. Some regions of the universe are expanding away from us forever. The universe is expanding, and that expansion is accelerating. As space stretches faster and faster, some galaxies are being pushed away so rapidly that their light will never reach us. Even if we waited forever, the space between us and those galaxies would grow too quickly for the light to close the gap. They've already passed a point of no return, slipping beyond the cosmic event horizon. Eventually, more and more of the universe will fade from view,
Not because it's gone, but because its light can no longer reach us. This isn't something we'll feel day to day, but over billions of years, it means the visible universe will shrink. The cosmos isn't just growing, it's also quietly letting go. Some black holes may be primordial, born before stars. Most black holes form from the collapse of massive stars. But there's another possibility. Black holes that formed in the earliest moments of the universe before stars even existed. These are called primordial black holes. They may have formed from tiny fluctuations in the dense, hot conditions just after the Big Bang, regions where gravity pulled matter together into ultra-compact knots. Some of these black holes could be incredibly small. Others might have grown over time. We've never directly detected one, but if they exist, they could help explain dark matter, seed the formation of galaxies, or unlock new insights into the early universe. They be older than stars, older than galaxies, silent fossils of the first seconds after time began. Entangled particles may link distant corners of the cosmos. Quantum entanglement is one of the strangest phenomena in physics. When two particles are entangled, their properties remain linked no matter how far apart they are. Change one, and the other changes instantly, even across vast distances. It doesn't transmit information faster than light, but it does suggest that reality at the quantum level is deeply interconnected. Some physicists think entanglement could play a role in the fabric of space-time itself, maybe even helping to hold space together. In theory, particles created in the early universe could still be entangled today, stretched across the expanding cosmos. If so, there may be quiet, invisible threads connecting distant regions. Quantum echoes from the dawn of time still present in the emptiness between galaxies. Even empty space hums with quantum fluctuations. At first glance, a vacuum seems like nothing at all. But on the smallest scales, even empty space is restless. Quantum physics tells us that pairs of particles and antiparticles flicker in and out of existence constantly, borrowing energy for a moment before disappearing again. This jittery dance is called quantum fluctuation, and it happens everywhere, all the time. Though fleeting, these tiny events may have shaped the universe itself. The ripples in the early cosmos, which grew into galaxies and clusters, may have begun as quantum fluctuations stretched by cosmic inflation. What looks like nothing is in truth a froth of activity, subtle and unseen. To imagine this is to realize that emptiness is never truly empty. It is alive with potential, humming quietly beneath reality, a hidden foundation for all that exists. The universe began in a fiery expansion we call the Big Bang. More than 13 billion years ago, everything we know, space, time, matter, and energy, was compressed into a single, hot, dense state. In an instant, it began to expand. This moment, called the Big Bang, was not an explosion into space, but the stretching of space itself. From that first fiery expansion came all the seeds of the cosmos, the galaxies, the stars, the planets.
and life itself. Though the idea can feel overwhelming, its traces are written in the sky, in the glow of the cosmic microwave background, and in the motions of galaxies still rushing apart. To know the universe began in such a moment is to feel both small and deeply connected. Every star you see tonight, every atom within you, began in that single cosmic unfolding, when time itself first began its endless journey. For a fraction of a second, space expanded faster than light. In the very first heartbeat after the Big Bang, the universe went through a phase called inflation. In less than a trillionth of a second, space itself expanded faster than the speed of light, swelling the cosmos unimaginably in an instant. This rapid growth smoothed out the universe, stretching tiny quantum fluctuations into vast ripples that would one day seed galaxies and stars. Though we cannot see inflation directly, its fingerprints remain in the structure of the cosmos all around us. To imagine it is almost impossible. A moment when distances greater than galaxies grew from something smaller than an atom. And yet without it, the universe would be uneven, chaotic, and nothing like the graceful web we see today. Inflation was the silent breath that set the stage for everything that followed. The very first whisper of the cosmos as we know it. Gravitational waves travel at the speed of light. Gravity doesn't just pull, it can ripple. When massive objects like black holes or neutron stars collide, they send waves through the fabric of space-time itself. These gravitational waves stretch and squeeze space as they pass, moving outward in all directions, and they travel at the speed of light, the fastest possible speed in the universe. It took decades to develop instruments sensitive enough to detect them. But now we can listen to these cosmic ripples from Earth. Each wave carries information about distant cataclysms, how much mass was involved, how fast the object spun, even how warped space became. Gravitational waves are silent to our ears, but they are real, measurable, and surprisingly gentle. Tiny shutters in the deep structure of the cosmos. The cosmic web connects galaxies across the universe. If you could map the positions of galaxies on the largest possible scale, you'd find something beautiful. A vast, interconnected pattern of filaments and voids called the cosmic web. Galaxies don't sit alone in space. They gather along invisible threads of dark matter and gas, stretching like tendrils between clusters. Where filaments cross, we find superclusters, enormous knots of galaxies. Between them lie immense quiet voids, almost empty. The cosmic web isn't something we can see with a telescope all at once, but its structure emerges from large surveys of the sky. It resembles a network or a foam or even the branching patterns of neurons. It's the shape of the universe on its grandest scales, not random but woven, like something grown rather than built. The James Webb Telescope can see galaxies that no longer exist. The James Webb Space Telescope was built to look farther than ever before, and in doing so, it also looks further back in time. Because light takes time to travel, distant galaxies appear to us as they were billions of years ago. Some of the galaxies Webb observes may no longer exist in the form we see them. They may have merged, faded, or changed entirely. But their light is still arriving, a snapshot frozen in time, still crossing space long after the source has changed. This is one of the quiet oddities of astronomy. Telescopes don't show us what's out there now. They show us what was at different moments across the history of the universe. Every deep field image is also a time machine, a gallery of vanished light. A second near a black hole could be years far away. Imagine standing near the edge of a black hole. To you, each second feels ordinary, passing as it always does. But if someone far away were watching, your seconds would stretch into years. This is the effect of gravitational time dilation taken to its extreme. The immense pull of the black hole slows time so dramatically that an entire lifetime could pass for someone near it, while only moments slip by for those far from its reach. In science fiction, this idea often fuels stories of travelers returning home to find centuries gone. If it is no mere story, the math of relativity shows it to be real.
To think that time itself can stretch and warp depending on where you are is humbling. Near a black hole, the border between minutes and millennia blurs, and reality itself bends into strangeness. Light from the early universe is stretched into gentle red. As the universe expands, the light traveling through it is stretched. What began as brilliant short wavelengths slowly lengthens, softening into redder hues. This effect, called redshift, is why the light from distant galaxies appears shifted toward red. The space between us and them has expanded during its journey. The farther away a galaxy is, the more its light is stretched, carrying with it a record of how the universe has grown. Some of the oldest light reaching us from galaxies billions of light years away has been stretched so much that it now falls into the infrared, beyond what our eyes can see. Using specialized telescopes, astronomers collect this softened glow and look back into deep cosmic history. It is as if the universe itself lowers its voice as it ages, pulling light into longer wavelengths. A gentle reddening that quietly records the expansion of time. Some galaxies shine most strongly in ultraviolet light, far outside human vision. Not every galaxy glows in colors we can perceive. Certain galaxies radiate primarily in ultraviolet, invisible to us but detectable with sensitive instruments. These are often places of intense star formation, filled with newborn stars that emit energy in the hottest, brightest part of the spectrum. To human eyes, they might appear dim or unremarkable, but in ultraviolet view, they blaze with power, their spiral arms laced with brilliant knots of stellar birth. It is like a hidden version of the universe, existing just beyond the limits of our senses. Telescopes such as Hubble have uncovered this unseen beauty, revealing galaxies in wavelengths our eyes were never meant to see. They remind us that what we see is never the whole story. Beyond our narrow vision, the cosmos shines with colors and patterns invisible to us, yet woven deeply into the fabric of creation. The universe may be infinite. When we look up at the stars, it's natural to wonder if there's a boundary somewhere, an edge to everything. But current observations suggest that space might go on forever. We can only see a finite region, the observable universe. But beyond that, the universe may continue without limit. No edge, no center, just more galaxies, more stars, more space. If that's true, it means that most of the universe will always be beyond our reach. We'll never see all of it, no matter how far we look or how long we wait. An infinite universe doesn't mean infinite possibilities, but it does mean endlessness, a quiet vastness that stretches on gently and without conclusion. Cosmic rays strike Earth from deep space.
Every second, high-energy particles called cosmic rays hit our planet. Some from the sun, others from distant parts of the galaxy or even beyond. They're made of protons, atomic nuclei, and other fragments accelerated to incredible speeds by exploding stars, black holes, or mysterious cosmic forces. Most are deflected by Earth's magnetic field or absorbed by the atmosphere, but some reach the surface and a few even pass through you. These particles are mostly harmless in small doses, but they're a quiet reminder that space is not empty. It's alive with motion, energy, and invisible messengers from far-off events. Every now and then, a cosmic ray hits a detector and tells a story that began light years away. A particle's journey from a supernova to your sky. There may be no such thing as before the Big Bang. The phrase "before the Big Bang" seems natural, but it may not make sense. According to general relativity and many cosmological models, time itself began with the Big Bang.
That moment wasn't just the birth of matter and energy. It was also the beginning of space and time as we know them. Asking what came before is a bit like asking what's north of the North Pole. Some theories suggest a previous state or universe, while others describe a quantum realm where time behaves differently or doesn't exist at all. But in most models, before the Big Bang isn't a place we can visit, even in thought. The Big Bang wasn't an explosion in space. It was the beginning of space. Some planets circle so close that they are torn apart. Some planets orbit so close to their stars that they are locked in a perilous embrace. Gravity stretches them, pulling their shapes into ovals, while intense heat strips their atmospheres away. In the most extreme cases, these worlds are literally torn apart, their matter pulled off and devoured by the star itself. These planets are often called hot Jupiters or ultra-close exoplanets, circling in just days or even hours.
The forces they endure are unimaginable, shaping them into strange forms and leaving behind trails of gas streaming across space. They remind us that not all orbits are safe or stable. Some worlds live on the edge of destruction, held too close to the very stars that once gave them life. To picture them is to feel the power of gravity itself, shaping destinies with no escape. Some are so distant they take millennia to complete an orbit. While some planets skim close to their stars, others wander far on enormous paths. These distant worlds may take centuries, even millennia, to complete a single orbit. Their skies are dim, their warmth faint, and yet they remain bound by gravity, tracing their endless loops around the stars that hold them. In our own solar system, the dwarf planet Sedna takes more than 10,000 years to travel once around the Sun. Farther out in other systems, there may be worlds even more remote, drifting in the thin light of their suns.
Imagine a year that lasts longer than human civilization itself. A world where seasons unfold across entire ages. These planets move at the very edge of belonging, still tied to their stars, yet almost free. They remind us how vast space is and how many ways a planet can live. Moons may outnumber planets by the trillions. Planets may be rare jewels of the cosmos, but moons may be even more common. Around gas giants, around rocky worlds, even around dwarf planets, moons gather in abundance. Some are larger than planets themselves, with atmospheres and hidden oceans. Others are small, captured asteroids pulled into orbit long ago. In our solar system, moons outnumber planets by far. And if we look beyond, it is likely the same across the galaxy. Trillions of moons may circle their worlds, shaping tides, sparking volcanism, and sometimes even nurturing life. Europa, Enceladus, Titan. These moons in our own neighborhood already hint at the possibilities.
Each is a world in miniature, unique in its landscapes and mysteries. To think of the universe filled with moons
is to imagine a cosmos of endless companions circling quietly in the glow of their parent worlds. In the distant future, stars will stop being born. Star formation depends on cold gas, clouds of hydrogen and helium that collapse under gravity. But over time, this fuel becomes scarce. It gets locked up in stars, blown away by supernova, or heated beyond usefulness. Billions of years from now, galaxies will run out of the material needed to form new stars. The ones that remain will age, burn out, and fade away. First the blue giants, then the suns, then the red dwarfs, until even the slowest burning embers cool into blackness. The universe won't end all at once. It will dim by degrees, quietly and gently. What's left will be black holes, white dwarfs, neutron stars, and the silence of a cosmos grown cold. Not tragic, just still.
Most matter in the universe is invisible. When we look at the universe, stars, galaxies, nebula, we're only seeing a small fraction of what's really there. Most of the matter in the cosmos doesn't shine. It doesn't emit or reflect light. This invisible substance is called dark matter. And although we've never detected it directly, we know it exists because of its gravitational effects. Galaxies spin faster than they should. Light from distant objects bends more than expected. Clusters hold together with more strength than their visible mass allows. All of this suggests a hidden mass, more than 5 times the amount of ordinary matter. Dark matter is everywhere, shaping the structure of the universe. We just can't see it. It's a quiet, invisible framework holding everything else in place. Light from the first galaxies has been stretched by cosmic expansion. When light travels through space, it doesn't just move, it stretches. That's because the universe itself is expanding, and as it grows, it pulls light waves along with it. The light that left the first galaxies billions of years ago has been stretched into longer wavelengths, moving from visible light into the infrared. This process is called redshift, and it's one of the main ways astronomers measure distance and time in the universe. The more stretched the light, the farther and older its source. With telescopes like James Webb, we can finally see that ancient light, now softened and greened by the journey. What began as the glow of young stars now arrives as a whisper, stretched by the breath of space itself. Some worlds are covered entirely in oceans. Imagine a planet where there is no land at all, only endless ocean stretching in every direction. Astronomers call them ocean worlds, and they may be common in our galaxy. These planets are covered in deep layers of water, perhaps hundreds of kilometers thick, with currents, storms, and waves rolling across their entire surfaces. Beneath, there may be high-pressure ices, or even hidden oceans warmed by internal heat. If life were to evolve there, it would live in seas without shorelines, drifting forever in alien tides. Even in our solar system, moons like Europa and Enceladus hint at vast hidden oceans beneath their icy shells. To think of a planet entirely given to water is to imagine something both familiar and strange. A world like Earth, yet without continents, only an eternal sea under foreign stars. Some planets burn with seas of lava. At the other extreme, a world so close to their stars that their surfaces are oceans of fire. Temperatures soar high enough to melt rock, creating vast seas of lava that churn and blow like rivers of molten metal. Some of these planets are called lava worlds, where dayside heat is unbearable, while the night side may freeze into stillness. The contrast can be extreme, one half blazing, the other silent and cold. These planets remind us how violent and varied the cosmos can be.
To imagine standing on one is impossible. The ground itself would ripple with heat, and the sky would shimmer with burning light. Yet they exist, circling in tight, dangerous orbits, showing us what happens when gravity pulls a world too close to its star. They are fiery reminders of how delicate balance must be for life to thrive. Some planets ring diamonds in their skies. Far from Earth, in the crushing atmospheres of giant planets like Neptune or Uranus, carbon may fall as rain. But instead of water, the pressure and heat transform it into diamonds. These glittering crystals form deep in the atmosphere, tumbling downward like gems from a hidden storm. On some worlds, scientists think the entire mantle could be made of diamond, forged by unimaginable pressures. Even exoplanets far away may experience the same. It's a vision both surreal and beautiful. Rain that sparkles, not with drops of water, but with shimmering jewels. The universe in its variety creates weather beyond anything Earth has ever known. To drift to sleep, imagining a storm of diamonds falling endlessly through alien skies, is to realize just how strange and how wondrous other worlds might truly be. The universe could end in a slow, quiet fade. Cosmologists once wondered if the universe would collapse back in on itself. But the evidence now suggests a different fate: slow, endless expansion. As galaxies drift farther apart and star formation slows, the night sky will grow darker. Existing stars will burn out one by one. Black holes will evaporate. Matter itself may decay, and the universe will become colder, quieter, and emptier. A state called heat death. It's not a sudden event, but a long, gentle fade. Over the trillions of years, the cosmos will grow still as energy spreads thin and structures dissolve. It's not the end as fire or ice, but as silence. A universe that whispered itself into being and eventually whispered itself away. Some galaxies have super winds that blow away stars. At the heart of some galaxies, especially those with active black holes or intense star formation, powerful winds can blow out from the center, carrying gas, dust, and even young stars with them. These galactic superwinds can stretch for tens of thousands of light years, pushing material into intergalactic space. They're driven by radiation, magnetic fields, and the explosive energy of supernova. Over time, these winds can strip a galaxy of its star-forming gas, leaving it quiet and red. They also help spread heavy elements into the cosmic web, seeding future generations of stars and planets. In this way, a galaxy breathes, taking in matter, igniting life, and then exhaling into the void. The far future of the cosmos is an endless, dark ocean. Trillions of years from now, the universe will look very different. Galaxies will have drifted apart so far that each one will seem alone in the dark. New stars will stop forming. Old stars will burn out. Even the faint glow of white dwarfs will fade. What remains will be cold, scattered remnants, black holes, and the thin echo of ancient light. Over unimaginably long timescales, black holes will evaporate, and even matter itself may decay. Eventually, all that remains will be particles moving through empty space, silent, slow, and the lone. This future is called the heat death of the universe. But it's not a sudden end. It's a vast, dark stillness. A cosmic ocean with no waves, no wind, and no shore. There are stars so large they could swallow our solar system. Among the giants of the cosmos are hyper-Eant stars, swollen to unimaginable proportions. Some are so vast that if placed where our sun is, they would stretch beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars within their blazing atmospheres.
These colossal stars burn fiercely, living fast and short lives compared to smaller suns. Their outer layers expand outward like vast shimmering veils of gas, trembling at the edge of collapse. From afar, they glow with an intensity that can outshine hundreds of thousands of ordinary stars. Yet, their very size is also their undoing. They are unstable, prone to shedding their mass in great storms of gas, and destined to die in catastrophic explosions. To imagine such a star is to feel the scale of the universe, immense, fiery, and humbling, beyond anything we could ever witness up close. Some stars are barely bigger than a planet. At the opposite extreme, there exists stars so small they blur the line between planets and suns. These are red dwarfs, the most common type of star in the galaxy. Some are only a little larger than Jupiter, glowing dimly with cool red light.
Though small, they are stable and can live for trillions of years, far longer than the universe has yet existed. Around many of these faint suns, planets circle quietly, perhaps warmed just enough for oceans and skies to form. To us, they are almost invisible without telescopes, hidden by their faintness. But they make up the majority of stars in the Milky Way. If life is abundant in the universe, it may be these quiet, long-lived stars that host the greatest number of worlds. They remind us that greatness in the cosmos is not always about size or brilliance, but endurance. Pulsars spin with the precision of cosmic clocks. When massive stars explode, their cores may collapse into neutron stars, objects so dense that a teaspoon of their matter would outweigh mountains. Some of these neutron stars become pulsars, spinning rapidly and beaming radio waves from their magnetic poles. As they rotate, these beams sweep across space like the beam of a lighthouse.
To observers on Earth, pulsars appear to pulse with astonishing regularity, ticking like cosmic clocks with a precision unmatched by almost anything in nature. Some spin many times each second, their rhythm steady for millions of years. Pulsars have helped astronomers test theories of gravity, map the galaxy, and even discover planets. Yet, they are also haunting reminders of the power of collapse. The remnants of stars once blazing, now reduced to tiny, spinning embers, flashing endlessly in the dark, steady as time itself. Black holes can twist space into a funnel of time. A black hole doesn't just trap light, it warps space-time itself. As you approach its event horizon, space bends inward and time slows down. To an outside observer, time near the black hole appears to crawl. At the very edge, it almost stops. This warping creates something like a funnel in the geometry of space. Narrow, steep, and one way. Inside, all paths lead toward the center, the singularity.
The closer you get, the more time and space seem to trade places, with inward becoming a direction in time, not space. You can't go back. This twisting of space-time is more than metaphor. It's geometry, drawn by gravity, written in the fabric of reality itself. Some regions of the universe may never see each other again. Because the universe is expanding and accelerating, some parts of it are already moving apart faster than light can travel. This means that even if we wait forever, the light from those regions will never reach us. The same is true in reverse. There are places we can never send a message to because the space in between is stretching too quickly. Over time, more and more of the universe will slip beyond reach. Each galaxy will become an island, isolated in space, surrounded by darkness. This doesn't break the laws of physics. Nothing is moving through space faster than light,
But space itself can grow calmly and unstoppably, separating one piece of the cosmos from another forever. The heaviest element made in a star explosion is gold. Gold is rare on Earth, not just in our economy, but in the universe itself. It can't be made in the core of an ordinary star. Instead, it forms in the most extreme events, the collisions of neutron stars or certain kinds of supernova. In those moments, atomic nuclei are smashed together under incredible pressure and heat, creating heavy elements like gold, platinum, and uranium. These precious atoms are then scattered into space, mixed into gas clouds, and eventually become part of new stars, planets, and people. Every gold ring, every fleck of dust was born in a cosmic catastrophe, a quiet trace of violence now resting on your hand. In that sense, gold is not just beautiful, it's ancient. It's stellar, and it came from a universe that forges treasure in fire. There are stars that end in explosions bright enough to outshine galaxies. Some stars live fiercely and end suddenly in an explosion called a supernova. When their fuel runs out, their cores collapse under immense gravity, and in an instant, the star releases a wave of energy so powerful it can outshine an entire galaxy for weeks. These cosmic fireworks scatter heavy elements across space: iron, gold, calcium, carbon, the very ingredients of planets, oceans, and life itself. Without supernova, Earth could never have formed. To witness one is rare and astonishing. Astronomers on Earth have recorded them throughout history, sometimes appearing as sudden new stars, bright enough to be seen in daylight. Yet, they are not endings alone. Each explosion is also a beginning, enriching the universe so that new stars, new planets, and perhaps new life can emerge. In the vast cycle of creation and destruction, even death brings light. Our Milky Way contains hundreds of billions of stars. When you look up at the night sky, you see only a handful of stars. Yet, our galaxy, the Milky Way, contains hundreds of billions. Most are too faint or too distant for our eyes to see undated. But together, they form a great spiral disk, stretching more than 100,000 light-years across. Within it are stars like the Sun, stars larger and brighter, and others barely glowing. Our galaxy is a vast, starry city, its spiral arms threaded with gas clouds where new stars are born. To us on Earth, the Milky Way appears as a pale band across the sky. But in truth, that hazy glow is the combined light of countless suns. To realize that every point of light belongs to this enormous family is humbling. We live within a single galaxy, one among trillions, carrying the quiet glow of ancient starlight. At its heart lies a supermassive black hole. Deep in the center of the Milky Way lies Sagittarius A*.
a supermassive black hole more than 4 million times the mass of our Sun.
Invisible on its own, its presence is revealed by the way stars whirl around it, orbiting at incredible speeds, as though caught in the grip of an unseen giant.
If you could stand near it, time itself would slow, light would bend, and space would stretch toward the abyss. Yet most of the time, it rests quietly, cloaked in darkness. Occasionally, it flares as gas drifts too close and vanishes into its depths. To know that such a monster resides at the heart of our home galaxy is both unsettling and awe-inspiring. And yet, it has been there since the Milky Way's earliest days, shaping its history and quietly keeping its place at the very center of our cosmic neighborhood. There are stars that flicker like fireflies in the night. Not all stars shine with steady light. Some pulse, shimmer, or dim and brighten in rhythmic patterns. These variable stars change for many reasons: internal pressure waves, surface eruptions, or eclipsing companions.
From Earth, they look like they're flickering gently in the sky, blinking with a slow, stellar rhythm.
Some complete their cycle in hours, others in years. These variations aren't random. Many are remarkably consistent, acting like celestial clocks. Astronomers use them to measure distances across the universe. A single flicker, repeated over and over, can tell us how far away a star is and even how bright it truly is. Stars don't just burn. Some of them breathe. Some black holes wander through space alone. Not all black holes live in the centers of galaxies. Some roam. A black hole can be ejected from its birthplace by gravitational interactions kicked out of a galaxy during a collision, or flung away by the recoil of a merger. Once released, it becomes a rogue object, moving silently through interstellar or even intergalactic space. These wandering black holes are hard to detect. They emit no light unless they pass through gas or pull on nearby stars, but they're likely out there, drifting through darkness, unseen and unbound. They carry no orbit, no companion, no home. Just mass, motion, and the deep gravity of a thing that fell inward and never stopped falling. Even black holes can get kicked across the galaxy. When two black holes merge, the violent event sends out a burst of gravitational waves. But those waves aren't always symmetrical. If the merger sends more energy in one direction, it can give the new black hole a kind of recoil, a gravitational kick strong enough to hurl it away at thousands of kilometers per second. Some black holes may be flung entirely out of their galaxies, doomed to drift through intergalactic space. Others settle into wide, wandering orbits. These kicked black holes are hard to spot, but astronomers believe they exist. Silent travelers pushed by the memory of their own collision. Even the heaviest, most anchored things in the universe can be moved by the right kind of wave.
Ancient starlight travels for billions of years before reaching us.
Every time you look up at the stars, you are looking into the past. Light does not travel instantly. It takes time to cross the gulf of space. The light from our sun is 8 minutes old by the time it touches Earth. The light from the nearest stars may be decades old. And the faintest galaxies we see through telescopes send us messages that have been traveling for billions of years, crossing most of cosmic history to reach our eyes. In a way, the night sky is a vast time machine, showing us the universe as it once was. Some of the stars we see may no longer exist, their light still racing onward long after they have faded. To watch the stars is to catch whispers of ancient stories written in photons carrying memories across the ages. A faint cosmic glow still echoes from the birth of the universe. Long ago, the universe existed as a hot, radiant ocean of particles. As it expanded and cooled, light was finally released and began a long outward journey. That ancient light is still with us today, stretched into faint microwaves by billions of years of cosmic expansion. We call it the cosmic microwave background, a dim glow that fills the entire sky, unseen by our eyes, but detectable with delicate instruments. It is the lingering afterglow of the Big Bang, a remnant from a time when the universe was only a few 100,000 years old. To chart it is to glimpse the earliest ripples of structure, the seeds from which galaxies and stars would eventually grow. Quiet, ancient, and everywhere. This glow is the oldest light the universe carries. A whisper from its blazing beginning, still surrounding us as we drift through space. An invisible web of dark matter binds galaxies together. Although galaxies are composed of stars, gas, and dust, these visible components alone cannot explain how they move.
Something unseen must be at work, holding them in place.
That something is called dark matter, an invisible form of matter that does not shine, does not glow, and cannot be touched, but outweighs all the stars we see. Dark matter forms a vast, hidden web, its gravity sculpting the large-scale structure of the cosmos. Galaxies are like beads caught along its threads, bound together by its invisible hand. Though we cannot see it, we can measure its presence in the motions of stars and the bending of light. To imagine the universe without dark matter is impossible. It is the silent framework upon which all else hangs. We live inside its shadowy embrace, held by something we cannot yet fully know. The light from a distant star can be twisted by a single planet. We usually think of gravity bending light on a massive scale, by stars, black holes, or galaxies. But even a planet can do it. If a planet passes directly between a distant star and Earth, it can act as a tiny gravitational lens, magnifying and distorting the starlight. This effect is called microlensing. It's subtle and rare, but powerful enough to reveal planets we could never see otherwise, even in other galaxies. A flicker in the light, a gentle curve in the brightness, and suddenly a world is revealed. The planet itself might be cold, dark, and invisible, but its presence twists the starlight ever so slightly, and that twist is enough to say, "I'm here." The universe once glowed with a brilliant orange light. In the early days after the Big Bang, the universe was a hot, dense plasma, glowing with intense light. But as it expanded and cooled, that glow shifted. When the temperature dropped to around 3000 Kelvin, the first atoms formed and light could travel freely. At that moment, the universe would have looked orange.
Not the blue-black of night we see now, but a soft, warm radiance filling all of space. This light has since been stretched by the expansion of the universe into the faint microwave glow we detect today, the cosmic microwave background. But long ago, there was a time when the entire cosmos glowed orange, as if lit from within, a quiet ember fading into time. Some parts of the universe are cooling slower than others. As the universe expands, it cools gradually, gently, like a vast oven being turned off. But not every region cools at the same rate. Some areas, filled with more matter or trapped light, retain heat longer. Clusters of galaxies, for example, contain hot gas that remains warm for billions of years. Other regions are more isolated and chill more quickly.
These temperature differences affect how structures form, how stars evolve, and how long certain processes can last. Even in a universe governed by simple rules, there are local variations.
Warmer pockets, slower fates, small delays in the great unfolding. The universe doesn't cool like a machine. It cools like weather, uneven, textured, and quietly alive. The universe may be infinite, yet we see only a small part of it. When you look into the night sky, you're seeing only the smallest glimpse of what may exist. Our telescopes can peer across billions of light years, yet even then, the universe continues beyond our sight. It may stretch forever, endlessly unfolding. Or it may curve back upon itself in ways we cannot yet imagine. What we can see is called the observable universe, a sphere around us limited by the age of light itself. Beyond that boundary, there may be countless galaxies, stars, and worlds, hidden not by distance alone, but by the very fabric of time. The thought is both humbling and soothing. We live inside a cosmic horizon, like a small island surrounded by an infinite sea. To gaze upward is to stand at the edge of everything we know, with the possibility that the universe has no edge at all. A mysterious force called dark energy is pushing space apart. Not only is the universe expanding, it is expanding faster and faster, as though pushed outward by a hidden force. Astronomers call it dark energy, a mysterious pressure woven into the fabric of space itself. We do not know what it is, only that it makes up most of the universe, and its effects grow stronger with time. Because of dark energy, distant galaxies are racing away from us more quickly than ever before. And in the far future, they will drift beyond sight altogether. Dark energy is perhaps the greatest mystery in cosmology, a quiet force guiding the destiny of everything. It means that the universe is not static, but alive with motion, an ocean of space swelling ever outward. To rest beneath the stars is to feel its gentle pull, carrying all things slowly apart into the unknown.
Black holes twist space and time into impossible shapes. At the heart of collapsed stars, or at the center of galaxies, lie black holes, regions where gravity grows so strong that nothing, not even light, can escape. To approach a black hole is to step into a place where space and time themselves are bent and twisted. Clocks tick more slowly. Light stretches and re-eens. To an outside observer, anything falling in seems to freeze at the edge forever. Yet from within, the fall continues unstoppably to a hidden singularity. Some black holes are small, just a few times the mass of our Sun, while others are monsters millions or billions of times larger. They are silent, invisible, and mysterious. Yet, they shape galaxies and stir the fabric of the cosmos. To imagine them is to confront the strange truth that the universe is not only vast, but stranger than our deepest dreams. We might one day watch the birth of a new universe.
Some theories of cosmology suggest that new universes could form within our own, being off through quantum fluctuations, black holes, or other mechanisms we don't yet understand. If this happened, it would likely occur far from us, beyond any observational reach. But in theory, it might be possible to witness the signs. A sudden expanding bubble of new physics tearing away from our familiar reality. We don't know if this has ever happened. We don't know if it ever will. But the idea remains that somewhere, someday, the quiet darkness of our universe
could give birth to something new. A beginning inside an ending, a whisper inside a silence. The cosmos is still ringing from its earliest moments. In the first fraction of a second after the Big Bang, the universe expanded explosively, an event known as inflation. That burst of motion left behind ripples, tiny quantum fluctuations stretched across space.
These ripples became the seeds of all future structure, galaxies, stars, planets, and they also left behind echoes. We see them in the cosmic microwave background as temperature variations, and we may one day detect them as primordial gravitational waves, faint rhythmic pulses in the fabric of space-time itself. The universe may seem quiet now, but it still carries the memory of that first vibration, like a bell still humming softly long after the strike. The universe is vast, and you are a way for it to know itself. Of all the strange facts in astronomy, perhaps the most quietly astonishing is this: you are made of stardust. The carbon in your body, the calcium in your bones, the iron in your blood, all were forged in stars, scattered across space and gathered into life. You are not separate from the cosmos. You are a moment of it made conscious, a flicker of awareness in a universe that otherwise only moves and burns and cools. In this sense, the universe has grown eyes, and through those eyes, it looks back at itself, wonders at itself, dreams of itself. And even now, as you drift towards sleep, it keeps dreaming. Galaxies drift like islands across an endless sea of darkness. Each galaxy is a floating city of stars bound together by gravity, yet adrift in the vastness of space. They glide slowly, silently across a cosmic ocean, their spirals and ellipses shaped by billions of years of motion. Our own Milky Way is just one of trillions moving gently through the void, drawn by the subtle pull of its neighbors. Sometimes galaxies approach one another, merging in long, graceful dances that take hundreds of millions of years. Other times they drift apart, carried on the steady current of cosmic expansion. When we look at a galaxy far away, we see it not as it is now, but as it was millions or billions of years ago, frozen in the past. To imagine them all scattered like glowing islands across a dark and endless sea is to glimpse the quiet majesty of the universe. Stars are forged in hidden nurseries of gas and dust. In the quiet depths of space, there are vast clouds of gas and dust, dark, cold, and invisible to the naked eye. Yet within these clouds, stars are born. Gravity gathers the gas together, pulling it inward until pressure and heat ignite a new light. These stellar nurseries are veiled places, glowing softly in infrared, where hundreds or even thousands of stars may form at once. The Orion Nebula is one such nursery, visible from Earth as a hazy patch of light. Yet inside it lies an entire cradle of suns. Every star we see in the sky was once born in such a hidden place, emerging from darkness to shine for millions or billions of years. To know this is to realize that the universe is always growing, always creating. Even now, as we drift to sleep, new stars are kindling their first light. Some stars burn with a gentle glow for billions of years. Not all stars live fast or die young. Some, like our Sun, shine with a steady and patient glow, burning hydrogen slowly in their cores. These stars can endure for billions upon billions of years, giving warmth and light to the worlds that circle them. Their lives are measured not in centuries or millennia, but in ages so vast we can barely imagine them.
They rise, shine, and continue while civilizations bloom and fade on planets that may orbit quietly nearby. When you look up at the night sky, many of the stars you see are these long-lived companions of the cosmos, content to glow softly for eons. They are steady candles in a universe of change, constant enough to guide life and enduring enough to remind us that time, even on the grandest scale, can be gentle and unhurried. Some stars are stripped down to back cores of pure carbon.
When a star like our Sun dies, it sheds its outer layers and leaves behind a core, a white dwarf. Some white dwarfs are made mostly of carbon, and under the immense pressure of their own gravity, that carbon may crystallize. In other words, some stars become giant diamonds. These stellar diamonds are about the size of Earth, but far heavier. Glowing faintly with leftover heat, they no longer fuse atoms, but they still shine for billions of years before cooling to blackness. Astronomers have even detected pulsations in some white dwarfs, a kind of ringing like the sound of a struck bell. A silent, cooling jewel floating in space. Once a star, now a crystal of ancient fire. Most of the universe's history hasn't happened yet. 13.8 billion years sounds like a long time, but if you imagine the entire future of the universe, not just tomorrow or a million years from now, but trillions of years into the future, we're still near the very beginning. Stars are still forming, galaxies are still assembling. Black holes still shine with the heat of falling matter. In the far future, the stars will fade, the galaxies will drift apart, and the universe will grow cold and quiet. But that chapter hasn't begun yet. Right now, we live in a moment of light, a brief golden season when the cosmos is alive with motion and change. The past is vast, but the future is bigger still. Supernova remnants keep expanding for thousands of years. When a massive star dies, it goes out in a supernova, a brilliant explosion that can briefly outshine an entire galaxy. But the event doesn't end with a flash. The shock wave expands outward for centuries or even millennia, sweeping up gas, dust, and anything in its path. These expanding shells of debris are called supernova remnants. They glow in many wavelengths, radio, X-ray, visible light, and their patterns tell the story of the explosion. Some form delicate filaments, others turbulent clouds. The Crab Nebula is one such remnant, still spreading outward from a blast that was seen on Earth in the year 1054. Supernova remnants are the slow exhalations of dead stars still unfolding long after the light has faded. Galaxies can collide and merge into something new. Though galaxies look serene from afar, they are not still. Slowly, over billions of years, they drift together and collide. When they do, their stars rarely crash into one another. The spaces between them are too vast, but their gas and dust swirl, compressing into new bursts of star formation. Over time, two galaxies can merge into one larger system, reshaped and reborn. The Milky Way itself is on a slow collision course with our neighbor, the Andromeda Galaxy. In about 4 billion years, the two will begin to merge, creating a single new galaxy that astronomers sometimes call Milkdromeda.
From Earth, if life still watches, the night sky will blaze with streams of stars as the two galaxies intertwine. What seems calm now is part of an endless, graceful dance where galaxies meet, merge, and emerge transformed, more luminous than before. Stars often form in clusters, like families born together. When stars are born in dense clouds of gas and dust, they rarely emerge alone. Instead, they form in clusters, hundreds or thousands at a time, like families born from the same cradle. These clusters can be tight and brilliant, shining as jewels in the sky, or loose and scattered, slowly drifting apart over time. Our Sun, too, was likely born in the cluster billions of years ago, surrounded by sibling stars that have since wandered away across the galaxy. Some of those long-lost siblings may still exist, hidden among the Milky Way's billions. To think that every star has a birth family is strangely comforting. The stars we see at night are not just scattered randomly, but are the children of vast, ancient nurseries. They remind us that even in the cosmos, creation happens in gatherings where many lives begin together. Some stars travel alone across the galaxy. While many stars are born in clusters, some become wanderers. These lonely stars drift through the galaxy with no companions, expelled from their birthplaces by gravitational encounters or collisions. They are sometimes called runaway stars, traveling at astonishing speeds, flung outward by the dynamics of their crowded homes. Others may simply form in isolation, quiet and solitary, far from bustling clusters. Imagine a star alone in the vast dark, carrying its light across thousands of light years, with no close neighbors, no nearby companions, just empty space stretching in every direction. Some of these solitary stars may even host planets, tiny worlds circling in quiet solitude. Though alone, they remind us of resilience, of endurance, and of the way light continues to shine even when surrounded by silence.
The galaxy holds not only great families of stars, but also these solitary voyagers drifting endlessly.
The space between galaxies expands while light travels through it. When we observe light from distant galaxies, we're seeing it as it was long ago, but also stretched by the space it moved through. As the universe expands, so does the distance the light has to travel. And that means the light itself is stretched. Its wavelength lengthens, shifting toward the red. This is called cosmological redshift. The light isn't slowing down or losing energy by hitting things. The space it moves through is simply getting bigger. In effect, the universe stretches the signal on its way to us. When we see faraway galaxies, we're seeing more than age or distance. We're seeing how space has changed since the moment that light began its journey. A silent record of the universe's steady breathing. There are sound waves frozen into the structure of the cosmos.
In the early universe, before atoms formed and light could travel freely, matter and energy were tightly coupled in a hot plasma. In that plasma, pressure and gravity created oscillations, ripples of compression and rarefaction, like sound waves in air. These acoustic waves left an imprint in the density of matter, a kind of frozen echo. Today, we can see that echo in the distribution of galaxies, a preferred distance between galaxy pairs, like a standing wave preserved in space. This phenomenon is known as baryon acoustic oscillation. It's subtle but measurable, a fossil record of cosmic sound ringing out from a time before the universe became transparent. A wave that never fades, quietly shaping the structure of everything we see.
Galaxies can be eaten by larger ones without a trace. In the vast timescales of cosmic evolution, galaxies don't just float alone. They interact, collide, and sometimes devour each other.
When a small galaxy comes too close to a larger one, gravity can tear it apart. Its stars are pulled into long streams, absorbed into the larger galaxy's halo, and eventually blended so thoroughly that the smaller system vanishes from view. We've found remnants of such mergers around the Milky Way, stellar streams arcing through the sky, once part of other galaxies. This process is called galactic cannibalism, but it's slow and elegant, not violent, just inevitable. Over time, large galaxies grow this way, not through building, but through quiet consumption, one galaxy absorbed into another, leaving only a ripple in the stars. Neutron stars pack the mass of suns into a city-sized sphere. Imagine compressing the mass of the sun into a ball no larger than a city. That is a neutron star, one of the densest objects in existence. Inside, matter is crushed into a strange state. The protons and electrons fuse into neutrons, packed so tightly that the surface is harder than steel, and gravity is nearly unimaginable. If you could drop a pebble onto its surface, it would hit with the energy of a nuclear explosion. Yet, despite this extreme density, neutron stars are only about 20 kilometers wide, tiny on cosmic scales. They are the remains of massive stars that ended their lives in supernova blasts, leaving behind these extraordinary cores as compact spheres. Some rotate at incredible speeds, others release flashes of radiation, but all carry the legacy of stars that no longer exist. They stand as monuments to extremes, small yet unimaginably heavy, glowing quietly within the vastness of space. Quasars shine brighter than entire galaxies. Across immense distances, astronomers have discovered beacons so luminous they outshine whole galaxies.
These are quasars, powered by supermassive black holes consuming surrounding gas. As the gas spirals inward, it heats to extreme temperatures, releasing light that can travel for billions of light years. Some quasars are so far away that we observe them as they were when the universe was young, blazing like cosmic lighthouses in the early darkness. Though they are powered by destruction, they are also signs of creation, marking the growth of galaxies and the shaping of the universe itself. To see one is to peer into both power and mystery, the heart of darkness blazing with light. They remind us that the cosmos is full of contrasts. The most radiant light born from the deepest gravity wells, and brilliance shining from the very edge of nothingness. There may be more planets than stars in the universe. For a long time, astronomers could only guess how many worlds might circle other suns.
But now with telescopes able to detect even the faintest dips of starlight, we know planets are everywhere.
Almost every star seems to have at least one, and many host entire families of them. Some orbit close, some drift far, and some systems are unlike anything in our imagination. When you consider that there are hundreds of billions of stars in the Milky Way alone, and trillions of galaxies across the cosmos, it becomes likely that planets outnumber stars themselves. Each one a world with its own history, its own landscapes, its own silent orbit. The night sky above you, filled with stars, is in truth filled with more unseen planets than shining suns. Countless hidden places circling quietly in the dark. we might be living inside a giant cosmic void. The universe is filled with clusters of galaxies, and between them, enormous empty regions called voids. These voids span hundreds of millions of light years and contain very little matter.
Some researchers believe we may be inside one of these voids right now, a relatively underdense region compared to the average cosmic background. If true, it could help explain certain observations like the expansion rate of the universe or patterns in the cosmic microwave background. Living inside a void doesn't change our day-to-day life, but it means that what feels like emptiness may be part of a much larger structure. The quiet middle of a cosmic bubble gently drifting through a web of invisible gravity. Magnetars have magnetic fields trillions of times stronger than Earth's. A magnetar is a type of neutron star, a city-sized remnant of a collapsed star with an unimaginably powerful magnetic field. Earth's magnetic field is enough to guide a compass. A magnetar's field is so strong it could erase data from thousands of miles away, distort atomic structures, or tear matter apart. These fields are temporary, decaying over time, but while they last, they produce flares and bursts of high-energy radiation. A single magnetar flare, even from across the galaxy, can be detected on Earth. No lab could create such intensity. They are among the most extreme objects in the universe, dense, silent, and wrapped in invisible force like stars that have become nothing but memory and magnetism. The universe's largest known object is a giant quasar group. In 2013, astronomers discovered a vast structure made up of quasars, the luminous cores of distant active galaxies stretching over 4 billion light-years across. This structure, called a large quasar group, is so big it challenges our understanding of cosmic uniformity. According to current theory, the universe should be relatively smooth on the largest scales, with no structures exceeding a certain size. But this quasar group is larger than that theoretical limit. It's made of dozens of quasars, connected across an enormous stretch of space, suggesting that the early universe may have formed larger patterns than we once thought. Whether it's a true physical structure or a statistical fluke is still debated. Either way, it reminds us that the universe is more complex and perhaps more connected than our models can always predict. There are frozen worlds of ice and ammonia. Not all planets burn with fire. Many drift in the cold outskirts of their systems, wrapped in layers of ice. These frozen worlds may be covered with ammonia snow, methane glaciers, or icy plains stretching endlessly under dim starlight. Some may be solid spheres of frozen gas, while others conceal oceans beneath their frozen crusts. In the distant reaches of our own solar system, objects like Pluto and Triton remind us of this strange category of worlds. Cold, silent, and often tinted with colors from frozen chemicals. Though lifeless on the surface, they may still hold secrets beneath. To stand on one would be to see a sky with little light and a horizon of endless frost. They are reminders that not all planets glow with warmth. Some are places of silence where time itself seems frozen, waiting in the dark. Rogue planets drift through space without a star. Most planets orbit suns, but not all. Some are set adrift, torn away from their systems, or perhaps never bound to a star at all. These are robe planets, worlds wandering the galaxy in eternal night. Without a sun to warm them, they may still glow faintly with heat left over from their birth, or be warmed by radioactive elements within.
Imagine a world with no sunrise, no sunset, only darkness, with moons or rings circling in silence. Some might even host subsurface oceans hidden beneath thick crusts of ice, warmed only by the planet's core. To float endlessly, carrying oceans, mountains, or storms into the deep dark between stars.
That is the fate of a rogue planet. They are cosmic orphans, solitary travelers through the endless night. Some planets orbit two suns at once. In some systems, two stars circle each other, like partners in a slow dance. Around them, planets can form, locked into orbits that bring two sunrises and two sunsets each day. These are circumbinary planets, places where the sky glows with two suns. Sometimes the stars are close together, appearing as twin lights in the heavens. Other times, they drift farther apart, creating shifting patterns of warmth and shadow. The landscapes on such a world would change in rhythms we can only imagine. With skies lit by double dawns and long, complex twilights. Though once thought unlikely, astronomers have found real planets in such orbits, proving that the universe is more inventive than we guessed. To imagine standing on one is to feel like a character in a dream, a world warmed by not one, but two guiding stars. The universe may be a hologram. It sounds like science fiction, but some physicists have seriously explored the idea that our three-dimensional universe might be a projection from a deeper two-dimensional reality. This is known as the holographic principle. It comes from studies of black holes, where information about everything that falls in seems to be encoded on the surface, not the volume of the black hole itself. Some theories suggest that the universe as a whole might work the same way. What we perceive as space and depth could be a kind of mathematical illusion arising from information encoded on a distant boundary. It's not proven and probably won't affect your day-to-day life, but it's a gentle reminder that reality, even at its most solid, may not be quite what it seems. Space may be granular at the smallest scale. To the naked eye, space appears smooth. Even under a microscope, it's still empty and continuous. But some theories of quantum gravity suggest that space itself may be made of tiny, discrete units, like grains or pixels in a digital image. This smallest possible scale is called the Planck length, about 10 to the power of 35 meters. At that level, smoothness may break down into something more fundamental, a grainy, foamy texture of space-time itself. We don't yet have the tools to see it, or even to test it directly. But if it's true, then everything, stars, galaxies, thoughts, even sleep, happens not in a perfect void, but in a universe with structure all the way down. There are stars that spin faster than kitchen blenders. Some stars rotate so rapidly that their equators bulge outward and their surfaces blur into a speeding blur. Neutron stars, the dense remnants of massive stars, take this even further. A type called a millisecond pulsar can spin hundreds of times per second. That means the entire star, a city-sized sphere of nuclear matter, rotates faster than a blender blade. These objects emit beams of radiation that sweep across the sky like cosmic lighthouses, ticking with astonishing precision. Many of them are locked in tight orbits with companion stars, pulling in matter and gaining speed.
They're some of the fastest known rotators in the universe, and also some of the oldest clocks ticking silently in the night. Gravity can bend light like a lens. In the vastness of space, even light does not always travel in straight lines. Gravity, the same force that holds us to Earth, can bend the path of light as it passes near massive objects. This effect, predicted by Einstein, is called gravitational lensing. When light from a distant galaxy or star passes by something heavy, like a toaster of galaxies or a black hole, its path curves as though it had passed through a giant cosmic lens. To us, the image may appear stretched, doubled, or magnified, revealing details we could not otherwise see.
The universe in this way helps us look deeper into itself, bending and magnifying its own light. It is a quiet trick of nature showing that space is not empty, but flexible, and that gravity can shape even the most intangible thing, the light of the stars themselves. Distant galaxies appear multiple times in the sky because of it. Sometimes, when we gaze deep into the universe with our telescopes, we see something curious. The same galaxy appearing in several places at once. This strange vision is caused by gravitational lensing, where the gravity of a massive object bends light around itself like glass bending a reflection. To us, it can make one distant galaxy look like 2, 3, or even 4 separate images, shimmering around the edge of the lensing mass. These cosmic mirages not only dazzle the imagination, but also allow astronomers to study galaxies too faint to otherwise detect, magnified by the bending of space itself.
To think that we can see echoes of the same galaxies scattered across the sky is to realize how strange the fabric of reality truly is. The cosmos, through gravity, paints illusions that reveal deeper truths. Time passes differently in strong gravity. Time, which we often think of as steady and constant, can flow at different speeds depending on where you are. In regions of strong gravity, like near a massive planet, star, or black hole, time slows down compared to places with weaker gravity. This is not just theory. It has been measured with delicate instruments, even between clocks on mountaintops and clocks at sea level. In space, near the densest objects, the effect becomes extreme. To an outside observer, everything near a black hole seems to slow, as though caught in a never-ending pause. Yet to the one experiencing it, time feels normal. This bending of time is part of the deep connection between gravity and the fabric of the universe. It reminds us that reality itself is flexible, and that time is not the same everywhere, but is woven into space like a living thread. Astronomers once mistook quasars for nearby stars. When quasars were first discovered, they looked like faint, point-like objects, almost identical to ordinary stars. But their light didn't behave the way it should. Their spectra were strange, and their brightness varied in puzzling ways. It took years to realize that these weren't stars at all. They were distant galaxies with incredibly active centers. A quasar is powered by a supermassive black hole surrounded by a swirling disk of hot, falling gas. That gas heats up and glows with unbelievable intensity, sometimes outshining the rest of the galaxy combined. The first quasars were so far away that their light had traveled billions of years to reach us, and yet they looked like tiny stars. A case of mistaken identity that turned out to be one of the brightest discoveries in astronomy. Our local group of galaxies is falling toward a hidden region. The Milky Way doesn't sit still. Along with the Andromeda Galaxy and dozens of smaller companions, it drifts through space as part of a loose collection called the local group. And this group, in turn, is moving towards something larger, a gravitational anomaly called
the Great Attractor. But beyond even that lies a more mysterious region, the Shapley supercluster, and perhaps others still hidden by the dense plane of our galaxy. These distant masses exert a pull we can measure, even though we can't yet see all of them. It's as if our entire neighborhood is sliding towards something enormous, wrapped in shadows. We don't know what lies in that direction, only that we're moving toward it slowly, pulled by the weight of unseen giants. We are living in the universe's stellar springtime. Right now, the universe is filled with stars, burning, forming, exploding. But this is a relatively recent development.
For the first few 100 million years after the Big Bang, there were no stars at all. The first ones formed in darkness, lit up their surroundings, and began the process of cosmic evolution. Since then, star formation has risen, peaked, and slowly declined. We now live in what might be called a cosmic spring, a time when new stars still form, but less than before, and much more than will come in the far future. One day, the last stars will be born, and after that, the universe will slowly darken. But for now, it is still alight with new beginnings, bright enough to wonder, quiet enough to rest. There are galaxies that shine in radio waves like celestial beacons. Some galaxies do not glow brightly in visible light, but instead shine fiercely in radio waves. These are often powered by supermassive black holes at their centers, driving jets that extend for thousands of light years. Through radio telescopes, they appear as enormous, ghostly structures, far larger than the galaxies themselves. To human eyes, they may look dim, but in radio frequencies, they blaze like beacons. Radio galaxies allow astronomers to trace magnetic fields, energetic particles, and the activity of black holes across cosmic distances. They are reminders that the universe speaks in many voices, from visible light to invisible waves. By tuning into these hidden channels, we hear stories otherwise lost in silence. They are proof that the cosmos is not dark, but full of signals calling out across the void in ways our eyes alone can never see. The universe is filled with invisible neutrinos streaming through us. Every second, trillions of particles called neutrinos pass through your body, through the Earth, and out the other side. They are nearly massless, ghostly travelers that interact so rarely with matter that they slip through planets and stars as though nothing is there. Neutrinos are created in nuclear reactions, in the heart of the Sun, in exploding stars, and even in the Big Bang itself. For decades, they were thought to be massless, but now we know they carry the faintest weight, enough to influence the universe's evolution. To detect them requires enormous underground detectors, filled with pure water or heavy metals, waiting for the rarest of collisions. Yet, whether we detect them or not, they are always here, streaming invisibly around us, through us, within us. The universe is not empty. It is alive with ghostly rivers of neutrinos. Cosmic rays from distant explosions strike Earth constantly. From the farthest reaches of the cosmos, high-energy particles race through space at nearly the speed of light. These are cosmic rays, born in supernova, black hole jets, and other violent events. They flare for millions or billions of years before reaching Earth, where they strike our atmosphere in constant showers. Most are harmless, their energy absorbed before they reach the ground.
but their presence is a reminder that the universe is always in motion, always sending whispers of distant violence across the void. Sometimes, the highest energy cosmic rays carry more punch than any particle we can create in human laboratories. A staggering force delivered by nature alone. Even as we rest beneath the quiet night sky, we are surrounded by these ancient travelers, cosmic messengers carrying stories of explosions that occurred long before Earth existed. Faraway galaxies shine with light that departed them before our planet was formed. When you look at a galaxy several billion light-years away, you are not only seeing distance, you are seeing time. The light from that galaxy began its journey long before Earth came into being, before the Sun was born, before our solar system had even started to form. Some of the galaxies we observe today released their light more than 10 billion years ago. That glow moved through expanding space, stretching and reddening along the way, until it finally reached our telescopes. In this way, we are watching the universe's deep past unfold in real time. The stars we see in those galaxies may no longer exist. Their light persists, a gentle reminder that the night sky holds stories far older than Earth itself. Entire galaxies can disappear behind vast clouds of dust. Even something as enormous as a galaxy can be hidden by dust. In some regions of space, thick clouds of interstellar dust obscure the light behind them. This dust isn't like the kind you find on a bookshelf. It's made of tiny grains of carbon and silicates drifting through cold, molecular clouds. When a galaxy lies behind one of these clouds, much of its light can be blocked in visible wavelengths. We only see it when we look with special instruments in infrared, radio, or X-ray light, which can slip through the dust more easily. Astronomers have discovered entire galaxies this way, lurking behind what once seemed like empty sky. Even in space, appearances can be deceiving. Darkness doesn't always mean absence. Sometimes, it just means waiting to be seen in the right light. Some galaxies are surrounded by perfect circles of lensed light. Sometimes the gravity of a galaxy bends the light from something even farther away. If the alignment is just right, this bending creates a phenomenon called an Einstein ring, a perfect circle of distorted light. It's a form of gravitational lensing, where the mass of the foreground galaxy curves space-time, acting like a lens for background light. Einstein rings are rare, but beautiful glowing loops suspended in space, formed not by motion, but by perspective and gravity. The light can come from a distant galaxy, a quasar, or even a supernova. These rings help astronomers measure the mass of galaxies, map dark matter, and study the early universe. They are silent, perfect illusions, natural lenses created by the shape of space itself. Matter and antimatter once battled for balance. In the young universe, energy condensed into particles of matter and their opposites, antimatter. Whenever the two met, they annihilated, leaving behind pure light. For reasons still mysterious, there was a slight imbalance. Just enough matter was left over after the battles to form the stars, galaxies, and planets we see today. Without that tiny excess, the universe would have been filled only with radiation, with no worlds, no atoms, no life. The symmetry of matter and antimatter was nearly perfect. Yet it was the tiniest imperfection that allowed everything we know to exist. Scientists still search for answers to why the balance tipped, but to us, it is enough to know that the cosmos itself arose from this fragile difference, a faint bias toward matter that became mountains, oceans, and our own bodies. Existence is the echo of that ancient battle. The universe glowed like a brilliant fireball in its youth. Hundreds of thousands of years after the Big Bang, the universe was still a searing plasma of particles and light. It glowed everywhere, brilliant and uniform, like an immense fireball without edges. The photons within it scattered endlessly, bouncing from particle to particle, unable to travel far. To an observer, then there would be no stars, no galaxies, only an endless bright fog. Slowly, as the cosmos expanded and cooled, atoms began to form and the fog lifted. Light could finally move freely, beginning its long journey outward. That ancient glow still exists as the cosmic microwave background stretched into faint microwaves after billions of years. To remember that the universe was once a glowing sea is to see it not only as dark and starry, but also as something that once shone everywhere, a cosmic dawn before the first stars were ever born. Galaxies formed from tiny ripples in that early glow. The first structures in the universe began as the faintest ripples in the sea of early light. These tiny variations in density, born from quantum fluctuations, grew slowly over time as gravity pulled matter together. Where the glow was slightly denser, galaxies would eventually form. Where it was emptier, cosmic voids would stretch. In this way, the vast web of galaxies we see today traces back to the smallest of ripples written into the afterglow of the Big Bang. Astronomers have mapped these patterns with satellites, finding the seeds of everything in delicate variations just a fraction of a degree warmer or cooler. It is humbling to think that the spiral arms of galaxies, the stars overhead, and even our own Milky Way all grew from those first subtle patterns. From whispers in the light, entire universes of form and beauty arose. The vacuum of space has quantum pressure. Even in perfect vacuum, where there are no atoms, no particles, no radiation, there's still energy. Quantum physics tells us that empty space isn't truly empty. Instead, it's filled with tiny, restless fluctuations. Particles and antiparticles appearing and disappearing. Fields shifting slightly, always moving. This activity creates pressure known as vacuum energy. On large scales, this pressure may help explain dark energy, the force driving the universe's accelerating expansion. Unlike other kinds of energy, vacuum energy doesn't dilute as space grows. It stays constant, stretching space faster the more there is of it. It's a strange thought, but the more nothing you have, the more something it becomes. The quiet force of empty space may be what drives the cosmos apart. Black holes radiate faint heat over trillions of years. Black holes are famously dark, so dense that nothing, not even light, can escape their gravity. But thanks to physicist Stephen Hawking, we know they aren't completely silent. According to quantum theory, black holes can emit a faint glow called Hawking radiation. It happens at the edge of the event horizon, where virtual particle pairs occasionally result in one particle escaping while the other falls in. The escaping particle becomes real, a tiny bit of energy lost from the black hole. Over incredibly long timescales, this slow leakage can cause the black hole to shrink and eventually evaporate completely. For a black hole the mass of the Sun, that process would take more than 1 trillion years. It's the quietest kind of ending. Not an explosion, but a long, slow fade into nothing. The universe contains more plasma than solid matter. When we think of matter, we usually imagine solids, liquids, and gases. But the most common state of matter in the universe is something else entirely: plasma.
Plasma is an ionized gas, a cloud of particles where electrons and nuclei move freely. It's found in stars, in the solar wind, in interstellar space, and even in the vast regions between galaxies. Most of the visible matter in the universe is in this state. Plasma behaves differently from other forms of matter. It responds to magnetic fields, flows like fluid, and can carry electrical currents across enormous distances. On Earth, we rarely see it outside of lightning, fire, or neon lights. But in space, plasma is everywhere, glowing, flowing, and shaping much of what we see, even when we don't realize it. Without supernova, planets like Earth could not exist. The explosion of a supernova is both an ending and a beginning. In its final breath, a massive star scatters the elements it forged across light years, seeding space with carbon, silicon, oxygen, and iron. Without these gifts, there could be no rocky planets, no oceans, no living beings.
Earth itself is built from the ashes of stars that lived and died long before. Our very planet is a mosaic of ancient starlight reassembled into continents, mountains, and seas. Every rock, every tree, every heartbeat carries within it the legacy of explosions that tall stars apart. To know this is to understand that destruction in the cosmos is not only loss, but creation. Out of the death of stars comes the possibility of new worlds. Earth is proof. A planet formed from stardust carrying life in the wake of stellar sacrifice. Even now, new stars continue to shape the universe. Though billions of years have passed since the first stars lit the cosmos, the universe is still creating. In vast clouds of gas, stars continue to form, igniting their fires and beginning their long journeys through time. Each newborn star shapes its surroundings, carving bubbles in the gas, sending out winds, and sometimes giving rise to new planets.
The process is slow but unending, a quiet heartbeat of creation woven into the fabric of the universe. In places like the Orion Nebula, we can see this happening even now. Nurseries where countless suns are being born. To realize that the universe is not finished, but still unfolding, is a comfort. Creation is not a single event in the past, but an ongoing story. As you drift to sleep, stars are kindling across the galaxy, adding their light to the eternal sky. Some black holes may be primordial, born in the early universe. Not all black holes may come from dying stars. Some scientists believe that moments after the Big Bang, when the universe was still dense and chaotic, regions of space could have collapsed directly into black holes. These are called primordial black holes, and if they exist, they could range from the size of mountains to objects as heavy as whole planets. Some may have evaporated long ago, while others could still drift unseen, hidden among the stars. They may even account for some of the mysterious dark matter that shapes galaxies. Though we have yet to find them, the idea is haunting that scattered across the cosmos, there may be ancient black holes older than any star, relics from the very first heartbeat of time. Silent, invisible, and mysterious, they would be fossils of the universe itself, holding secrets from its earliest moments. Some black holes launch jets thousands of light years long. At the hearts of galaxies, supermassive black holes sometimes feed on gas and dust, spiraling inward. But instead of swallowing it all, they can launch colossal jets of energy outward,
stretching for thousands of light years. These jets, made of charged particles traveling near the speed of light, shine brightly in radio waves and can sculpt the very shape of their host galaxies. From Earth, we see them as ghostly streams glowing across the darkness, marking the places where black holes feed.
The power involved is beyond comprehension.
The energy of entire stars funneled into narrow beams that pierce the cosmos. Yet in their violence, these jets also nurture creation, compressing gas and sparking new bursts of star formation. They are a reminder that black holes are not only destroyers, but also shapers, sculpting galaxies with both gravity and light. Entire galaxies can be stripped of their gas by neighbors in crowded regions of the universe. Galaxies do not always drift peacefully. As they move through clusters filled with hot plasma or pass close to larger companions, their reservoirs of gas can be stripped away. This process, called ram pressure stripping, leaves galaxies barren, unable to form new stars. What remains is a silent collection of aging suns, slowly fading. Astronomers sometimes call these quenched galaxies, star cities cut off from the very fuel that once gave them light. To see them is to glimpse the quiet consequences of cosmic interaction.
Beauty turned stillness.
Yet even in this stripping, there is motion and balance as gas flows into other regions, feeding new creations elsewhere. Galaxies, like living things, are shaped by their environments, nurtured or diminished by the forces around them. The universe is never static. It is always reshaping itself, sometimes gently, sometimes with great force. There are stars that suddenly blink out and reappear. Most stars shine steadily, their light constant across years and centuries. But some behave strangely, fading away and then returning without warning. Astronomers have observed stars that dim so drastically they seem to vanish, only to brighten again later. Some may be hidden by passing clouds of dust, others by the strange dynamics of collapsing matter. A few may represent events we still cannot fully explain. One famous example, known as Tabis star, baffled scientists with irregular dips in brightness that seemed too complex for planets alone to cause.
These blinking stars remind us that even something as familiar as starlight can hold surprises. They are quiet enigmas shimmering in and out of view like cosmic lanterns behind shifting veils. Each flicker is a question, a reminder that the universe still holds secrets even in the lights we have watched for centuries. Some galaxies are so faint they are almost invisible. Not all galaxies glow brightly. Some are so diffuse their stars spread thin across vast regions that they are nearly invisible against the night sky. These ultra-diffused galaxies can be as large as the Milky Way, yet contain only a fraction of its stars. To even requires sensitive instruments carefully tuned to pick out faint smudges of light from the darkness. Their existence challenges our understanding of how galaxies form and survive. Some seem to float quietly in space, while others live in crowded clusters, surviving despite their fragile appearance. They remind us that the universe is filled not only with brilliant spirals and dazzling ellipticals, but also with ghostly forms, barely there, delicate and strange. To know they exist is to imagine galaxies like wisps of smoke drifting across the cosmos, almost unseen, yet still part of the grand tapestry of creation. There are galaxies are so dense they contain trillions of stars. Some galaxies are so crowded with stars that they contain trillions within their boundaries. These giant ellipticals are among the largest structures in the universe, glowing with the combined light of countless suns.
They are often found at the centers of galaxy clusters, where they dominate their surroundings with their sheer mass. Their light is soft and diffuse, yet immense, like a glowing ball of starlight stretching across space. Within them, stars move in all directions, a chaotic sea without the graceful spirals we see in galaxies like our own.
They are cosmic metropolises, star cities on a scale difficult to imagine. To gaze upon one is to see not just a galaxy, but a universe within a universe, packed with light and life. A radiant monument to the slow, patient growth of the cosmos over billions of years. Gamma ray bursts can release more energy than the sun will in its lifetime. Among the most powerful events in the universe are gamma ray bursts, sudden flashes of high-energy radiation that can outshine entire galaxies for moments at a time. They are thought to occur when massive stars collapse into black holes or when neutron stars collide. In seconds, they release more energy than our sun will in 10 billion years of steady burning. From Earth, they appear as brief bursts lasting only seconds or minutes, but their brilliance travels across billions of light years. Though dangerous up close, they are far enough away that we only catch their echoes, brief whispers of unimaginable violence.
They remind us that the universe, while often calm and quiet, also carries moments of staggering intensity. A single burst, unseen by our eyes but recorded by telescopes, tells of distant destruction, carrying the raw power of stars tearing themselves apart. Magnetars hold the strongest magnetic fields known. Neutron stars are already extreme, but a rare few are stranger still. These are magnetars, stars with magnetic fields trillions of times stronger than Earth's. Their fields are so intense they could strip information from a credit card from thousands of kilometers away. On their surfaces, crusts crack and shift, releasing bursts of X-rays and gamma rays. Though only a few dozen have been found, they are among the most powerful objects in existence. Tiny spheres just a few kilometers wide, yet holding more energy than entire planets. Magnetars are fleeting in cosmic terms, their intense fields fading after tens of thousands of years.
Still, during their brief lives, they shape their surroundings in ways we can barely imagine. They are the universe's magnets, strange and fearsome, showing us that even among stars, there are extremes beyond comprehension. Gravitational waves ripple through space from colliding black holes. When black holes or neutron stars collide, they send ripples through the fabric of space itself. These are gravitational waves, first predicted by Einstein and confirmed only recently by detectors on Earth. Like ripples on a pond, they spread outward, carrying information about the cataclysm that created them. For a fraction of a second, the detectors stretch and squeeze by distances smaller than an atom, recording the faintest whispers of cosmic collisions. Each wave tells us about the masses involved, their spins, and their fates. To think that space itself can ripple and that we can feel those ripples across billions of light years is astonishing.
It is as though the universe has a voice, speaking in vibrations too subtle for us to hear, but strong enough to be measured. Through them, we listen to the deep music of the cosmos. Space itself can stretch and shrink with these ripples. Gravitational waves are not just disturbances moving through space. They are stretches and squeezes of space itself. As a wave passes, distances briefly change, expanding in one direction while contracting in another. Though the effect is incredibly small, it carries the story of some of the universe's most dramatic events. When two black holes spiral together, the waves they send out alter the very fabric of reality. On Earth, these ripples are so faint
we would never notice them in daily life. But with sensitive detectors, we can measure the tiniest shifts in length. Each detection is like catching the echo of a collision across unimaginable distances.
To imagine space itself stretching and shrinking is to realize that reality is more fluid than solid. The cosmos is not just a stage on which events unfold. It is part of the performance itself. Earth orbits a modest star in the spiral arm of the Milky Way. A home planet circles a star that is neither the brightest nor the largest, but steady, calm, and longeved. The Sun is a middle-aged, medium-sized star, resting quietly in one of the Milky Way's spiral arms, the Orion arm, a minor branch compared to the galaxy's grander spirals. From here, we orbit at just the right distance for life to flourish, far from the crowded and dangerous galactic center, yet close enough to see the glow of our neighbors in the night sky. Our position gives us a peaceful vantage point, surrounded by open space, but not too isolated. To think of it is to realize how fortunate Earth is, a small world orbiting a modest star tucked away in a quiet corner of a galaxy with hundreds of billions of suns.
Humble, fragile, and yet just right for us to call home. Our galaxy is part of a small group called the Local Group. The Milky Way is vast, but it is not alone. It belongs to a collection of more than 50 galaxies, bound together by gravity, known as the Local Group. Our closest large neighbor is the Andromeda Galaxy, a spiral even bigger than ours. Slowly moving toward us in a dance that will one day bring the two together, scattered around are smaller galaxies, companions like the Melanic clouds visible from the southern hemisphere, or tiny dwarf galaxies orbiting quietly nearby. Together, these galaxies form a kind of family, drifting through the larger cosmos as a unit. Though the Local Group is only a tiny fraction of the universe, it is our immediate neighborhood in the stars. To imagine it is to picture a cluster of glowing islands floating together in the great ocean of space, companions on a shared journey through the dark.
That group orbits within the vast Virgo supercluster.
Beyond our Local Group lies something far larger, the Virgo supercluster, a sprawling collection of thousands of galaxies spread across hundreds of millions of light years. Within it, galaxies are not randomly scattered, but gathered into clusters, each bound by gravity, into enormous cosmic cities. The Local Group is just one tiny suburb in this grand expanse, circling quietly at the edge. At the heart of the Virgo supercluster lies the Virgo cluster itself, a dense swarm of galaxies, glowing like a cluster of jewels in the night. To us on Earth, these galaxies appear as faint smudges in the telescope, but in truth, they are entire universes of stars. To know we belong to such a supercluster is to see how connected all things are. Our galaxy is not adrift alone, but part of an immense cosmic structure, a vast community of light. Even that supercluster is only one thread in the cosmic web.
As immense as the Virgo supercluster is, it is still only part of something even greater. Across billions of light years, galaxies and clusters gather into filaments, vast threads of matter, forming a structure called the cosmic web. These filaments stretch and weave together, separated by enormous voids almost empty of galaxies. When mapped in 3 dimensions, the universe looks less like a scattered spray of stars and more like a living network. Glowing strands crossing the dark. Our supercluster is only one thread in this cosmic tapestry, connected to others like fibers in a web too large to comprehend. To imagine it is to think of the universe as not only vast, but beautifully organized on the grandest scale.
We are part of a web that stretches across all space, a quiet reminder that nothing exists in isolation. Everything is connected. We see galaxies gathered into clusters like pearls on a string. Galaxies rarely exist completely alone.
Gravity pulls them together into groups and clusters, bound into great families that can contain hundreds or even thousands of galaxies. When we look deep into space, we often see them strung along in long chains, aligned like pearls on an invisible string. These alignments trace the filaments of the cosmic web, showing the scaffolding of the universe itself. Each galaxy in a cluster carries its own billions of stars, yet together they move in harmony, orbiting their shared center of gravity. Sometimes clusters collide, merging into even larger collections. Other times they quietly glide in place, glowing gently against the dark. To see galaxies gathered in this way is to glimpse the underlying patterns of creation. The universe arranges itself with an elegance we are only beginning to understand, building structures larger than imagination can hold. The cosmic web stretches across billions of light years.
When astronomers map the positions of galaxies across the sky, a picture emerges. A vast web spanning the observable universe. The cosmic web stretches for billions of light years, its filaments filled with galaxies and clusters, while enormous voids lie in between. It is the largest structure we know of, a map of how matter has flowed since the dawn of time. Each filament is like a highway of galaxies drawn together by the gravity of dark matter, glowing faintly in the darkness. From our tiny place inside it, we can only see pieces of this grand design, but computer simulations reveal its breathtaking scale. To imagine the cosmic web is to picture a universe alive with threads of light woven across unfathomable distances. It is both delicate and immense, a structure so vast that even billions of years of light cannot capture it all. Most of the universe is empty, vast beyond imagination. For all its galaxies, stars, and planets, the universe is mostly empty space. Between galaxies stretch voids so large that a beam of light could travel for hundreds of millions of years without encountering a single star. Even within galaxies, the distances between stars are immense, with more emptiness than matter. Yet this emptiness is not nothing. It is the canvas upon which the cosmos is painted, the stage where the drama of stars and galaxies unfolds. To us, the universe feels crowded with stars, but in truth, they are scattered thinly across incomprehensible distances. This emptiness is what allows galaxies to drift, expand, and evolve. And without it, the universe could not exist as it does. To contemplate such vast silence is to feel both small and comforted. There is so much space. And yet, here we are, a quiet spark within it. Yet everywhere we look, we find patterns of structure. Though the universe is mostly empty, it is not random. From the smallest scales to the largest, structure emerges. Stars gather into galaxies. Galaxies gather into clusters. Clusters stretch into filaments of the cosmic web. Even the ripples left in the glow of the Big Bang reveal patterns that seeded all later creation. This order arises naturally from gravity and motion, shaping the universe into a balanced whole. To us, it appears as beauty spirals, clusters, threads, and voids, patterns repeated across vast scales. Everywhere we look, we find symmetry and rhythm, echoes of creation woven into the fabric of space. To realize this,
is to see the universe not as chaos, but as a living design, its structures both grand and delicate. We are part of that pattern, a tiny filament of life woven into the cosmos, endless weave. The universe has no center. It expands everywhere at once. It is tempting to imagine the universe as a balloon expanding outward from a central point. But in reality, there is no center.
The expansion happens everywhere at once, like the surface of the balloon itself, stretching with every point moving away from every other. To an observer in any galaxy, the universe would appear to expand around them, with distant galaxies rushing away in all directions. There is no single place where it all began, no edge from which it spreads. Instead, space itself grows, carrying galaxies with it. This can be hard to grasp, yet it is one of the most beautiful truths of cosmology. The universe has no favored location, no privileged center. Every point takes part in the expansion, equally central, equally immense. To exist in such a universe is not to belong to an edge, but to the whole. Every galaxy is moving away from us as space expands. When astronomers analyze the light from distant galaxies, they see it stretched and shifted toward red, a signal that those galaxies are receding. The more distant a galaxy is, the faster it appears to move away, carried outward by the expansion of space itself. From our perspective, it feels as though everything is rushing outward. Yet to an observer in another galaxy, the same pattern would appear. All galaxies see others moving away from them. This realization, first uncovered in the early 20th century, revealed that the universe is not fixed and still, but active and evolving, filled with motion. It also means that long after we are gone, the night sky will continue to change, with distant galaxies slowly slipping beyond view as expansion carries them away. To understand this is to sense both the transience and the magnificence of existence. The universe is never still, always expanding, a vast river of galaxies flowing endlessly outward. Some stars are so cool they barely glow red. Not all stars blaze brightly in the sky. Some are so cool and faint that their light is barely visible. These stars, often called red dwarfs, glow with a deep crimson hue. Their heat so low, they simmer rather than burn. Many are smaller than half the size of the sun. Their light, dim and steady, like embers that never quite go out. Though they may be faint, they are the most common stars in the galaxy, numbering in the hundreds of billions. Some live for trillions of years, far longer than the universe has existed so far. Around them, planets may circle quietly, warmed by the faintest glow. These tiny, cool suns are the quiet keepers of the cosmos, enduring when brighter stars fade away. A reminder that sometimes the smallest lights are the ones that last the longest. Others burn so hot they shine blue-white. At the opposite extreme are the hottest stars of all, massive suns that shine in fierce shades of blue-white. The temperatures can reach tens of thousands of degrees, blazing with energy so intense it bathes their surroundings in ultraviolet light. These stars are short-lived, burning through their fuel in only a few million years. But while they live, they dominate their regions of space. Their light sculpts nearby gas clouds into glowing nebula, sparking new generations of stars. They are rare, outnumbered by smaller suns, yet their brilliance ensures they stand out in the night sky. To imagine one is to picture a furnace brighter than 1,000 suns, hot enough to melt anything we know, radiating with impossible intensity. Though fading,
Their beauty is unmatched, and their brief lives leave behind legacies of new stars, new elements, and new wonders. Brown dwarfs bridge the gap between planets and stars. There are objects in the universe that are neither fully stars nor fully planets. These are brown dwarfs, often called failed stars. They form like stars collapsing from clouds of gas, but they never grow massive enough to ignite sustained nuclear fusion in their cores. Instead, they glow faintly with leftover heat, sometimes giving off only a dim red or infrared glow. Some are large enough to resemble small stars, while others are barely bigger than giant planets like Jupiter. They drift quietly through space, often invisible without special telescopes. Though they lack the brilliance of true stars, they are fascinating in their own right, a hidden population between categories, reminding us that the universe does not always follow simple boundaries. To imagine a brown dwarf is to picture a ghostly ember glowing softly in the dark. Neither star nor planet, but something in between. Some white dwarfs will crystallize into cosmic diamonds. When stars like our Sun reach the end of their lives, they shed their outer layers and leave behind dense cores called white dwarfs. These remnants, no larger than Earth, glow faintly as they slowly cool. Over billions of years, their matter may crystallize, forming enormous spheres of carbon and oxygen arranged like a diamond lattice. In time, they will become cosmic gems, stars transformed into giant diamonds drifting in the galaxy. Astronomers believe some white dwarfs we see today are already beginning this process, their cores hardening into crystalline form. To think of such a thing is breathtaking. Stars that once blazed brightly, ending not in fire, but in quiet transformation, leaving behind the largest diamonds the universe could ever create. Silent, eternal, and glittering invisibly in the dark. They are reminders of beauty hidden even in stellar death. Others will one day fade into black embers. White dwarfs do not shine forever. After trillions of years, as they lose their heat, they will grow colder and dimmer, until at last they no longer glow at all. These hypothetical remnants are called black dwarfs, stars that have faded into darkness, embers cooled beyond visibility. None yet exist because the universe is not old enough. Even the oldest white dwarfs still shine faintly, their warmth slowly ebbing. But given enough time, the galaxy will one day be filled with these silent, darkened stars, relics of suns that once gave light and life. It is a haunting vision, a cosmos where the lights go out one by one until only cold embers remain. Yet it also speaks to the deep patience of the universe. Even stars must rest eventually, fading gently into sleep after eons of shining. Hypergiant stars can shed entire shells of gas. Some of the most massive stars in the universe are unstable giants, their atmospheres so swollen and turbulent that they shed layers of gas into space. These hypergiants can lose as much mass in a year as our Sun will in its entire lifetime, throwing off shells of glowing material that expand outward like halos. Over thousands of years, these shells form intricate nebulae, glowing in the starlight as cosmic sculptures. The star itself continues burning fiercely, destined for a spectacular end as a supernova. Hypergiants live fast and end violently, but their eruptions help enrich the galaxy with elements that will form future stars and planets. To see one is to witness both beauty and fragility. A colossal star trembling on the edge of collapse, surrounding itself with veils of gas, leaving luminous reminders of its turbulent existence. Collapsing stars can form black holes in seconds. When the most massive stars run out of fuel, their cores collapse under the crushing force of gravity. In just seconds, the matter inside shrinks to an impossibly dense point, creating a black hole. The outer layers of the star explode outward in a supernova, scattering elements across space, while the core vanishes behind an event horizon. The speed and violence of this process is staggering.
A star that shone for millions of years, ending in a collapse that happens almost instantly. To imagine it is to picture an enormous sun folding in on itself, its light extinguished in a heartbeat, leaving behind a shadow in space. These events are rare to witness, but their consequences shape the galaxy, creating black holes that can grow, merge, and influence everything around them. Even in destruction, they are creators, opening doors to new mysteries. Some black holes consume entire stars whole. Every so often, a star wanders too close to a black hole. When it does, the black hole's gravity stretches and pulls it apart in a process called spaghettification. The star is shredded, its gas forming a glowing disk as it spirals inward, heating to millions of degrees before vanishing into the black hole. These violent meals can outshine galaxies for brief periods, as the infilling matter releases enormous energy. From afar, we see them as sudden flares of light, the signatures of stars being devoured. For the black hole, it is simply growth, feeding on what chance has brought too near. Though terrifying in scale, these events are also part of the balance of the cosmos, reminders that nothing is permanent and that even stars can be undone by the gravity wells lurking silently in the dark. Others quietly sip gas from their surroundings. Not all black holes are dramatic in their feeding. Many grow slowly, drawing in thin streams of gas from their surroundings. As the gas swells inward, it heats and glows faintly, but without the enormous flares of more violent meals. These black holes are quiet, hidden in the dark, revealed only by their subtle effects on nearby stars, or by the faint X-rays of their glowing disks. In some galaxies, countless black holes sip gently on interstellar gas, growing steadily over billions of years. Though less spectacular than star-devouring events, this quiet feeding may be far more common. It paints a picture of the universe not only filled with sudden violence, but also with slow, patient processes unfolding invisibly. These silent black holes remind us that growth takes many forms, sometimes a sudden flare and sometimes a slow sip across eternity. There may be black holes wandering the galaxy unseen. Most black holes remain hidden without bright disks of gas or dramatic eruptions to reveal them. Some may drift alone through the galaxy, remnants of ancient stars wandering invisibly through space. Astronomers believe there could be millions of these rogue black holes in the Milky Way, passing silently between the stars. We cannot see them directly, but we may detect them when their gravity bends starlight or nudges nearby stars in their paths. To imagine them is to picture shadows roaming the galaxy, unseen and silent, yet present. They are reminders that the universe holds far more than meets the eye. For every brilliant star we see in the sky, there may be countless invisible companions traveling endlessly in the dark. These hidden wanderers remind us that space is filled not only with light, but also with mysteries that quietly drift beyond sight. The cosmos will continue expanding for billions of years. The universe is not still. It stretches slowly, gently, carrying galaxies farther apart with every passing moment. This expansion began with the Big Bang and shows no sign of stopping. For billions of years to come, space will continue to grow and galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion,
always spreading wider. Though invisible to our senses, this expansion is constant, a background rhythm of the cosmos itself. To imagine it is to picture all of space breathing outward, forever stretching into the unknown.
We live in a universe that is not fixed but alive with change. Its future already unfolding in the silent pole of dark energy. Even as we rest tonight, the cosmos grows larger, and the distances between galaxies stretch ever further into infinity. Distant galaxies will drift beyond our sight. As the universe expands, more and more galaxies will slip away. Beyond a certain distance, their light can no longer reach us, carried away faster than the speed of light by the stretching of space itself. In billions of years, the night sky will grow emptier, as only the closest galaxies remain visible. Eventually, future observers may see only the stars of the Milky Way and its merged descendants, unaware of the larger universe beyond. The cosmos will appear smaller, not because it has shrunk, but because its light has been carried away. We live in a fortunate time when telescopes can still gloat billions of galaxies across the sky. To imagine them fading from view is bittersweet, a reminder that the universe is not only vast, but changing, and that the vision we hold today is a fleeting gift of cosmic history. Stars will burn out, leaving darkness. Though stars feel eternal, each has a lifespan. In billions or trillions of years, they will exhaust their fuel and fade. The largest stars will collapse into black holes or neutron stars. Smaller ones, like red dwarfs, will simmer slowly before fading into faint white dwarfs. Over unimaginable stretches of time, the galaxy's stars will go out one by one until only embers remain. The night sky, once alive with light, will darken into silence. Yet even in this fading, there is beauty. The elements forged in stars will remain, drifting in space, carrying the legacy of light long after it is dimmed. To think of it is to realize that nothing, not even starlight, lasts forever. But like a candle at the end of its flame, the stars will leave behind a memory of brilliance, a story of creation written into every atom. White dwarfs will slowly cool to nothing. When stars like the sun end their lives, they leave behind white dwarfs, small, dense remnants glowing faintly with heat. For billions of years, these stars will shine softly, cooling slowly as their warmth fades. Eventually, after unimaginable spans of time, they will radiate no light at all. These invisible corpses are called black dwarfs, stars that have grown cold, silent, and dark. None exist yet because the universe is still too young. But in the far future, when enough time has passed, the cosmos may be filled with them. Quiet embers scattered through the void. They will be reminders of a time when stars once filled the skies, glowing across galaxies. To picture a universe of black dwarfs is to imagine silence, an end not in fire or violence, but in stillness, as light itself slips into memory. Black holes will evaporate over trillions of years. Even black holes, the darkest and most enduring objects we know, will not last forever. Through a process called Hawking radiation, they slowly lose energy, emitting faint particles as they shrink. Over trillions upon trillions of years, even the largest black holes would evaporate, vanishing in a final burst of light. This process is so slow that none have yet begun to fade. But in the far future, long after stars have gone dark,
Black holes will be the last luminous events in the cosmos. To imagine them evaporating is to picture the universe slowly emptying, its most powerful engines dissolving into nothing. What remains is silence, a cosmos without stars, without galaxies, only faint whispers of energy fading into the dark. It is a reminder that even the most enduring giants of space are not eternal, but subject to time itself. Even protons may one day decay.
The matter that makes up our world feels permanent, as though atoms will last forever.
Yet some theories suggest that even protons, the building blocks of atoms, may eventually decay. If so, then after unimaginable spans of time, every atom in the universe would slowly dissolve, leaving nothing but radiation behind. This would mean not only stars and galaxies would vanish, but matter itself would fade into energy. No mountains, no oceans, no planets, only a thin mist of particles spread across endless space. Though this idea is not yet certain, it is a haunting vision of impermanence. Even the most solid stone may one day vanish, not in moments, but in ages so long they dwarf the history of the cosmos. To rest beneath the stars is to hold on to the fleeting gift of matter itself, fragile and temporary. The universe may end in the cold, quiet heat death. One possible fate of the cosmos is heat death, a time when all energy is evenly spread and no more work can be done.
Stars will fade, black holes will vanish, and even particles may decay, leaving behind only a thin, uniform haze of radiation. In this vision, the universe does not end in fire or collapse, but in silence, an infinite stillness where nothing stirs. Time itself would continue, but with no change, no events, no warmth. It would be a cosmos asleep forever. Though it sounds bleak, it is also strangely peaceful. The ultimate quiet, the final drift into stillness. If this is the end, it will come not with violence, but with calm after countless trillions of years. The universe, having burned bright for ages, will simply rest, its long story closing in infinite silence, or collapse back inwards in a big crunch. Another possibility is that the universe, instead of expanding forever, might one day slow, halt, and reverse. In this scenario, gravity overcomes expansion, pulling galaxies back together. The cosmos would shrink, growing hotter and denser, until all matter collapsed into a final singularity, a big crunch. If so, the universe would end as it began, in fire and density, time folding back upon itself. Some versions of this theory suggest it might not be the end at all, but part of a cycle with each crunch followed by a new bang, a rebirth of creation. Though current evidence suggests expansion will continue, the idea remains powerful, a vision of the universe breathing in and out across eternity. To imagine it is to see not just an ending, but a renewal, a cosmos forever collapsing and blooming like a great cosmic heart. Some theories suggest it may bounce and begin again. In some models of cosmology, the universe does not end at all, but cycles endlessly between expansion and contraction. After reaching its largest size, it may collapse inward, only to rebound in another Big Bang, beginning again with new stars, new galaxies, and new stories. This is called the Big.
Each cycle may erase the details of the last, yet carry forward some faint imprint, passing echoes of past universes into new ones. If true, the cosmos may have no beginning and no end, only an infinite rhythm pulsing across time like a heartbeat. To imagine such cycles is to see existence not as a straight line, but as a circle repeating forever, each turn different but connected. It is a comforting thought that even if our universe fades, another may rise, carrying the story forward into eternity. Others imagine new universes sprouting from ours. Another possibility is that our universe is only one among many. In this view, new universes may sprout from black holes or emerge from quantum fluctuations, each with its own laws of physics and its own unfolding story. Our universe may be just one bubble in a vast cosmic foam, with countless others floating unseen beyond. Some may last only moments. Others may grow vast and rich with galaxies.
If this is true, then even as our universe evolves, others are being born in silence, each with its own beginning and end. To think of this is to expand imagination beyond even the stars above us. The cosmos may not only be infinite in space, but infinite impossibilities. With every universe a dream within a dream, we may live in just one of countless realities, each drifting quietly in the endless sea. Even black holes can get kicked across the galaxy. When two black holes merge, they do not always settle quietly. The collision can release powerful gravitational waves in one direction, giving the new black hole a kind of kick. This kick can send it hurtling through its galaxy at astonishing speeds, sometimes fast enough to escape entirely. Imagine a black hole, millions of times the mass of the Sun, drifting alone between galaxies, ejected by the force of its own creation. Astronomers have found evidence of these wandering giants, their influence revealed by the stars and gas they disturb in passing. To think of black holes, already so mysterious, being flung across the cosmos is both haunting and beautiful. They remind us that even the most massive objects are not fixed in place. The universe is full of motion, full of surprises, even in the shadows where light itself cannot escape. The universe might be older than we thought. Most current estimates place the age of the universe at about 13.8 billion years. This number is based on measurements of the cosmic microwave background and how fast the universe is expanding. But not all methods agree. Some observations of ancient stars and galaxies suggest they may be older than that estimate allows. Others question the assumed rate of expansion, or suggest that dark energy may be changing over time. These tensions haven't been resolved, and most astronomers still accept the 13.8 figure. But the questions remain. Could the universe be older? Did we miss something fundamental? It's possible that what we think of as the beginning was just one part of a longer, stranger story. There are thousands of rogue planets drifting through space without stars. Not all planets orbit stars. Some are completely unbound, floating alone through the galaxy without a sun to warm them or light their skies. These rogue planets may have formed normally, then ejected from their star systems by gravitational chaos. Others might have formed on their own, like failed stars. They're dark, cold, and nearly invisible unless they pass in front of background stars or glow faintly in infrared. Astronomers estimate there may be billions of them in the Milky Way, perhaps even more than the number of stars. Each one is a silent world, adrift in darkness, spinning alone in the vast spaces between. No sunrises, no sunsets, just endless night,
broken only by distant starlight.
The universe may recycle itself through infinite cycles. The standard model of cosmology describes a universe that began with the Big Bang and will continue expanding, possibly forever. But some theories imagine a different story, one where the universe goes through cycles of expansion and collapse. In these models, the universe doesn't end with a cold fade or a final crunch. Instead, it resets. After reaching a certain point, it might bounce, collapsing inward, then rebounding into a new expansion. Each cycle could wipe away the old structures, but preserve subtle traces of what came before. These ideas are speculative, but intriguing. They suggest that the universe may have no true beginning or end, just a rhythm stretched across unimaginable spans of time. One universe giving rise to another over and over again. The light from a distant star can be twisted by a single planet. We often think of planets as small compared to stars or galaxies, but their gravity still has power. When a planet passes in front of a distant star, it can bend and magnify the starlight through a process called micro-lensing. For a brief time, the star appears brighter, its light warped by the hidden planet's pull. This effect has allowed astronomers to discover planets far beyond our reach, worlds we could never see directly. To imagine it is to picture a tiny planet, invisible in the vast dark, briefly revealing itself by bending the light of a star billions of years old. It is proof that even the smallest bodies can leave marks on the grand stage of the cosmos. The universe is not only shaped by giants, but also by the quiet pull of unseen companions drifting silently in the dark. The universe once glowed with a brilliant orange light. Long before stars and galaxies filled the sky, the young universe itself glowed. As it cooled from its hot beginnings, the light it emitted shifted through colors. For a time, the entire cosmos was bathed in a brilliant orange glow, like an eternal sunset stretched across all of space. Slowly, as the universe expanded and cooled further, this light softened into red, then infrared, and finally into the faint microwaves we detect today as the cosmic background radiation. Though invisible to our eyes now, that orange glow was once everywhere, filling the skies of a universe without stars. To picture it is to imagine space itself alight, an infinite horizon glowing with warmth. The stars we see today are only echoes of that first radiance, the universe's original light show, fading into memory, but still whispering through the background of the cosmos. Some parts of the universe are cooling slower than others. The universe as a whole cools as it expands, but not all regions do so at the same pace. Some pockets of space remain warmer for longer due to differences in density, energy, or the influence of dark matter and dark energy. This uneven cooling leaves behind variations in the cosmic microwave background, tiny temperature differences that map the seeds of galaxies. Even today, astronomers find regions that appear slightly warmer or colder than expected, puzzling signs that the universe is not perfectly uniform. These subtle differences may hold clues to new physics or even to processes beyond our visible horizon. To imagine it is to see the universe as a patchwork, not seamless, but textured, with quiet variations woven into its fabric. Even in its vast calm, the cosmos carries hints of complexity, patterns still waiting to be fully understood. We've captured the shadow of a black hole. In 2019, the Event Horizon Telescope released the first direct image of a black hole, or rather, of its shadow. The black hole itself can't be seen, but the glowing ring of hot gas swirling around it reveals its presence. This particular black hole lives in the center of a galaxy about 53 million light-year away.
The image shows a circular silhouette, the region from which no light escapes, surrounded by a halo of radiation twisted by gravity. It took years of global collaboration, coordinating telescopes around the world to act as a single planet-sized lens. The result was more than a picture. It was a quiet triumph of science, giving us our first glimpse at one of the most mysterious objects in the universe. Not through fiction or theory, but through light. You can see a galaxy with your naked eye from your backyard. Most galaxies are so far away that even powerful telescopes reveal only faint smudges. But there's one you can see without any equipment at all: the Andromeda Galaxy. On clear, dark nights in the northern hemisphere, it appears as a soft, hazy oval in the sky, just visible to the eye. It's over 2.5 million light-years away, meaning the light you see began its journey long before humans evolved.
Andromeda contains 1 trillion stars, more than double the Milky Way, and it's slowly moving toward us. It's hard to grasp, but you can look up and see an entire galaxy with no telescope, no filter, just the sky, your eyes, and the soft glow of something vast and ancient drifting in the dark. One tiny satellite detected the whisper of a distant black hole collision. In 2015, a small satellite named LIGO detected something extraordinary. A faint ripple in spacetime from more than 1 billion light-years away. It was caused by 2 black holes colliding, sending gravitational waves across the cosmos. These waves are incredibly subtle. When they reach Earth, they stretch and squeeze space by less than the width of a proton. Yet with delicate instruments, we can detect them. LIGO and its sister observatories act like cosmic ears, listening to the universe's deepest rumblings. What they heard was confirmation of a prediction Einstein made a century earlier. But even in the silence of space, massive events can send out waves. We can feel a single chirp from the merger of invisible giants caught by a tiny detector on a quiet corner of a small blue planet. Some stars in the Milky Way are older than the Milky Way itself. Not every star in the Milky Way was born here. Some halo stars, ancient metal-pur and wandering in long tilted orbits, appear to have formed even before the Milky Way had fully taken shape. Astronomers believe these stars may have originated in smaller primordial galaxies that merged with our own billions of years ago. Their chemical fingerprints show almost no heavy elements, suggesting they were born shortly after the Big Bang. They move slowly and high above the galactic plane, like elder spirits from a time before spirals, before order. In their light, we glimpse a universe that was younger, wilder, and still learning to become what it is. Our solar system orbits the center of the Milky Way at over 828,000 kilometers per hour. That's more than 230 kilometers every second. And still, it takes about 225 million years to complete just one loop around the galaxy. This path is called a galactic year. In Earth's time, we've only gone around the Milky Way about 20 times since the solar system formed. When the first dinosaurs appeared, we were in a different part of the galaxy entirely. The stars we see today weren't always nearby and won't always remain. Everything is in motion, quietly,
slowly, endlessly. Even as we sleep, the Earth turns, the Moon circles, and the entire solar system sweeps forward through a galaxy in motion. The galaxy is still growing. Although the Milky Way is ancient, it isn't finished. Even now, it continues to gather material, gas from the intergalactic medium, stars from captured dwarf galaxies, and streams of dark matter that feed its halo. It grows not like a living thing, but like a gravitational structure deepening over time.
Some of this growth happens quietly, through unfailing clouds. Other times, it comes with disruption, as satellite galaxies are torn apart and their stars scattered across the sky. The galaxy you live in today is not the same one the dinosaurs saw, and the one your distant descendants may know could be larger still, stitched from the ruins of 1,000 smaller worlds. We still don't know how many arms the Milky Way has. It seems like something we should know. How many arms spiral from the center of our own galaxy? But from our position deep inside the disk, it's hard to see the whole structure. Dust clouds obscure distant regions. Stars blur into one another. For decades, astronomers believed there were 4 major spiral arms. More recent observations suggested maybe fewer, or that the arms twist and split in ways more complex than expected. Some fade into fragments, others wrap around unexpectedly. The Milky Way may not be a neat pinwheel at all, but a living, layered swirl of stars, shaped by forces we still don't fully understand. The Milky Way holds worlds larger than Jupiter, but float alone. Scattered throughout the galaxy are enormous planets that drift freely without orbiting any star. These rogue giants can be larger than Jupiter and wander through space in cold silence. They likely formed in young planetary systems, but were later flung out by gravitational interactions with other large bodies. Once ejected, they continue on solitary paths, illuminated only by the faint glow of their internal heat. Some of these planets may still retain thick atmospheres that trap warmth. Others may harbor swirling storms that churn slowly in the deep dark. Detecting these worlds is challenging because they do not reflect starlight. Instead, astronomers search for the faint infrared radiation they emit, or watch for subtle gravitational effects when they pass in front of distant stars. These lonely giants reveal how dynamic and chaotic planetary systems can be. Their existence suggests that planets are not always bound to the stars that formed them. Instead, they may roam indefinitely through the galaxy, traveling far from any warmth or light. These wandering worlds add a quiet and mysterious dimension to the Milky Way's population of planets. There are stars that feed on their companions. In some binary systems, one star grows dense enough to draw material from its partner. This process can occur when a star becomes a white dwarf, neutron star, or black hole. The stronger gravitational pull of the compact object strips gas from the companion's outer layers. This material forms a swirling disk around the feeding star, heating up as it spirals inward. The interaction can produce bursts of radiation that appear as bright flares in the sky. Over long periods, the feeding star may gain significant mass, altering its behavior and sometimes setting the stage for future explosive events. The star being consumed may lose much of its outer envelope, changing its structure and evolution. These dramatic relationships reveal how closely paired stars can influence one another. They show that stellar life cycles are not always solitary. Instead, some stars grow by taking material from their neighbors, creating systems shaped by both cooperation and conflict. These feeding stars remind us that even distant suns can experience intense
and transformative interactions. The Sun has completed fewer than 25 galactic orbits. In all of its 4.66 billion years of existence, the Sun has only circled the Milky Way around 20 times. That's fewer than you might expect, considering its incredible speed, nearly 830,000 kilometers per hour.
But the galaxy is so vast, and the Sun's path so long, that each orbit takes hundreds of millions of years. We often think of the stars as ancient and unmoving, but our solar system is still young on a galactic scale, a newcomer in a city of older, more traveled suns. We are part of the galaxy's motion, but still early in its long, winding story. The Milky Way's rotation defies Newton's predictions. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, just as outer planets move more leisurely around the Sun. But in the Milky Way, stars in the outer regions orbit almost as quickly as those near the center. This defies classical expectations. The reason, astronomers believe, is dark matter, an invisible, unknown form of mass that surrounds the galaxy in a vast halo. Without dark matter, the galaxy would not hold together. With it, the math works.
The Milky Way turns like a solid wheel, not because we understand it fully, but because something unseen is holding it in place. The Milky Way hums with cosmic radiation. Beyond visible light, the galaxy glows with more mysterious forms of energy. Cosmic rays, high-energy particles born in supernova and distant galaxies, stream through space and pass through your body every second. X-rays and gamma rays shimmer from dying stars and black holes. Radio waves drift from gas clouds, pulsars, and the cold breath of hydrogen. These invisible hums reveal what light cannot: the violence, magnetism, and ancient fires still flickering within the galaxy's bones. When you look into the night sky, you're only seeing a narrow band of the Milky Way's true spectrum. Beneath the stars, the galaxy hums softly in many colors. Many frequencies, a hidden symphony in the dark. There are double planet systems that orbit each other like dance partners. Not all permits revolve around stars alone. In rare cases, two planets of similar mass form close enough to one another that they share a mutual orbit. Instead of one dominating the other, the pair circles a common center of gravity located between them. These double planet systems move through space like partners, performing a slow and graceful dance. Their shared motion affects their rotation, their tides, and their long-term stability. Finding such systems is challenging because they often resemble single planets when viewed from afar. However, detailed observations can reveal small variations in their orbits that hint at their dual nature. These systems provide insight into how planets form and interact. They show that worlds can develop in cooperative pairs rather than solitary paths. The existence of such arrangements highlights the diversity of planetary configurations possible in the Milky Way.
Imagining two planets bound together in a cosmic waltz adds a touch of elegance to the vast and varied structures scattered across the galaxy. Some stars are shaped into flattened spheres by extreme rotation. Certain stars rotate so quickly that they become noticeably flattened. Their equators bulge outward due to centrifugal force, while their poles remain more compact. This shape affects the distribution of temperature across the surface. The poles tend to be hotter and brighter because the material there is more compressed, while the equator can appear cooler. This phenomenon is known as gravity darkening. Rapidly rotating stars are often young and massive, still carrying the angular momentum of their formation.
Their rotation also influences how they evolve. Fast-spinning stars can mix their internal layers more efficiently, changing the way they burn fuel.
Observing these stars helps astronomers understand the complex interactions between rotation, structure, and energy output. Their distorted shapes challenge the simple idea of stars as perfect spheres. They reveal that even familiar-looking points of light can hide unusual physical behavior. These flattened stars add another level of diversity to the Milky Way, showing that rotation can sculpt a star into forms very different from the ones we see near home. The Milky Way has already collided with other galaxies, and it will again. Our galaxy may feel like a stable home, but it is built from the wreckage of others. Over billions of years, the Milky Way has absorbed smaller galaxies, drawing them in, unraveling them, and scattering their stars into tidal streams that wrap around the disk. One such galaxy, the Sagittarius Dwarf, is being pulled apart right now. And far off in the night sky, Andromeda is drifting slowly closer. In about 4-5 billion years, the two great spirals will merge in a cosmic collision. Stars will almost never hit each other, but the galaxy's shapes will change forever, folding into a new form, vast and quiet. Even galaxies are not eternal. They evolve, collide, and begin again. The Milky Way holds regions filled with primordial hydrogen. Scattered throughout the galaxy are pockets of hydrogen that have remained largely unchanged since the earliest eras of the universe. These regions contain gas that existed before many generations of stars were born. While much of the hydrogen in the Milky Way has been processed through stars and enriched with heavier elements, these primordial areas preserve a simpler chemistry. Their presence helps astronomers trace the early history of the galaxy and understand how it grew from smaller structures. These clouds are cold, faint, and difficult to detect. Yet they play a vital role by feeding material into star-forming regions. They also allow scientists to compare modern galactic environments with ancient ones. Primordial hydrogen stands as a quiet reminder of the universe's beginnings, still drifting through the arms and halo of the Milky Way. There are stars that collapse into dense remnants without exploding. Not every massive star ends its life in a bright supernova. Some collapse directly into dense remnants without producing an outward explosion. This muted kind of collapse happens when a star's internal structure fails abruptly, allowing its core to become a black hole or neutron star with little outward display. Instead of being hurled into space, the outer layers may fall inward. These silent endings are hard to detect because they produce very few clear signals. Astronomers look for stars that simply disappear without explanation, or they search for faint gravitational clues that a compact remnant has taken shape. These quiet collapses help scientists map the boundary between explosive deaths and silent ones. They point to a more intricate picture of stellar death, where a star's final moments depend on delicate balances of mass, rotation, and inner structure. Some worlds are born within chaotic systems of multiple stars. In the Milky Way, there are planetary systems that form amid groups of 3 or more stars. Such environments are shaped by shifting gravitational forces that steer the paths of growing planets. Disks of dust and gas can twist and wobble, forming planets that must settle into stable orbits while competing pulls act on them from every side. Some planets end up circling one star in the group. Others find orbits around pairs of stars. In rare cases, planets may orbit all the stars together in wide loops. The chaos of these systems
creates a wide range of outcomes. Some planets are ejected and become rogues.
Others survive in balanced orbits that remain stable for long periods.
Studying these complex systems helps astronomers understand how planets form under extreme conditions. They show that planetary birth can occur even in environments filled with disorder and constant change. The galactic center contains whirling disks of hot dust. Near the Milky Way's core, swirling disks of dust encircle the central black hole. These disks glow brightly in infrared light because the dust grains absorb intense radiation and heat to high temperatures. The material moves in fast, spiraling paths shaped by gravity and magnetic fields. As the dust orbits, it interacts with surrounding gas, creating structures that shift over time. Observing these disks helps astronomers understand how material flows toward the black hole and how energy from the core affects the surrounding environment. These glowing spirals reveal the dynamic nature of the galactic center.
They show that even dust behaves dramatically when placed in such powerful conditions, forming elegant structures that twist in the deep gravitational well. Some stars are kicked to extreme speeds when their companions explode. When a star in a binary system explodes as a supernova, the sudden release of energy can disrupt the delicate balance that holds the pair together. If the surviving star is flung outward at the right moment, it can be propelled to extraordinary speeds. These runaway stars move far faster than typical stars in the Milky Way. Their high velocities reveal the violent events that set them in motion. As they travel, they carry with them the chemical signatures of their original environments. Studying these stars helps astronomers understand the outcomes of stellar explosions and the dynamics of binary systems. Their rapid motion also provides clues about the gravitational landscape of the galaxy. These swift stars remind us that even the seemingly peaceful sky holds records of dramatic and energetic processes. The galaxy contains solar systems with planets that circle in wildly tilted orbits. Not all planetary orbits align with the equators of their stars. Some planets move on steeply tilted paths, circling their stars at sharp angles that differ greatly from the orbits of their siblings. These tilted orbits can arise from past interactions with other planets, passing stars, or the gravitational pull of a distant companion. The unusual angles affect the climate and long-term stability of the parrot. Seasons can become extreme, and the length of daylight can vary dramatically. Observing these systems helps astronomers understand the chaotic processes that shape planetary architecture. The presence of tilted orbits shows that solar systems can evolve in surprising ways, creating arrangements far different from the orderly patterns seen in our own system. These worlds highlight the diversity of planetary motion in the Milky Way. Some worlds are covered in ice that never melts. In the far reaches of the galaxy, or in systems where stars emit only faint heat, some planets remain frozen from surface to core. Their icy crusts can extend for kilometers, sealing away oceans or rocky interiors beneath solid layers. These worlds may have atmospheres too thin to trap warmth, or may orbit stars so cool that temperatures never rise above freezing. Some exist as rogue planets drifting in total darkness, where internal heat gradually fades until the surface becomes completely frozen. Although these planets seem quiet, their interiors may still harbor activity if enough heat remains from their formation. Studying frozen worlds helps astronomers understand how planets lose heat and how different environments evolve. Their silent, unchanging surfaces contrast sharply with the dynamic weather and geology seen on warmer planets. These icy worlds show that the Milky Way contains environments where cold dominates completely.
The Milky Way holds electric-charged nebula that glow with ghostly light. Certain nebula in the galaxy emit a faint, eerie glow created by charged particles moving through magnetic fields. These electric-charged regions occur when energetic radiation strips electrons from atoms, creating ionized gas. As electrons recombine with ions or move through magnetic structures, they emit soft, ghost-like light detectable in various wavelengths. These nebula often form near hot stars or in regions shaped by past explosions. Their appearance reveals the presence of powerful forces acting on the gas. Observing them allows astronomers to trace magnetic fields that are otherwise invisible. The glow carries information about temperature, density, and the processes that energize the gas. These nebula add a subtle, ethereal beauty to the Milky Way, showing that even faint light can tell rich stories about the energy flowing through space. The chemical makeup of stars reveals their origin. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at birth. By studying these signatures, astronomers can trace a star's history. Some stars are rich in heavy elements like iron and calcium, suggesting they formed in dense, metal-rich regions. Others are nearly pure hydrogen and helium, born when the universe was still young. These differences allow scientists to group stars into families, uncover ancient mergers, and reconstruct the hidden story of the Milky Way's formation. In this way, chemistry becomes a kind of time machine, letting us read a star's past like a line of ancient poetry written in light. The sky is full of stellar streams from shredded galaxies.
Across the sky, thin ribbons of stars stretching arcs and curves, barely visible, but unmistakable when mapped with precision. These are stellar streams, the remnants of smaller galaxies that wandered too close to the Milky Way and were pulled apart. As they orbit, their stars are smeared across space by tidal forces, forming long, delicate trails that trace their former paths. Some wrap around the galaxy like ghostly halos, others dive in toward the core. These streams are evidence of past collisions, quiet merges that built the Milky Way over billions of years. The galaxy, like a tree, carries the rings of its past in every thread of light. The Milky Way is warped. Our galaxy doesn't lie flat like a perfect spiral. Its disk bends upward on one side and downward on the other, forming a graceful wave across the stars. This subtle warp was invisible to us until radio telescopes mapped the hydrogen gas that stretches far beyond the starlight. Astronomers believe the distortion may be caused by satellite galaxies tugging gently on the Milky Way's edges, or by clumps of dark matter bending the structure from below. Like ripples in a great spinning sheet, the warp reveals that even galaxies are never fully still. Over time, they bend, flex, and change form in response to invisible forces. From a distance, the Milky Way might look like it's dancing slowly through space. You can only see about 0.00003% of the Milky Way with the naked eye. Under a clear, dark sky, far from cities and streetlights, you might see a few thousand stars. To the human eye, that seems like an ocean of light, but it's barely a droplet. The Milky Way contains over 100 billion stars. Most are hidden from view. Some lie behind thick curtains of dust. Others are too faint or far away for our vision to reach. The pale streak of the Milky Way that crosses the sky on moonless nights is just the innermost whisper of the whole. We live surrounded by a colossal river of starlight, and yet almost all of it remains invisible to us, too vast to grasp from within. There are dense clusters where stars live only a light year apart. In certain regions of the Milky Way, stars form in such high numbers
that they end up packed very closely together. In these dense clusters, the distance between neighboring stars can be as small as 1 light-year, far closer than the distance between the Sun and its nearest companion. The intense gravitational pull within these clusters influences the motion of each star. Their combined light creates brilliant scenes that would fill the sky for any planet orbiting within such a cluster. Over time, these groups gradually lose stars as gravitational interactions push some outward. However, the densest clusters remain tightly bound for long periods. Studying them provides insight into the earliest stages of stellar evolution and the environments in which many stars are born. These compact clusters show that the Milky Way contains regions of both solitude and incredible crowding. They offer a glimpse into the vibrant communities where stars begin their lives. The galactic center contains arcs of energized gas that twist like ribbons. Near the heart of the Milky Way, clouds of gas become energized by the intense radiation and magnetic fields surrounding the central black hole. These forces shape the gas into long, graceful arcs that twist and curve like ribbons in the dark. The structures glow in radio and infrared wavelengths, revealing their delicate outlines. Many of these arcs trace the paths of magnetic fields that thread through the region. Others form where energetic particles collide with gas, creating bright filaments. Observing these ribbon-like shapes helps astronomers map the complex interactions at the galaxy's center. They show how gas flows, how magnetic energy is distributed, and how past events have influenced the environment. Although these arcs may appear serene, they are shaped by powerful and dynamic forces. Their graceful forms add an unexpected beauty to one of the most extreme places in the Milky Way, where energy and gravity continually sculpt the surrounding space. Some worlds orbit stars that flare with intense radiation. Throughout the Milky Way, certain stars pulse with sudden bursts of radiation that surge outward like brief shocks of energy. These flares are caused by rapid changes in the star's magnetic field, releasing heat and light far stronger than the star's usual glow. When a planet orbits close to such a star, it experiences sharp waves of radiation that can heat its atmosphere, disrupt its chemistry, or gradually strip away its upper layers. Yet some planets endure these harsh conditions, developing atmospheres that adapt over time. Observing these systems helps astronomers understand how flares shape planetary environments and influence the potential for habitability. The intensity of the flares varies, with some stars erupting only occasionally, while others release bursts on a frequent schedule. These planets experience skies that can brighten suddenly, transforming their atmospheres with each flare. The idea that entire worlds orbit such volatile suns adds a dramatic sense of diversity to the galaxy. It shows that life and stability are shaped by forces far beyond simple sunlight, and that stars themselves can be restless, changing the conditions of any world that circles them. The Milky Way holds enigmatic gamma burst sources. Hidden throughout the galaxy are rare objects capable of releasing brief flashes of gamma radiation, the most energetic form of light. These bursts are sudden, short-lived, and incredibly powerful. Some occur when dense stellar remnants collide, while others may form through magnetically driven events in compact stars. Because gamma bursts happen quickly and fade rapidly, they are difficult to observe. Instruments must be watching at exactly the right moment to detect them. When these bursts are captured, they provide valuable insight into extreme physics. The energy released in a single burst can exceed the total output of many stars combined, yet the event may last only seconds. These powerful flashes illuminate the environments around their sources, revealing conditions that cannot be reproduced anywhere else. Studying them helps astronomers probe the nature of magnetic fields, gravity, and dense matter. Even though these bursts are rare, their presence shows that the Milky Way hosts events of astonishing intensity. They offer glimpses into the most powerful processes shaping the lives of compact stars. Stellar nurseries shape the spiral arms. The Milky Way's spiral arms are not simply made of stars, they're woven from the birthplaces of stars. Giant clouds of hydrogen, dust, and molecules drift through the galaxy.
And when these clouds pass through the spiral arms, they are compressed and set alight with newborn suns.
These regions are called stellar nurseries, chaotic, glowing, and full of motion. Ultraviolet light from new stars lights up the clouds, painting the arms with radiant blues and silvers. These bursts of creation trace out the spiral shape, illuminating the curves of the galaxy with quiet fire. Every star, even the sun, was born from one of these cloudy cradles long ago. The Milky Way is surrounded by a vast halo. Beyond the flat spiral disk lies something far more diffuse, a spherical halo that surrounds the entire galaxy. It contains ancient stars, globular clusters, and enormous amounts of dark matter. Though it is nearly invisible, this halo may hold the majority of the Milky Way's mass. Its stars are spread thin across vast distances, orbiting in long, slow arcs that rarely touch the disk.
The halo also preserves the remnants of ancient galactic mergers,
streams and shells of stars torn from smaller galaxies and left behind like cosmic fossils. It is the galaxy's outer memory, quiet and dim, but still in motion, still shaping what the Milky Way becomes. It contains over 150 globular clusters. Globular clusters are among the oldest objects in the galaxy. Compact spheres made of hundreds of thousands of tightly bound stars. They orbit the galactic center in the halo like moths circling a distant flame. These clusters are incredibly stable, some more than 12 billion years old, and many contain stars that predate the Milky Way itself. Their stars are matter poor, meaning they formed before the universe had time to create many of the heavier elements. They serve as time capsules, holding clues to how the galaxy formed, what it consumed, and what conditions were like in the early cosmos.
These quiet golden spheres drift patiently above and below the galactic plane, glowing in the dark.
The galaxy is still growing. Although the Milky Way is ancient, it isn't finished. Even now, it continues to gather material. Gas from the intergalactic medium, stars from captured dwarf galaxies, and streams of dark matter that feed its halo. It grows not like a living thing, but like a gravitational structure deepening over time. Some of this growth happens quietly through infilling clouds. Other times it comes with disruption as satellite galaxies are torn apart and their stars scattered across the sky. The galaxy you live in today is not the same one the dinosaurs saw, and the one your distant descendants may know could be larger still, stitched from the ruins of 1,000 smaller worlds. Some planets orbit dead stars. Although it may seem unlikely, permits can survive the dramatic transformation of a star into a stellar remnant.
Some orbit white dwarfs, the hot cores left over after stars like the Sun shed their outer layers.
Others circle neutron stars, which form from the collapse of massive stars. These environments are harsh, flooded with intense radiation. Yet, some planets endure. They may have formed after the star's death, assembling from leftover debris, or they may have migrated inward over time. Around white dwarfs, a planet can receive stable light and heat once the remnant cools enough. Around neutron stars, conditions can be extreme, with strong magnetic fields influencing the planet's atmosphere. The presence of planets around dead stars challenges assumptions about planetary survival. It shows that worlds can persist even after dramatic cosmic events. These planets offer insights into how systems rebuild themselves and how diverse planetary environments can be. They serve as reminders that even the aftermath of stellar death can give rise to new and surprising structures.
The galaxy contains regions rich with organic molecules. Across the Milky Way are clouds filled with complex organic molecules. These molecules form on the surfaces of dust grains or within cold gas, combining simple elements into intricate structures. Some of these molecules are precursors to the chemistry found in living organisms, although their presence does not imply life. Instead, they show that the building blocks of biology can arise naturally in many environments. These regions are often located in dense molecular clouds, where temperatures are low and ultraviolet radiation is limited. Infrared and radio telescopes detect the signatures of these molecules, revealing their abundance. Their presence suggests that chemistry in the galaxy is rich and varied. Understanding how these molecules form helps astronomers learn about the early stages of planetary development. They may eventually become part of comets, asteroids, or even planets. The idea that organic complexity exists in quiet clouds scattered throughout the Milky Way brings a sense of connection to the broader universe. It shows that the seeds of chemistry are widespread, waiting for the right conditions to unfold. The galaxy has enormous molecular clouds. Scattered throughout the Milky Way are vast, dark clouds of cold gas, the raw material of stars. These molecular clouds, composed mostly of hydrogen molecules and traces of dust, can span hundreds of light years across. Within their cold, dense interiors, gravity begins to gather material, forming clumps that collapse into new stars and planets. Some of these clouds are so large and so cold that they absorb visible light entirely, appearing as black patches against the starry sky. They are the galaxy's wombs, quiet, hidden places where the future begins in silence, tucked within curtains of shadow and gas. Supernovas stir the galaxy like storms. When massive stars reach the end of their lives, they explode in cataclysmic supernova. Events so powerful they can outshine entire galaxies for a brief moment. These explosions don't just end lives, they create. Shockwaves from supernova ripple through the interstellar medium, compressing nearby clouds and triggering new waves of star formation. They enrich the surrounding space with heavy elements like iron and gold forged in the heart of the dying star. In this way, supernova act like storms within the galactic ecosystem, stirring, fertilizing, and reshaping everything around them. They are the galaxy's moments of chaos, destructive, radiant, and necessary. There are worlds locked in perpetual twilight between their suns. In some binary star systems,
a planet can settle into an orbit that places it between two stars in a balanced configuration. When this happens, the combined light from the pair can create a world bathed in constant twilight. The sky would never become fully dark, and true day might never arrive. The lighting on such worlds would shift softly as the stars move in their own orbit, but darkness would remain rare. Temperatures on these planets depend on the distance from the stars and the intensity of their light. Some of these twilight worlds may be mild, while others could be cold or even warm enough to allow liquid water. The gravitational forces from two stars create complex patterns in the planet's orbit. Yet many of these configurations remain stable for long periods. Studying such systems shows how planetary environments can vary in surprising ways. They reveal that sunlight is not always simple or singular. These dusk-lit worlds offer a picture of planetary life shaped by soft and constant glow. Stellar nurseries in the Milky Way can spawn entire star clusters at once. Deep within the Milky Way lie vast regions of cold gas where new stars are born. These stellar nurseries often produce not just single stars, but entire clusters. As gravity pulls large quantities of gas together, the material breaks into many dense pockets. Each pocket can collapse into a star, leading to the formation of groups that emerge together. These clusters often contain stars of many different sizes, from massive blue giants to small red dwarfs. The stars interact through their gravity and radiation, shaping the environment around them. Young, massive stars create strong winds and intense light that carve out cavities in the surrounding gas. These processes can trigger additional star formation, or halted, depending on how the material is affected. Once the gas is cleared, the newly formed cluster begins to drift through the galaxy. Over time, some clusters remain intact, while others slowly dissolve. Studying these nurseries reveals how the Milky Way continues to renew itself, building new generations of stars in waves of creation. Some stars shed their outer layers in vast, shimmering shells. As certain stars near the end of their lives, they undergo changes that cause them to shed their outer layers. These layers expand into space, forming large, glowing shells of gas surrounding the dying star. The shells appear luminous because the remaining core heats the gas, causing it to emit soft light. These elegant structures are called planetary nebulae. Although they have nothing to do with planets, each one carries unique shapes formed by the star's rotation, magnetic fields, and the motion of surrounding material. Some nebula form rings, others take on butterfly-like forms, and still others appear spherical. Over time, the gas disperses into the surrounding space, enriching the interstellar medium with elements created inside the star. These shimmering shells represent a brief but beautiful phase in the life cycle of low to medium mass stars. They provide vital clues about how stars evolve and how they contribute new material to the galaxy. Their delicate structures transform the quiet death of a star into a luminous event that ripples outward for thousands of years. The Milky Way contains strange carbon stars that burn with deep crimson light. Among the many stars in the galaxy, some shine with an unusually rich red color. These carbon stars have atmospheres filled with carbon compounds that absorb blue light and allow deep crimson tones to dominate. They form when aging stars dredge up carbon from their interiors and release it into their outer layers. This process changes the chemical balance of the atmosphere and gives the star its distinctive appearance. Carbon stars often appear especially bright in infrared wavelengths, making them stand out in surveys of the galaxy.
They also produce dust that enriches the interstellar medium.
Studying these stars helps astronomers understand how elements are cycled through stellar evolution. Their red glow adds diversity to the Milky Way's population of stars, showing how different chemical processes can influence the appearance of starlight. These stars burn with a warm and gentle radiance, offering a reminder that even small changes in composition can create dramatic effects in the light we see. Some stars travel far from the places where they formed. A star's birthplace does not always determine its fate. Over time, many stars drift away from their natal clouds, nudged by gravitational encounters, orbital resonances, or the slow influence of spiral arms. Some are even thrown out at great speeds, hurled across the galactic disk or into the halo. Others move more slowly, gradually shifting their orbits inward or outward as they circulate through the galaxy. Even our Sun did not begin where it is now. Following stellar paths reveals a Milky Way that is anything but still, a galaxy full of motion, exchange, and quiet displacement. For a star, home may be only a temporary condition. The galaxy's habitable zone may extend across tens of thousands of light years. Just as Earth resides in a Goldilocks zone around the Sun, not too hot and not too cold for life, the Milky Way may possess its own galactic habitable zone. This region is thought to lie between the hazardous inner core, rich in radiation and gravitational turmoil, and the thin, metal-poor outer edges, where forming planets may be more difficult. Somewhere in between lies a wide band where conditions are stable. Star density is moderate, and elements like carbon, oxygen, and iron are abundant. Earth lies within this zone. One quiet orbit in a vast swirl where life might not be alone in finding a foothold. The spiral arms are not fixed structures. The Milky Way's spiral arms might seem like permanent features, grand sweeping lines carved into the galaxy's disk. But they are not made of fixed stars. Instead, they are patterns, density waves that ripple slowly through the disk, compressing gas and triggering new stars as they pass. Stars drift into these arms, shying for a while and then drift out again. The spiral structure moves at a different speed than the stars themselves, like a traffic jam moving through a highway. From afar, it looks like form and order. From within, it's a pattern of shifting motion, held together by gravity and time, never still, always flowing. Massive supernova remnants still glow with fierce energy. When a massive star explodes, it leaves behind a cloud of gas and debris known as a supernova remnant. These remnants expand outward for thousands of years, interacting with the surrounding interstellar medium. Even long after the explosion has faded from view, the remnants continue to glow. Shockwaves heat the gas to high temperatures, producing X-rays and visible light. The filaments and knots within the remnant reveal details about the original star and the force of the explosion. Studying these remnants helps astronomers understand how heavy elements are dispersed throughout the Milky Way. They also show how energy from dying stars shapes nearby regions. Over time, the expanding remnant slows and cools, eventually blending into the surrounding gas. Yet, during its active phase, it stands as a brilliant reminder of the dramatic events that occur when massive stars reach the ends of their lives. These glowing clouds show that the aftermath of a supernova remains vibrant and full of information long after the initial flash has faded. Some planets skim so close to their stars they glow red-hot. In the Milky Way, there are planets that orbit so near their stars that their surfaces heat to extreme temperatures. These close-in worlds are often large and gaseous, with atmospheres that swell and shimmer under the intense radiation. The heat causes their clouds to glow, sometimes giving the entire planet a reddish or golden hue.
Their dayside temperatures can vaporize minerals and metals, creating exotic atmospheric chemistry. The intense stellar winds constantly strip away particles from their upper layers, forming long tails of gas that trail behind them. These planets complete orbits quickly, sometimes in only a few days. Studying them reveals how planets adapt to being in such harsh proximity to their stars. Their structure, weather, and atmospheric escape provide valuable clues about planetary survival under extreme conditions. These red-hot worlds show that the Milky Way contains planets far stranger and more varied than the ones found in our solar system. Galaxies in the local group are gravitationally bound. Despite their vast separations, the galaxies of the local group are not drifting apart. In fact, many are moving slowly toward one another. Gravity holds them in a kind of slow-motion ballet, curving their paths across millions of years. Some of the smallest galaxies orbit the Milky Way like moons, looping and falling, dissolving into streams. Others drift independently, but remain tethered, caught in a web of shared motion. Over time, this group may condense. Galaxies may merge, fade, or be absorbed. It's not a static arrangement, but a gentle gathering of cosmic islands, a family drawn closer by time, inertia, and the long reach of gravity. The galaxy's disk has a thick and thin component. The Milky Way's disk looks flat from a distance, but up close it's layered. The thin disk is where we live. A wide, dense plain filled with young stars, open clusters, and star-forming gas. But above and below it lies the thick disk, older, puffier, and more diffuse. Stars in the thick disk tend to be older, with fewer heavy elements. They move in orbits that are more tilted and elliptical, suggesting they formed under different conditions or were stirred by early galactic collisions. The galaxy's disk is not uniform. It's textured, layered, and shaped by time, like sediment settled on the floor of a cosmic ocean. The galaxy's magnetic field threads through the disk. Though invisible to the eye, the Milky Way is laced with a vast magnetic field stretching across the disk, rising into the halo, and weaving through the interstellar medium. This field is weak by earthly standards, but over galactic distances, it shapes how cosmic rays travel, how gas clouds collapse, and how matter flows through space. It aligns with spiral arms, forms arcs above the plane, and twists into loops that defy simple explanation. Studying it requires radio telescopes and careful analysis, but its presence is unmistakable. The Milky Way does not just glow with light. It breathes with magnetism, a subtle pulse running through its bones. The interstellar medium is full of invisible structures. Between the stars lies more than emptiness. The interstellar medium, a thin blend of gas, dust, and plasma, weaves its way through the Milky Way like a fog. To the naked eye, it is mostly invisible, but when viewed with radio and infrared telescopes, it reveals a stunning complexity. It forms filaments, bubbles, shock waves, and cold, dense clouds where stars are born. Supernova carve vast cavities in it. Stellar winds sculpt it into shapes that ripple across light years. The space between stars is not a void, but a shifting web of matter and magnetism. The quiet fabric from which galaxies evolve and life eventually begins. The Milky Way has stars that blast jets of particles across space. Certain stars in the galaxy produce narrow, powerful jets of particles that shoot outward at tremendous speeds. These jets often form when material spirals onto a dense object, such as a neutron star or a young star surrounded by a disk of gas. As the material falls inward, magnetic fields twist and focus it into slender streams that leap into space. These jets can travel for long distances, sometimes reaching light years from their source. They illuminate surrounding gas, carving paths that reveal the structure of the region. In young stars,
Jets help clear away the leftover material from the formation process. In older, more compact stars, the jets can become extremely energetic, producing radiation detectable across the galaxy. These dramatic phenomena show how magnetic fields and gravity combined to create powerful and elegant structures. The sight of a star launching focused streams of energy into the dark is a reminder of how dynamic and creative the universe can be. Even small systems can produce effects that reach far beyond their immediate surroundings.
A few stars move so fast they will escape our galaxy forever. Most stars in the Milky Way follow stable orbits shaped by the galaxy's mass. However, a rare group of stars travels at extraordinary speeds, fast enough to eventually leave the Milky Way entirely. These hypervelocity stars are launched by powerful gravitational interactions. Some are slingshotted by the central black hole when they pass too close. Others are released when their binary partners explode, suddenly freeing them from an orbit. Once accelerated, these stars move on long paths outward, eventually drifting into intergalactic space. They shine like ordinary stars, but carry unusual velocities that reveal their dramatic histories. Studying them helps astronomers understand the extreme conditions near the galactic center and the outcomes of supernova explosions. These runaway stars remind us that even massive galaxies cannot hold all their members forever. Some will break free, carrying their light into the empty space between galaxies. Their journeys will last for billions of years, silent and solitary, shaped by the moment that set them on their way. Some regions in the Milky Way are filled with electricized plasma clouds. Scattered throughout the galaxy are clouds made not of cold gas, but of energized plasma. These regions contain charged particles that respond strongly to magnetic fields. As a result, they behave differently from ordinary gas clouds. They can twist into filaments, ripple like waves, or glow with soft light generated by electrons spiraling through magnetic structures. Many of these plasma clouds are created by massive stars or supernova explosions that pump energy into their surroundings. Others are shaped by turbulence in the interstellar medium. Studying these regions provides insight into the magnetic environment of the Milky Way, which cannot be observed directly. Plasma clouds help astronomers trace the invisible fields that thread the galaxy. They also influence how cosmic rays travel, guiding or deflecting them as they move. These charged regions add another layer of complexity to the Milky Way. They reveal that the spaces between stars are not empty, but filled with subtle energy, shaped by both matter and magnetic forces. Giant nebulae glow with colors created by energetic young stars. Throughout the Milky Way, there are vast nebulae lit by the presence of young, massive stars. These stars emit intense ultraviolet light that energizes the surrounding gas, causing it to shine with vivid colors. Hydrogen glows in soft reds, while oxygen can produce gentle greens or blues. These glowing clouds are often birthplaces of new stars. Inside them, dense pockets of gas collapse into young suns that eventually emerge from the surrounding material. The shapes of nebula are sculpted by stellar winds, radiation, and turbulence, forming arches, pillars, and cavities that create some of the most striking scenes in the galaxy. Studying these nebula helps astronomers understand how stars form and how they influence their environment. The glowing clouds also reveal the chemical makeup of the galaxy. Since different elements produce different colors when energized, these luminous regions remind us that starbirth is both powerful and beautiful. They fill the Milky Way with soft, colorful light,
transforming ordinary gas into radiant sculptures shaped by the presence of young and energetic stars. Spiral arms are shaped by density waves. The spiral arms of the Milky Way are not fixed trails of stars. They are patterns formed by waves of higher density moving through the galactic disk. As gas and dust pass through these waves, they are compressed, triggering star formation and lighting up the arms with bright, young stars.
These stars eventually drift out of the wave, while new ones form behind them, creating a self-sustaining illusion of structure. Like ripples in a pond or traffic clumping on a highway, the arms are dynamic, always in motion. From a distance, they appear still. From within, they are a dance of matter and rhythm, shaped by gravity and time. Stars are born from cold, collapsing gas. In the dark arms of the Milky Way, star formation begins in silence. Massive clouds of molecular hydrogen, sometimes hundreds of light years wide, drift through space, chilled to just a few degrees above absolute zero. Within these clouds, gravity slowly takes hold. Small regions grow denser and begin to collapse under their own weight. As the gas falls inward, it heats, spins, and flattens, forming a protoar at the center. Over time, the pressure and temperature grow until nuclear fusion ignites and a new star is born.
From the coldest shadows come the brightest lights, spun gently into being by the quiet force of gravity. Star clusters can dissolve into the galactic field. Many stars are born not in isolation, but in groups, tight clusters formed from the same collapsing gas cloud. These clusters, bound by mutual gravity, drift together for millions or even billions of years. But over time, they begin to scatter. Tidal forces from the Milky Way's mass, close encounters with other stars, and internal dynamics all work to pull clusters apart. Stars peel away one by one until the costa fades into the general star field of the galaxy. Even our Sun was likely born in a stellar cluster long ago. Its siblings now scattered, dimmed, or lost in the haze of distance. The galaxy contains ancient, hypermetal-poor stars. Among the rarest and most precious objects in the Milky Way are hypermetal-poor stars, stars whose atmospheres contain almost no elements heavier than helium. Some of these contain less than 1/10,000th the iron found in the Sun. These stars are believed to be among the first born after the very first supernova, carrying only faint traces of enrichment from a universe still forming itself. They are incredibly old, incredibly pure, and scattered in the halo like distant lanterns from the dawn of time. Each one is a kind of relic, a glowing, gravitationally bound signature from a near-forgotten epoch. Some stars in our galaxy rotate with blinding beams like cosmic lighthouses. There are stars called pulsars that rotate quickly and emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space. When the beam points toward Earth, we see a pulse of light that repeats with remarkable precision. The effect is similar to a lighthouse turning in the night, though far more powerful. Pulsars are created when massive stars collapse into neutron stars after supernovas.
Their rapid rotation and intense magnetic fields make them unique among stellar remnants. Some pulsars spin several times per second, while others rotate hundreds of times in that span. Their steady pulses help astronomers measure distances, map regions of the galaxy, and study fundamental physics. Pulsars reveal how matter behaves when compressed to incredible densities. They also contribute to our understanding of gravitational waves, since pairs of pulsars orbiting each other can produce ripples in space-time.
These cosmic lighthouses add rhythm to the Milky Way, sending steady signals through the darkness that allow us to study far-off regions with surprising clarity. Certain regions glow with radiation from past cataclysms. Throughout the Milky Way, there are zones that emit faint but persistent radiation. This glow is the lingering energy left behind by ancient events such as supernovas, gamma-ray bursts, or interactions between dense clouds of gas and high-energy particles.
These regions may no longer contain the original sources of the disturbance, yet the radiation remains as a signature of past activity. The glow often appears in wavelengths invisible to human eyes, such as X-rays or gamma rays. Observing these regions allows astronomers to uncover the hidden history of the galaxy. They reveal areas where powerful events once occurred, shaping the surrounding environment. Some of the radiation comes from electrons spiraling through magnetic fields or from gas heated to extraordinary temperatures. These glowing zones serve as reminders that the galaxy has experienced many energetic episodes. Even though the original explosions may have happened long before humans existed, their echoes still travel through space. This quiet radiation tells stories of enormous forces that once stirred the Milky Way, leaving behind traces that linger for millions of years. At the galactic center, clouds move with speeds that defy intuition.
Near the heart of the Milky Way, clouds of gas behave in ways that seem almost unreal. These clouds orbit close to the central black hole, where gravity becomes incredibly strong. As a result, they move with speeds that are difficult to imagine. Some clouds race around the center at hundreds of kilometers per second, tracing elongated loops shaped by the uneven distribution of mass in the region. The environment here is dense with radiation, magnetic fields, and swirling stars. These factors create turbulence that twists and stretches the clouds into strange shapes. Observing them requires infrared and radio telescopes because thick layers of dust block visible light. When scientists track their movement, they see gas rushing, colliding, and flowing in spirals that reveal the invisible structure of the core. These rapid motions also help astronomers estimate the mass of the central black hole by showing how strongly the region pulls on its surroundings. The pace and energy of this environment contrast sharply with the calm appearance of the night sky. Deep inside the Milky Way, the clouds dance at unimaginable speeds, shaped by forces far stronger than anything found near Earth. Some worlds orbit their stars in minutes instead of years. Not all planets follow slow, sweeping orbits like the ones we know in our solar system. In the Milky Way, there are worlds that circle their stars so closely that they complete an orbit in minutes. These ultra-rash short-period planets hug their stars so tightly that the side facing the star becomes incredibly hot, while the far side remains much cooler. Their paths are shaped by intense gravity and fierce radiation that constantly pulls at their atmospheres. Many of these worlds may have lost much of their original material, leaving behind dense, rocky cores. Their proximity to their stars means that they move at extraordinary speeds, sometimes traveling tens of kilometers per second. Studying these planets helps scientists understand how worlds evolve under extreme conditions. They reveal how orbits shrink over time and how planets adapt to intense heat. These rapid orbits also create unusual cycles of day and night. The idea of a year lasting only a few minutes challenges our sense of planetary motion and highlights the incredible variety of systems that exist throughout the galaxy. There's more mass outside the disk than inside. Most of the Milky Way's visible stars lie within the flat, luminous disk, but the majority of its mass resides elsewhere. The galaxy is surrounded by an enormous dark matter halo, extending far beyond the furthest stars. This halo holds the galaxy together,
outweighing the disk by a large margin. It is populated sparsely with ancient stars and globular clusters, but its true bulk is unseen. When we think of the Milky Way, we picture its spiral arms and starry plane. But that's only the glowing surface.
The mass that defines the galaxy, its gravity, its motion, its reach, is mostly hidden, enveloping everything like a quiet shroud. The Milky Way's core may have flared as a quasar. Today, the heart of our galaxy appears quiet, but there is evidence that it was once dramatically more active. The presence of huge gamma-ray structures, like the Fermi bubbles, and traces of high-energy light reflected in surrounding clouds suggest that the supermassive black hole at the center may have once flared as a quasar, a brilliant, violent beacon fueled by infilling matter. Quasars are among the brightest objects in the universe, outshining entire galaxies. If the Milky Way once burned like this, it would have looked dramatically different. A spiral wrapped around a blinding heart of light. That time has passed, but the echoes remain. The galaxy's structure changes over billions of years. Galaxies may look timeless, but they are always evolving. Spiral arms shift. Bars form and dissolve.
Gas flows inward and outward.
Stars are born and die, leaving behind a changing population. Even the shape of the Milky Way's disk, warped, rippling, and lopsided, is slowly altering. Encounters with dwarf galaxies and dark matter can bend or twist the structure. Over billions of years, the galaxy's silhouette has shifted like a drifting cloud. The Milky Way of today is not the one that was, and not the one that will be. Its beauty lies not in permanence, but in quiet transformation. Gravitational waves ripple through the galaxy from distant mergers. All across the universe, massive objects collide. Black holes spiral together. Neutron stars crash, and entire galaxies merge. These events send out gravitational waves, ripples in the fabric of space-time itself. Though faint, some of these waves pass through the Milky Way, distorting space by tiny amounts as they travel. They are incredibly difficult to detect, but observatories like LIGO and Virgo have already captured several.
New experiments aim to detect the background hum of gravitational waves that fills the cosmos. Even now, as you rest, space itself is shifting. Not enough to feel, but enough to tell us that somewhere far away, the universe is changing. Some planets in our galaxy orbit two suns at the same time. Across the Milky Way, there are planets that do not circle a single star, but move gracefully between two. These worlds orbit binary stars, following paths shaped by the combined pole of both suns, depending on the distance between the stars. A planet may move around them together as if they were a single glowing center, or weave an orbit between them in a more complex pattern. Sunrises and sunsets on such worlds would be unlike anything imaginable on Earth. Sometimes both suns would rise at once. Other times, one would set as the other climbed into the sky. The climate on these planets can be unusual, shaped by constant changes in heat and light. These systems reveal how flexible planetary formation can be. Instead of being disrupted by the presence of two stars, the surrounding disk of gas can still gather into planets that find stable paths. Studying these systems helps astronomers understand how planets adapt to different environments and how common these arrangements might be. The idea that entire worlds orbit twin suns
adds a quiet sense of wonder to the Milky Way, showing that nature often builds more creative structures than we expect. Antimatter clouds hide near the galactic center. Deep near the center of the Milky Way lie traces of something rare and mysterious. Antimatter, a form of matter that behaves like an opposite twin to normal particles, appears in faint clouds in this energetic region. These clouds are not thick or bright, but their presence can be detected through the radiation produced when antimatter meets normal matter and annihilates. The origins of this antimatter are still being studied.
It may come from the activity of massive stars, energetic jets near the central black hole, or interactions within dense clouds of gas. Because antimatter is difficult to produce and even harder to preserve, its presence in the galaxy is surprising. Studying these clouds helps scientists learn about the high-energy processes happening in the central region. It reveals conditions that cannot be recreated on Earth, where intense gravity, strong magnetic fields, and frequent stellar explosions combine. These subtle signals show that the center of the Milky Way is far from quiet. It is a place where unusual forms of energy gather, offering clues about the strange and powerful events that shape our galaxy's core. Long tidal streams expose the lingering ghosts of galaxies the Milky Way once absorbed. Spanning our galaxy are thin, graceful ribbons of stars, drifting through space like spectral traces. These tidal streams are the remnants of smaller galaxies that strayed too close.
Over vast stretches of time, the Milky Way's gravity tore them apart, spreading their stars along the routes they once followed. Each stream preserves the memory of a galaxy that once possessed its own form and structure. By examining their motions and compositions, astronomers can reconstruct the stories of these lost companions. Some streams arc far above the galactic plane, while others weave through the spiral arms. Their contours reveal how the Milky Way grows by taking in smaller galaxies. These streams also trace the distribution of dark matter because their paths curve in response to unseen structures enveloping the galaxy. Tidal streams remind us that the Milky Way carries a long, dynamic history. It has met and interacted with many neighbors, each encounter leaving behind a faint, beautiful signature. These stellar remnants drift silently through the night, carrying stories older than Earth itself. Binary stars sometimes spiral together until they collide. In many parts of the Milky Way, stars form in pairs rather than alone. These binary stars circle each other in a gravitational dance that can last billions of years. Over time, some pairs slowly spiral inward. Their orbits shrink as they exchange energy through tides, stellar winds, or interactions with surrounding material. Eventually, the stars can grow close enough to merge. This collision produces an enormous burst of light and energy, sometimes creating a brief but spectacular event known as a luminous red nova. The merged star often becomes larger and brighter than either of its predecessors. Binary collisions help enrich the galaxy with heavy elements because material is mixed and heated during the merger. Studying these dramatic unions helps astronomers understand how stars evolve and how certain rare objects are formed. Although the process takes an immense amount of time, the idea that two stars can slowly fall toward one another until they become one adds a poetic sense of motion to the Milky Way. Even in the calm night sky, quiet celestial dances are unfolding in ways we can only begin to imagine. Magnetic fields shape the flow of cosmic dust. Interstellar dust, tiny grains of carbon and silicate, moves not just under gravity,
but also under the influence of the galaxy's magnetic field. These fields thread through the Milky Way like invisible currents, guiding the motion of charged particles and influencing how gas and dust align. In some regions, dust grains spin rapidly, emitting faint microwave light. In others, they align with magnetic lines, polarizing the starlight that passes through them. Understanding these effects helps astronomers trace the magnetic field structure and even remove its influence from cosmic background studies. Dust is not passive. It dances to a magnetic rhythm, following hidden patterns in the dark. Some stars are enriched by neutron-star collisions. When two neutron stars spiral together and collide, they create one of the most violent events in the universe, a killer nova. In this brief, blinding explosion, enormous quantities of heavy elements are forged. Gold, platinum, uranium, and more. These materials are cast into space, mixing with gas and eventually forming new stars. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched in elements that could only have come from such collisions. They're not just luminous bodies, but record keepers of ancient cataclysms, burning with the residue of stellar wreckage and cosmic alchemy. The Milky Way may have a hidden bar within a bar. At the heart of the galaxy lies a bar of stars, an elongated bridge of light crossing the central bulge.
But deep within that bar, astronomers have found hints of another, smaller bar, tilted at a different angle, rotating independently. This inner structure is difficult to see directly, obscured by dust and distance, but its gravitational influence appears in the motion of nearby stars and gas. Bars like this may help funnel material toward the supermassive black hole, feeding it and shaping the dynamics of the core. The Milky Way's center is not one simple shape. It's a layered, shifting labyrinth of light and motion. Gas inflows feed the galaxy from the cosmic web. The Milky Way is not a closed system. It draws in fresh gas from the intergalactic medium, long, tenuous streams flowing through the vast cosmic web. These inflows provide the raw material for new stars, replenishing what the galaxy loses over time. Some gas arrives as cold filaments, slipping quietly into the disk. Other streams fall in hotter, shock-heated forms, lighting up in ultraviolet or X-ray light.
These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early cosmos. Some stars pulse in brightness like celestial heartbeats. There are stars in the Milky Way whose light rises and falls in rhythmic cycles. These pulsating stars expand and contract as their internal layers shift under the influence of heat and pressure. Each change in size alters the amount of light they emit, creating a pattern that can last hours, days, or months. The pulses act like heartbeats, revealing details about the star's interiors that cannot be seen directly. By studying the timing and strength of these pulses, astronomers can determine a star's mass, age, and temperature. Some of the most well-known pulsating stars are used as cosmic distance markers because their brightness patterns follow predictable rules.
These stars help map the structure of the Milky Way by providing reliable measurements for distant regions. Pulsation can occur in young stars, aging giants, or stars in transitional stages of their lives. Each category has its own signature rhythm. The gentle flickering of these stars adds a quiet sense of movement to the galaxy, reminding us that even stable-looking points of light can contain complex rhythms deep within their glowing layers. Shockwaves from ancient supernovas
still travel through the galaxy. Long after a supernova fades from view, the shock wave it created continues to move outward. These waves sweep through the Milky Way like expanding ripples, carrying the energy of the original explosion far across space. As they travel, they compress gas clouds, heat interstellar material, and leave subtle changes in their wake. Some shock waves move through regions filled with dust, sculpting it into new shapes. Others pass through more empty areas, gradually weakening, yet still preserving the memory of their violent origins. These shock waves can take tens of thousands of years to expand to their full size. Along the way, they can trigger new star formation by compressing cold regions of gas. They also enrich the interstellar medium with heavy elements created in the supernova. Modern telescopes can detect these shock waves by observing the faint X-ray and radio emissions they produce. They appear as expanding shells or filaments that reveal the structure of the surrounding space. Even though the star that created them may be long gone, its influence continues to travel quietly through the galaxy, shaping the environment for future generations of stars. Dust in the Milky Way was forged in the final breaths of dying stars. The dust that fills the Milky Way has a dramatic origin. Much of it was created in the outer layers of aging stars as they reached the ends of their lives. As these stars expanded into red giants, their outer atmospheres cooled enough for tiny solid particles to form. When the stars shed their outer layers, these particles escaped into space. Other types of dust were created when massive stars exploded in supernovas, releasing freshly formed elements into the interstellar medium. Over time, dust grains drifted throughout the galaxy, becoming essential ingredients in the formation of new stars and planets. They help cool collapsing gas clouds, shield molecules from radiation, and provide surfaces on which chemical reactions can occur. Dust absorbs and scatters starlight, giving the Milky Way its soft glow and shaping the appearance of nebula. Each grain carries the legacy of the star that created it. The thought that the dust in the galaxy, and even the dust that eventually formed Earth, came from the dying breaths of ancient stars adds a gentle sense of connection to the larger cycles of cosmic life. A few stars orbit the galactic center with incredible speeds. Near the center of the Milky Way lies a region where gravity grows exceptionally strong. In this dense environment, a handful of stars orbit at extraordinary speeds, far faster than stars located in the more distant spiral arms. These rapid motions were first detected through careful tracking of each star's position over many years. Their tight, fast orbits provide compelling evidence for the presence of a supermassive black hole at the core of the galaxy. As these stars swing close to the center, they follow curved paths shaped by intense gravitational forces. Their motion allows astronomers to calculate the mass of the unseen object controlling their orbits. These stars also help reveal the structure of the central region, which is filled with complex clouds of gas, magnetic fields, and radiation. Despite the extreme conditions, the stars themselves are stable, shining quietly as they trace their dramatic paths. Observing them requires advanced infrared telescopes that can see through the thick dust surrounding the core. Their speed and precision offer rare insight into one of the most mysterious areas of the Milky Way, a place where space is warped by immense gravitational power. The Sun was likely born in a stellar cluster. Stars rarely form in solitude. They're usually born in groups, stellar clusters shaped from the same collapsing cloud of gas and dust. Our Sun was almost certainly one of these. Long ago, it shared space with hundreds, perhaps thousands of sibling stars, all born in the same cradle. Over time, gravitational tides, passing stars, and the motion of the galaxy scattered the cluster. Most of the Sun's siblings have wandered far, flung into different orbits, carrying with them fragments of our shared past. Some may still shine nearby, invisible among the stars, lost family in a sea of light. The Sun's siblings are scattered across the galaxy.
Though the Sun's birth cluster has long since dissolved, astronomers are searching for its lost siblings, stars that share its age, motion, and chemical fingerprint. Using vast surveys like GIA and spectroscopic databases, researchers hope to identify these long-lost relatives. A few candidates have emerged, stars that may have shared our origin, formed from the same cloud of enriched gas. If found, they could reveal details about the conditions in which the Sun and the early solar system were born. Our place in the galaxy is not entirely solitary. Somewhere out there, the Sun's ancient kin may still shine. The galactic disk wobbles as it spins. The Milky Way's disk is not perfectly flat. It wobbles gently, rippling like a spinning plate nudged off balance. This warp is most visible in the outer regions, where the disk bends upward on one side and downward on the other. It may be caused by the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries. The wobble rotates slowly, like a vast wave moving through the stars. From Earth, we don't feel it, but from afar, the Milky Way is not a pristine spiral. It is a breathing, undulating sheet of stars, curving gently as it turns. Galactic tides can distort star clusters and streams. Just as the Moon's gravity pulls tides on Earth, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, and even globular groups feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, drawing out long stellar streams or peeling stars away from their orbits. Many of the faint arcs of stars mapped across the sky are remnants of such encounters. Clusters in the process of being unraveled, galaxies slowly torn apart. The galaxy doesn't break these structures suddenly. It unravels them patiently, strand by strand, over millions of years. Radio waves from the Milky Way reveal the echoes of exploding stars. Across the Milky Way, ancient explosions leave behind signals that travel farther than light from their shattered shells. These signals appear as radio waves, gentle in tone but powerful in reach. When a star dies in a supernova, the blast sends shock waves rippling through space. Those shock waves energize surrounding gas, causing it to glow in radio frequencies that can cross vast distances without fading quickly. Even long after the visible light of the explosion has dimmed, the radio glow remains, drifting quietly through the galaxy. Astronomers use sensitive instruments to trace these faint echoes, mapping the structure of old remnants hidden inside dusty regions. Each ripple carries information about the force of the explosion, the shape of the expanding cloud, and the materials released into space. These waves reveal the hidden history of stellar deaths that once enriched the galaxy with heavy elements. They allow us to study events far older than humanity, reaching into eras when entire regions of the Milky Way looked completely different. In this soft radio light, the galaxy speaks of its past, whispering memories of stars that lived brightly and ended in dramatic silence. A teaspoon of a neutron star would weigh more than a mountain. Neutron stars are among the densest objects in the universe, formed when massive stars collapse in on themselves after a supernova. Their matter becomes so tightly packed that ordinary atoms cannot survive. Protons and electrons merge into neutrons, creating a substance unlike anything on Earth. If you could take a teaspoon of this material, something no human could ever actually do, it would outweigh a mountain. This
unimaginable density reshapes the way light, magnetism, and gravity behave nearby.
Neutron stars can spin rapidly, sending beams of radiation sweeping across space. They also generate magnetic fields far stronger than anything produced by human technology.
Their surfaces are incredibly smooth, with gravity so intense that even a small bump cannot exist for long. These strange remnants cool slowly over millions of years, gradually fading as they release trapped heat. Studying them helps scientists understand the limits of matter and the conditions that exist in extreme environments. The thought that so much mass can be compressed into such a tiny space inspires a deep sense of wonder. Neutron stars remind us that the universe holds states of matter far beyond everyday experience. The Milky Way contains star streams that stretch across the sky like ancient rivers. Throughout the galaxy, long chains of stars drift together along gentle arcs. These star streams are the remains of smaller galaxies and clusters that were once whole, but slowly pulled apart by the Milky Way's gravity. As they were stretched, their stars scattered along their original orbits, forming sweeping trails that can span great distances. Although faint, these streams act as records of the Milky Way's past interactions. By studying their shapes and motions, astronomers can reconstruct the histories of the galaxies that contributed them. Some streams curve high above the galactic disk, while others flow quietly within it. They reveal how gravity sculpts the structure of the Milky Way over time, redistributing stars across enormous scales. These delicate ribbons also help scientists map the invisible dark matter halo surrounding the galaxy. The paths of the stars trace the gravitational field, allowing researchers to understand how unseen mass shapes their motion. In a quiet way, star streams show that the Milky Way is constantly evolving. They carry memories of ancient encounters stretched across the sky, like soft reminders of the galaxy's long and complicated history. New stars ignite in our galaxy every single second. Across the Milky Way, star formation never truly stops. In cold and shadowed clouds scattered throughout the spiral arms, new stars emerge as gravity pulls gas together into dense pockets. These pockets slowly compress until temperatures rise high enough for nuclear fusion to begin. That moment marks the birth of a star. Although it may seem incredible, this process happens so often across the vast disk of the galaxy that new stars ignite every second. Some are tiny red dwarfs that will burn quietly for trillions of years. Others are larger and brighter, destined to live fast and end in powerful supernovas. The locations where star formation occurs are shaped by turbulence, magnetic fields, and the leftover material from older generations of stars. Light from newly formed stars gradually clears surrounding dust, revealing clusters that shine against the darker background. These young stars also influence their environment by sending out energetic winds, sculpting the clouds that created them. The continuous birth of stars is one of the processes that keeps the Milky Way alive and dynamic. It ensures that even as older stars fade, new sources of light are always appearing. Some stars escape the galaxy entirely. Most stars are gravitationally bound to the Milky Way, but occasionally, a star reaches escape velocity over 500 kilometers per second and is flung outward, never to return. These hypervelocity stars are rare but real.
Some are thought to be ejected by interactions with the supermassive black hole at the galaxy's center. Others may be slinging-shotted by three-body encounters or supernova in binary systems. Once free, they travel alone into intergalactic space. Tiny lighthouses drifting far beyond the spiral's edge. They carry the galaxy's memory outward, becoming solitary pilgrims in the great dark between galaxies. The Milky Way contained stars fro. Not all stars within the Milky Way were born here. Some may have originated in other galaxies, captured during mergers, or flung into our halo from distant regions of the local group. These intergalactic wanderers often move on unusual orbits far from the disk, tracing paths through the outskirts or halo. They can be identified by their composition or motion, stars that don't quite fit the local patterns. Like cosmic immigrants, they bring stories from other environments, other histories, other skies. The Milky Way is not a sealed system. It is a living mosaic, slowly stitched together by time and motion. There's a fountain of gas cycling between the disk and halo. Above and below the Milky Way's bright disk, gas rises and falls in a quiet loop known as the galactic fountain. Supernova and stellar winds heat and eject material upward into the halo, where it cools, condenses, and gently rains back down over millions of years. This cycle stirs the interstellar medium, redistributes heavy elements, and helps regulate star formation. It's a quiet respiration, a breathing motion of matter between the dense plane and the vast halo. The galaxy in this way doesn't just spin, it circulates. It exhales and inhales, keeping its structuring motion across immense spans of time. The galaxy's dust grains carry organic compounds. Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and more. Though not alive, they are chemically rich, formed in the atmospheres of dying stars or within cold clouds shaped by radiation. These tiny grains, carried across light years by galactic winds, settle into the gas that forms stars and planets. Some may have fallen onto the early Earth. The galaxy's dust is not just debris. It is a cargo of potential, drifting silently through the dark. The sun races through the Milky Way faster than a bullet. We often think of the sun as steady and still, a warm and familiar anchor in the sky. Yet in reality, it is hurtling through the galaxy at a speed far beyond anything we can experience on Earth. It moves faster than a bullet, sweeping our entire solar system along with it. Everything you know, every planet, every moon, every drifting speck of dust is riding this grand motion. The sun follows a curved path around the center of the galaxy, guided by gravity and shaped by the mass of countless stars. Even though we cannot feel this motion, it is always happening. It shapes the long future of our solar system and determines how we drift through different regions of the Milky Way. As the sun journeys on, it encounters clouds of gas, faint radiation fields, and shifting gravitational currents that subtly influence the space around us. This silent voyage has lasted for billions of years and will continue for billions more. The thought that our familiar star is actually a traveler in an enormous galactic orbit invites a quiet sense of awe. We are passengers on a journey that never stops. Stars are born in clouds so cold, but fire cannot form there. When most people imagine starbirth, they picture heat, flames, and blazing energy. The truth is far stranger. Stars begin in clouds that are colder than anything on Earth. So cold that fire is impossible. These clouds are made of dust and gas drifting through the Milky Way. They look dark to our eyes because they block starlight. Inside them, temperature drops to levels where molecules move slowly and gently. Gravity does the work that fire cannot. It gathers the cold material, pulling it together until it forms dense pockets. As these pockets grow heavier, they contract even more. Slowly, through pressure alone, the center begins to warm. Over long stretches of time, the temperature climbs, and only when it becomes incredibly high does nuclear fusion finally ignite. That moment transforms a silent, cold cloud into a shining star. The idea that brilliant suns begin as chilled, shadowed knots of dust feels almost like a cosmic secret. It tells us that creation often begins in stillness. Before any light appears, the galaxy forms its stars in quiet places, where heat is only a distant dream. Our solar system floats in a giant bubble carved by ancient stellar explosions. We live inside a vast cavity in space without ever noticing it. Long before humans existed, powerful stars near our region of the galaxy lived fast lives and ended in explosive deaths. Those explosions pushed away enormous amounts of gas, clearing out a wide area. The result is a giant bubble that surrounds our solar system. This bubble is filled with thin, hot gas created by the shock waves of ancient supernovas. The material here is far less dense than the gas found elsewhere in the Milky Way. Our sun and planets drift comfortably within this airy region, moving through it as if passing through a quiet room left behind by violent events. The edges of the bubble are shaped like walls of cooler gas, with the remnants of those explosions finally slowed down. Astronomers can map this structure by tracing the faint light emitted by the gas inside it. Realizing that our entire solar system sits within the remains of long-vanished stellar giants brings a soft and humbling perspective. We are surrounded by the quiet echo of ancient cosmic events that shaped the space we now call home. The Milky Way is slowly consuming smaller galaxies. Galaxies may look peaceful from a distance, but they are dynamic structures that interact and merge over long stretches of time. The Milky Way is no exception. It is slowly drawing in several smaller galaxies that orbit nearby. Their stars are stretched into long streams that wrap around our galaxy like ribbons. These streams reveal the paths of the smaller galaxies as they are gradually torn apart. Gravity pulls them in bit by bit until their stars become part of the Milky Way itself. This process has happened many times in the past, and it will continue far into the future. It helps explain the presence of old star clusters and unusual stellar populations scattered throughout the galaxy. The Milky Way grows through these ancient mergers, absorbing the remains of smaller companions. Even now, faint galaxies like the Sagittarius dwarf are being pulled apart as they fall inward. The idea that our galaxy is shaped by a long history of gentle and relentless cannibalism feels both strange and fascinating. It reminds us that even structures as vast as galaxies are still influenced by the quiet pull of gravity. The farthest stars orbit well beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light years from the center. These stars move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches like distant sentinels. They are faint, sparse, and far between, but they help define the galaxy's size, shape, and gravitational influence. The Milky Way is not just what we see.
It extends deep into the dark, shaped by wanderers at its edge.
The Milky Way's shape is lopsided in several ways. Though often pictured as a symmetric spiral, the Milky Way is subtly lopsided. One side of the disk is thicker than the other. The spiral arms are uneven in brightness and reach, and even the stellar halo sits slightly off-center. These asymmetries likely come from gravitational encounters with the Magellanic Clouds, with clumps of dark matter, or with remnants of past mergers. The galaxy is not a flawless pinwheel. It is a living structure, shaped by poles and distortions, like a spinning dancer whose skirt has been caught by the wind. Its beauty is found in that irregularity, a poised imbalance sculpted over time. Astronomers map the galaxy using variable stars. Certain stars rhythmically change their brightness, swelling and shrinking like slow, glowing heartbeats.
These are variable stars, and some types, such as Cepheids and RR Lyrae, follow precise relationships between how bright they are and how long their pulses last. By measuring the time it takes for a star to brighten and fade, astronomers can determine its true luminosity, and by comparing that to how bright it appears, its distance. These stars act as cosmic yardsticks, allowing us to chart the Milky Way's shape, structure, and scale. They are lights that measure the dark blinking markers scattered throughout the spiral. The Gaia mission is revolutionizing our understanding of the Milky Way. Launched by the European Space Agency, the Gaia spacecraft is creating the most precise map of the Milky Way ever made. By measuring the positions, motions, and brightness of over 2 billion stars, Gaia reveals the galaxy's three-dimensional structure and its motion through time.
It has uncovered streams from shredded galaxies, mapped the warp of the disk, and traced the sun's orbit with exquisite detail. With each new data release, GIA deepens our understanding, turning a hazy smear of stars into a sharp, living map. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars. Our galaxy is so vast that light needs 100,000 years to cross it. When you imagine light, you might picture something impossibly fast. It slips across a room in an instant and touches your eyes before you even notice it has moved. Yet, when that same light tries to cross the Milky Way, it becomes almost slow in comparison. It would take it 100,000 years to go from one end of our galaxy to the other. That distance is so enormous that it stretches the imagination. The space between the stars is not empty, but it is open enough that light travels freely through it, rushing past dust grains and drifting atoms.
The sheer scale means that when we look deep into the Milky Way, we are not seeing it as it is now. We are seeing layers of history stacked across unimaginable distances. The light from distant regions began its journey long before any human being existed. Every faint shimmer in the sky carries a fragment of ancient time. It reminds us that even the fastest thing in the universe becomes gentle and patient when measured against the size of our cosmic home. A supermassive black hole sits at our center, with a grip strong enough to bend space. Deep in the heart of the Milky Way lies something that cannot be seen directly, yet its presence shapes the entire galaxy. A supermassive black hole waits there, hidden behind clouds of dust and stars that whirl around it at incredible speeds. Its gravity is so intense
that it bends the very structure of space. Stars near the center trace looping paths that reveal the invisible mass guiding their motion.
At great distances, its influence is gentle, but close to the core, it becomes overwhelming. Gas clouds stretch and twist as they fall inward, heating up and glowing as they spiral toward the dark center. Although the black hole itself is silent, the region around it pulses with activity, created by matter rushing into its grasp. This hidden heart anchors the Milky Way, giving shape to its rotation and helping bind its stars together. Imagining something so powerful and yet so quiet, something that can bend space without light or sound, invites a deep sense of wonder. The center of our galaxy is not a calm place, but a restless zone ruled by an unseen giant. The Milky Way once swallowed a galaxy nearly half its size. In the deep past, a large companion galaxy drifted too close to the Milky Way and was gradually pulled apart by powerful tides. Its stars, star clusters, and streams of debris were absorbed into the halo, becoming part of the structure we see today.
Evidence of this ancient feast appears in the form of unusually energetic stars and broad sweeping arcs of stellar material that trace the remains of the lost system. Astronomers can still identify these fragments by studying their motion and chemical fingerprints, which differ from those of stars born within the Milky Way. This event may have thickened the galactic disk, stirred its dark matter halo, and influenced the development of the spiral arms. It stands as a reminder that galaxies grow through acts of cosmic consumption, absorbing entire systems over immense stretches of time. The Milky Way we know carries within it the remnants of this vanished giant, a ghostly companion whose stars now shine as part of our own celestial home. Our galaxy is surrounded by dozens of ancient satellite galaxies. Encircling the Milky Way is a quiet community of smaller galaxies, each one carrying memories of a much earlier universe.
These companions drift in long, graceful orbits, some so faint that they blend almost completely into the dark around them. Their stars are often old and lightly populated, giving them a fragile appearance. Yet they play an important role in the Milky Way's evolution. Their slow passages tug at our galaxy's outer halo, stirring subtle waves that ripple through the dark matter envelope. Some have already begun to shed delicate streams of stars, leaving pale trails that wrap around the Milky Way like ancient threads. Studying these companions reveals how large galaxies grow, not through sudden events, but through countless, gentle interactions spread across unimaginable spans of time. They move like elders around a great family, each one preserving a chapter of cosmic history, but deepens our understanding of how the Milky Way became the spiral we know today. The galactic plane marks a dense path of stars. If you look up on a dark night, away from city lights, you may see a hazy river of starlight crossing the sky. That's the galactic plane, the thickest slice of the Milky Way's disk. It's not a line, but a depth, a vast, flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed, dust is layered, and star formation is common. From our vantage point, we're looking along the grain of the galaxy, peering through its richest corridors. This band isn't just beautiful, it's the crowded, humming heart of where most stars live and die. The night sky is brightest toward the galactic center. The core of the Milky Way lies in the direction of the constellation Sagittarius, a rich, glowing concentration of stars, dust, and unseen mass. From Earth, we can't see the very center in visible light. Dust clouds obscure our view,
but the area glows with brightness in infrared and radar.
Even with the naked eye, the region appears more crowded, more luminous, filled with the overlapping light of billions of stars. We orbit far from the center, in a quiet suburb of the galactic disk. But when we look inward, we glimpse the crowded city at the galaxy's heart. We see the Milky Way jawn from Earth. Because we live within it, we cannot look down on the Milky Way from above. Instead, we see it from the inside. A flat ribbon of stars stretching across the sky, curved only by the horizon. This jawn view compresses the galaxy into a single arc, making it hard to grasp its full structure from our perspective. It took centuries of observation, cataloging, and mathematical deduction to realize the spiral we belong to. From Earth, we gaze through its disk like standing in a forest and looking along the line of the trees. We do not see the shape we're part of, only the vastness that surrounds us. The galaxy holds far more than we can ever possibly see. Even with our most sensitive instruments, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust. Motion is hidden in silence. Dark matter outnumbers luminous stars. Between every star lies emptiness, and within every empty space, potential. The Milky Way is not just what we see, it is what we suspect, what we infer, what we long to understand. It holds ancient light, future stars, drifting worlds, and questions still without answers. And within that vastness, somehow we find ourselves, one planet among many, orbiting a quiet star, floating through a story too wide for the eye. Some stars here are more than twice as old as Earth. The Milky Way holds stars that formed long before Earth ever existed. Some of them are more than twice as old as our planet. These ancient stars provide a glimpse into the early days of the galaxy. They carry chemical signatures that reveal what the universe was like shortly after the first generations of stars lived and died. Old stars contain fewer heavy elements because those elements had not yet been created in large amounts by earlier supernovas. Their light is different, their atmosphere simpler, and their stories longer. Many of these stars drift in the galactic halo, a sparse region surrounding the Milky Way. They move on orbits that take them high above the spiral arms. Observing them allows astronomers to study the early universe in a quiet and direct way. These ancient suns burn steadily, holding secrets from a time when the galaxy was still new. Their existence adds a deep sense of continuity, a reminder that long before our world formed, the Milky Way was already shining with the light of its earliest stars. The galaxy glows with light from stars too faint for any telescope to see. When we look at the Milky Way on a clear night, we see a glowing band stretching across the sky. Much of that glow comes from stars so faint that not even powerful telescopes can pick them out individually. These stars are small and dim, but they are incredibly numerous. Their combined light forms a soft background that fills the disk of the galaxy. Dust and gas scatter this light, giving the Milky Way its hazy appearance. Even though these faint stars are individually invisible, they contribute significantly to the mass and structure of the galaxy. They help shape the gravitational pull that guides the motion of brighter stars. Some of them are old red dwarfs that burn slowly and quietly. Others are young stars just beginning their long lives. The idea that the galaxy shines with the collective breath of countless unseen suns creates a gentle feeling of mystery. The light we see is not just the glow of a few bright stars, but the soft chorus of multitudes
that whisper across the sky. Rogue planets drift through the Milky Way without a sun. Not all planets belong to a star. Some worlds move freely through space, drifting alone through the darkness. These rogue planets were likely born in solar systems, but were later cast out by gravitational interactions. Without a sun to warm them, they travel through the galaxy in deep cold. Their surfaces may be frozen, yet some could hide warm interiors powered by internal heat. The idea of planets wandering alone creates a haunting sense of quiet beauty. These worlds do not follow predictable orbits. They move on long paths shaped only by the gravity of the galaxy itself. They may pass near stars, slip through clusters, or disappear into the galactic halo. Although difficult to detect, their presence is predicted by simulations and hinted at by faint observations.
There may be far more of them than planets that orbit stars. Thinking of these silent travelers drifting through the Milky Way invites a calm sense of wonder. In the vast, dark spaces between the stars, entire worlds glide unseen, cold and solitary, carrying their own stories through the night. A halo of gas hotter than any flame on Earth surrounds our galaxy. Far beyond the spiral arms of the Milky Way lies a massive halo of extremely hot gas. This halo extends for great distances above and below the galactic disk. The gas within it is heated to temperatures far hotter than any flame found on Earth. It becomes so energized that it emits faint X-ray light. Although extremely thin, it contains enough mass to influence the motion of stars and satellite galaxies. This halo is thought to be a leftover from the early formation of the Milky Way, as well as the ongoing activity of supernovas that push material outward.
It also acts as a reservoir of matter that may one day fall back into the galaxy, fueling new star formation. The halo is invisible to normal sight, yet it surrounds everything we know. It is a reminder that the Milky Way is not just a flat disk of stars, but a layered and intricate structure with components that stretch far into space. This hot, quiet atmosphere envelops our galaxy like a vast and ancient cloud. Interstellar clouds may seed solar systems with ingredients for life. The birthplaces of stars are also the birthplaces of worlds. As planetary systems form from collapsing clouds of gas and dust, they inherit the chemical fingerprints of their parent nebula. If that cloud contains water, carbon compounds, and other building blocks of biology, those ingredients may end up in comets, asteroids, or planets. Some regions of the Milky Way are especially rich in such prebiotic chemistry.
We don't yet know how common life is, but the conditions for it seem to arise naturally.
The seeds of life may be scattered far and wide, tucked into the galaxy's coldest cradles, waiting for a place to grow. Some stars rotate hundreds of times faster than the Sun. Most stars spin, but some spin incredibly fast, completing a full rotation in just a few hours. These rapid rotators are often young, massive, and unstable, with equators that bulge from centrifugal force. A few reach such high speeds that they fling off material, forming glowing disks around themselves. The Sun rotates once every 25 to 35 days, depending on latitude. But these fast-spinning stars rotate hundreds of times more quickly, approaching physical limits. Their internal structures and evolutionary paths are different. Their lives may be brief, but while they last, they spin like sirens in the dark. The galaxy is tilted relative to the ecliptic.
From Earth, the Milky Way arcs across the night sky in a graceful band of light. But it doesn't align with the plane of our solar system.
The galactic plane, the flat disk in which most of the galaxy's stars reside, is tilted about 60 degrees relative to the ecliptic, the path traced by the Sun and planets. This tilt is why the Milky Way rises at an angle and why it shifts position with the seasons. We are part of the galaxy, but our own little system is angled slightly askew, a small tilted boat drifting through a larger spinning sea of stars. Some stellar remnants are older than the galaxy's disk. Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of one's luminous stars that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled. Their existence hints at an earlier time of star formation, a deeper history etched into the outer halo.
They have burned for billions of years, slowly fading, carrying with them the quiet residue of a time when the Milky Way was still gathering its shape. The disk may be bright, but the halo remembers further back. Some stars spin so rapidly they would fly apart without gravity. In the Milky Way, there are stars that rotate with astonishing speed. Their equators can move at hundreds of kilometers per second, far faster than the rotation of our Sun. If not for the immense pull of their own gravity, these stars would tear themselves apart. Their rapid spin causes them to bulge outward, forming flattened shapes rather than perfect spheres. This distortion affects the temperature on their surfaces, making their poles hotter than their equators. The fast rotation can also lead to strong magnetic fields and affect how material flows around them. Some of these stars eject gas into surrounding space, creating disks or rings that glow softly. Their speed influences how they evolve over time, affecting how they burn their fuel and how they will eventually die. Observing them helps astronomers understand the limits of stellar physics, revealing how fast a star can spin before breaking. These rapid rotators offer a glimpse into a more extreme side of the Milky Way, where gravity and motion balance each other with delicate precision. They show that even stars can experience tension between stability and the forces that push them outward. Enormous cavities in the Milky Way hold vast amounts of empty space. Not all regions of the galaxy are filled with stars and gas. Some areas are surprisingly empty, carved out by ancient events that swept material away. These enormous cavities can span hundreds of light years, leaving behind pockets of thin space inside the spiral arms. Many of them were created by clusters of massive stars whose intense winds and powerful supernovas pushed outward, clearing large sections of the surrounding medium. Over millions of years, these blasts hollowed out bubbles that merged into even larger voids. Although these regions contain fewer particles than their surroundings, they are still influenced by the gentle pressure of nearby gas and the gravitational pull of the galaxy. Studying these cavities helps astronomers understand how energy from dying stars shapes the Milky Way. They reveal where clusters once lived and how their activity influenced the surrounding environment. These vast pockets of emptiness contrast with the dense molecular clouds that form stars. They remind us that the galaxy is not uniform, but shaped by cycles of creation and destruction that leave behind both bright birthplaces and quiet gaps in the starlit landscape. Diamond worlds exist deep in our galaxy. Among the many strange planets in the Milky Way, some worlds are thought to be rich in carbon, to such an extent that their interiors may form diamond-like layers. These planets likely developed in regions where the materials available during their formation were different from those near our Sun. Instead of being dominated by silicate and metals, they contain high amounts of carbon that becomes compressed under intense pressure.
In the deep interiors of these worlds, that pressure can turn carbon into solid, crystalline structures similar to diamond. Their surfaces might be dark and rocky, but below lies a landscape shaped by exotic chemistry. These planets can orbit close to their stars or drift farther away depending on how they formed. Studying them helps scientists understand the wide variety of conditions that exist across the galaxy. They show that planets can differ dramatically from those in our own solar system.
Imagining entire worlds built from carbonary materials with glittering layers hidden beneath their crusts offers a quiet sense of wonder. These diamond worlds reveal that the Milky Way holds forms of planetary beauty far beyond anything we have seen on Earth. The Milky Way contains stars that release energy bursts powerful enough to scour planets. Some stars in our galaxy are capable of unleashing sudden bursts of energy that can dwarf the output of normal stellar activity. These bursts can occur when magnetic fields on the star's surface become twisted and then snap, releasing enormous amounts of radiation. The energy can be so strong that it would strip atmospheres from nearby planets or drastically alter their surfaces. These events are rare, but they show how unstable certain stars can be. The bursts travel through space as intense flashes of light and high-energy particles. Even from far distances, they can be detected by sensitive instruments.
Studying these outbursts helps astronomers understand the magnetic behavior of stars and the environments around them. Many of these stars are young and still settling into stable patterns of rotation and energy output. Others are older but possess unusually strong magnetic fields. These sudden eruptions remind us that stars are not perfect spheres of calm light. They can be dynamic and unpredictable, sending out powerful pulses that reshape the space around them. Some gas clouds orbit in polar directions. Not everything in the Milky Way follows the neat plane of the disk. Some clouds of gas, and even some stars, move in highly inclined orbits, passing above and below the galaxy's main structure. These polar orbits likely come from past mergers, when dwarf galaxies or stray clouds were captured at odd angles. Over time, they've continued to orbit on tilted paths, like comets around a planet.
These misaligned orbits are records of disruption. Visible remind us that the galaxy is not a closed system, but an evolving structure shaped by the unpredictable flow of cosmic history. Giant shells of gas surround past starbursts. In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some spanning hundreds of light years. These shells are the remnants of powerful starbursts, episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined winds and supernova carved out huge cavities in the interstellar medium, blowing gas outward in all directions. Over time, the expansion slows, but the shells remain, ghostly bubbles marking where the galaxy once burned bright with stellar birth and death. These are the fossils of cosmic fireworks, still echoing in the cold. Stars occasionally collide in dense regions. Space is vast, and stars are small. But in the densest regions of the Milky Way, such as the cause of globular clusters, stars can pass close enough to interact and even collide. When they do, the result can be dramatic: a burst of light, the merging of two suns, with the formation of a rare blue straggler star, one that appears younger than its neighbors. These collisions are rare, but not impossible. Over billions of years, the tightest stellar neighborhoods can rearrange themselves through gravity and chance. In these crowded stellar cities, time moves differently, and space is never quite empty. Binary stars can be torn apart by tidal forces,
Many stars live in pairs, orbiting each other in gravitational embrace. But even this bond can be broken. If a binary system passes close to the Milky Way's central black hole or through a dense cluster, tidal forces can disrupt their orbit, flinging one star away while the other is captured or slowed. In some cases, a companion is hurled out of the galaxy entirely, becoming a rogue star speeding through intergalactic space. These stellar breakups happen silently in places we rarely see. A quiet tearing of ancient partnerships by gravity's indifferent hand. Some planetary systems boast dozens of worlds. While our solar system contains a modest number of planets, the Milky Way holds systems far more crowded. Some stars are orbited by dozens of planets, each following its own path through space. These systems form when large disks of gas and dust collapse around young stars. The material gathers into many clumps that grow into planets over time. Because the disks are large and dense, they can produce far more worlds than the one that gave rise to Earth. These planets can be small or large, icy or rocky, close to their star, or drifting farther out. Their interactions create complex gravitational patterns that can shift over long periods.
Studying these rich systems helps astronomers understand how planets form under different conditions. They show how varied planetary architecture can be, even within a single system. The idea that some stars host entire families of planets far larger than our own adds to the sense of abundance in the Milky Way. It suggests that the galaxy may hold endless varieties of worlds waiting to be discovered. As we drift to the end of our quiet journey, take a moment to feel how wide the universe truly is. Every mystery we explore tonight is a reminder that our understanding is still young. Even after all the discoveries made by science, so much remains hidden in the deep, dark spaces between the stars. Every unanswered question is an open door. Every strange signal or unusual pattern is an invitation to look closer. The unknown is not something to fear. It is a landscape that continues to grow as we learn. If you enjoyed this calm voyage into possibility, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. Now, allow the quiet to settle. Let the mind loosen. Let the weight of the day fall away as the night wraps softly around you. There is nothing you need to solve, nothing you need to hold, only the slow comfort of drifting thought and the gentle feeling of rest rising to meet you. Good night.